Hello guys, welcome to a complete end-to-end LangGraph crash course for beginners. If you're looking to build powerful AI agents for your product, for your business, or even if you're looking to make your next big job switch, then this course is for you. By the end of this course, you will learn how to build powerful AI agents that can think for its own, it can make decisions for itself. If there is a human approval needed, it can pause its work and come to you for approval. And even this is the tip of the iceberg. And if this sounds too much for you, don't worry. This course is going to be very beginner friendly and we'll add on more difficulty and more concepts one step at a time. And by the end of this course, we are going to be building an AI agent that remembers your past conversations, streams information to the front end, answers questions if it knows the answer, else it smartly makes an internet search, pulls data from various URLs in the internet, as you can see right here, and gives you an accurate answer. Exactly like what Perplexity, a billion-dollar valued company, does. So let's actually go ahead and look at the course overview. So first, we will look at the different levels of autonomy in LLM applications. So autonomy meaning freedom. So starting with code, which has very little freedom to think on its own, right? It does exactly what we tell it to. And in the end, we have agents which have very high autonomy. It can think on its own, and that is exactly where LangGraph is going to come into the picture. But to get here, we will have to understand how we progressed here. Okay, so now understanding agents and tools, and this is where we'll be deep diving. Not just on what agents are, but actually look at how agents are built under the hood. Okay, so basically this would set a very strong foundation for us for the rest of our course. So yes, we'll learn them how to build them from scratch. Also, we will also be learning how to build agents using predefined classes that LangChain provides out of the box. And then we will understand the graph data structure, the differences between DAGs and cyclical graphs. So now that we've understood the prerequisites, then we will move on to what is LangGraph, why is it required, why not just stick with LangChain, right? What are the limitations of LangChain? So then with LangGraph, we will be building different agentic architecture patterns like the reflection agent, reflexion agent, multi-agent workflows, right? So we will understand all of the key terminologies that come with learning LangGraph, like what is a graph, what is a state, what is a node, right? What is visualization, what are breakpoints, etc., etc. Okay, so at that point, we would have learned enough to start building our very own LangGraph chatbot. The chatbot will have the ability to answer questions by searching the web. It will be able to route complex queries to humans for review. It can go back in the chain and then explore alternative paths. And this is where these agentic patterns like human in loop, React patterns come into the picture. Okay, so we will also build multi-agent systems like very similar to what Crew AI does. But I believe that LangGraph is much more powerful because it's much more low level and that gives us a lot more flexibility on how we can actually build the flows. Alright, so multi-agent systems meaning we basically create multiple agents and those agents can sort of communicate with each other to get a particular task done. And then we will integrate RAGs into LangGraph. So we will explore what C RAGs are, or it's basically called corrective RAGs. We will also see what A RAGs are. Basically, it means adaptive RAG and also self RAGs. And most importantly, we'll also be looking at how persistence works in LangGraph. Also learn some of the other tools that LangGraph provides to help build production grade agents, right? So like the LangGraph Studio is something that it provides. It provides LangGraph Cloud API, etc., etc. We'll also be looking at that. And finally, we will look at agents in production. So basically explore enough real life use cases so that you get a absolute complete picture for what is to come in the future of technology. So if this excites you, make sure to subscribe to the channel and hit the bell icon as well so that you'll be notified every time I release new videos. Now let's actually go ahead and look at the prerequisites for this course. So first thing obvious, Python, because we will be working with Python. And secondly, understanding of LangChain can be essential, and I'll tell you why. LangGraph, which we are going to be looking at in this course, uses LangChain's classes under the hood. For example, chat models, prompt templates, and these are things that LangChain provides, and learning that is going to be very important to continue with this course. So if you don't know LangChain already, I've already made a 2.5 hour long tutorial that teaches you in depth the concepts like, chat models, prompt templates, right? RAGs, agents and tools, right? So these are things that are very important. These are prerequisites. So if you're not familiar with these concepts, I would highly recommend that you watch LangChain video first and then come back to this particular video. So with that said, let's get started. In this section, let us explore the levels of autonomy in LLM applications. And this list is going to be starting from the least zero autonomy to maximum autonomy. So the first thing that we have is code. Code has zero autonomy and is 100% deterministic. We all know that everything is hard-coded and it is not even really a cognitive architecture. What are the disadvantages though? The problem is you would need to write rules for every possible scenario, making it impossible to handle real-life complexity. Let us now look at the next one, LLM call. A single LLM call means your app basically does one main thing. You give it an input, it processes it, and it gives you back an output. Think of chatbots that just take your message and respond, or apps that translate text. This was a huge leap from hard-coded rules, even though it is still pretty simple. And it is only in the second stage of autonomy. So here is a very simple diagram that I've prepared. So we have the user input right here. The user is inputting an input to the LLM, which is right in the middle, and then it gives out an output. So an example user input could be something like, you are an expert LinkedIn post writer. Write me a post on AI agents taking over content creation. So the user is giving just one prompt, one particular task to the LLM, and then the LLM is pretty good at doing that one particular thing. Okay, but there is one disadvantage as well. So as you can see right here, trying to get everything done in one shot often leads to confused or mixed up responses. Just like how one single person cannot be an expert at everything. So you can imagine that if I ask it to, write a Twitter post and a LinkedIn post and a blog post as well in one single prompt, it is not going to do it really well. If you're going to tell the LLM to do one particular thing, give it enough instructions and just give it one task, it is capable of doing it really well. But multiple things it cannot do really well. And this brings us to the next level of autonomy called chains. Think of chains as having multiple specialists instead of one generalist. Instead of asking one AI to do everything, we break it down into steps where each AI is really good at one thing. Imagine a customer service chatbot. The first AI reads your complaint and figures out exactly what product you're talking about. And the second AI finds the right solution from the company's help docs, and then the third AI turns that solution into a friendly response. Each step is simple, but together they create a much smarter system than a single LLM call. And this is where we first started seeing AI applications that could handle more complex tasks, not just by being smarter, but by breaking big problems into smaller, manageable pieces. But what are the disadvantages? The downside is that these fixed sequences are like a rigid assembly line. They always follow the same steps defined by the human. So let's look at an example of chains. So right here you have a user input. Okay, so the user input is going to be just a title for a particular post. So for example, the user is saying AI agents taking over content creation. That's it. The user wants this particular application to go off and create a LinkedIn post based on this particular topic, as well as a Twitter post based on this particular topic, as well as a blog post. Okay, so what you see right here, this is a chain for LinkedIn. This is a chain for Twitter. This is a chain for blog post. So basically we are having these parallel chains, and just by initiating this particular node, all these chains start executing parallelly at the same time. All right. And what are the upsides of this? What are the advantages of using this particular chain? It is not a single LLM call. These are three different LLM calls, right? So these are three different specialists doing, one specialist is doing LinkedIn, the second one is doing Twitter, the third one is doing blog post. So the advantage of using chains is that we have three specialists instead of one generalist. But what are the downsides? What did we see right here? The downside is that these fixed sequences are like a rigid assembly line, right? They always follow the same steps defined by the human. So basically what I'm trying to say here is that the level of autonomy is very less. right? The level of autonomy is very less. It is not making any intelligent decisions or anything right here. Okay, so let's now look at the next level of autonomy in LLM applications, and we come to router. This is where it gets really interesting. Routers are like smart traffic cops for your AI. Instead of having a fixed path like in chains, the AI itself decides what steps to take next. Imagine a personal assistant bot. When you ask it something, it first figures out if you need help with scheduling, research, or calculations, and then routes your request to the right tool or chain for the job. Okay, so I know this looks a little bit complicated, but let's take it one step at a time. Okay, so the example user input is going to be write me a LinkedIn post on AI agents taking over content creation. Okay, so the user is actually being very specific about LinkedIn. All right, so let's see what happens. This is the user input, and then we have another LLM right here. Okay, so we have an actual LLM where we would have written the prompt. Okay, so basically look at this particular user input and then figure out which social media channel that the user is asking this topic to be written on. All right, so this router LLM, what is it going to do? It is just going to return, is it LinkedIn or is it Twitter or is it X, whatever, threads or whatever, right? So that keyword is being returned by this particular LLM node, and that is being returned to a simple input classifier. So what is this classifier? It could just be a simple Python function. It just takes in an input, a keyword. That keyword, depending on whether it is LinkedIn or Twitter or a blog post or whatever, depending on that particular keyword, it is then either directing the control flow to the first chain or the second chain or the third chain. Okay, so if based on this particular input, since the user is asking for LinkedIn, it is then going to direct the control flow to this LinkedIn chain. All right, so that is the only difference. Basically, in the previous chains, you saw that there is no real intelligence happening. So whatever we decide, it is just going to go. There is no real decision making happening there. If we basically chains are predefined, we define, okay, this is the direction that it needs to go into. But in a router, this router LLM, it is actually making a decision based on the user input. It is looking at, okay, LinkedIn is what we want. So it is directing the control flow to that particular chain. Okay, but there is another disadvantage with a router as well. So while it can choose different paths, it still cannot remember previous conversations or learn from mistakes. And it is exactly to fix this particular disadvantage that we have the next level, which is going to be called state machine, or in other words, agent. And this is exactly where LangGraph is going to come into the picture. Let's dive into it. So this is combining the previous level, router, but with loops. And then why do we call state machine as an agent? Basically, whenever the control flow is controlled by an LLM, it is then called an agent. Very simple. I just wanted to give you a reason why we are calling state machine as an agent. And this involves features like the ability to have human in loop, ask for approval before moving on, multi-agent systems, advanced memory management, going back in history and exploring better alternative paths, adaptive learning, meaning it gets better even if it makes mistakes. So it won't make the same mistake again, and many more. And this is where LangGraph comes into the picture. So let's actually look at what is possible with this particular type, which is the state machine. All right. So we have the user input right here. And then this user only has to deal with the head of content agent. Okay. So we're taking the same example, which is the user input is like, write me a LinkedIn post on this particular topic, write me a Twitter post, write me this thing, write me both a Twitter as well as a LinkedIn post, right? The user can basically say anything to the head of the head of content agent. So normally this is how it works in business, right? Basically you would have one high level subordinate that you will give all your instructions to, and that subordinate will have multiple subordinates under it, and then that will take care of it, right? And that is exactly what is happening here. The user is inputting this to the head of agent, and this head of agent looks at this particular prompt and decides, okay, does it need to talk to the LinkedIn script writer agent? Does it need to talk to the blog post writer agent? Does it need to talk to the social media publisher agent? Okay, so it looks at this thing. Okay, it sees the LinkedIn thing, it sees the topic as well. So now it instructs the LinkedIn scriptwriter agent to write this particular post. All right, and we can also add a human in loop here as well. Okay, so we have time travel abilities when it comes to state machine, basically LangGraph. So once the LinkedIn scriptwriter agent is done with writing the LinkedIn post, we can also have an approval step right here. So basically, an approval step is it sends the draft back to the head of agent, I mean the head of content agent, and then asks basically, okay, is this good? Do you want me to make any more corrections? So this head of agent, content agent, is going to send it back to the user because we want this to be the point of contact. We don't want to deal with these agents, right? So this head of content agent is going to come back to the user, say, okay, this is going to be the first draft. Do you want me to make any more suggestions? I mean, improvements, right? So if the user says, okay, make it shorter, make it more, punchier, add a better hook to the post or something like that, all of that feedback is going to be again sent back to the LinkedIn scriptwriter agent. This agent already has what it generated previously, and then it has the feedback as well. So it has the full context, right? So, and then once it is done, it again does it. So you can see that there is a sort of a loop happening, right? It can go back in time, and then it can sort of iteratively make a particular thing really good. All right, that is where state machine really shines, and this is exactly where LangGraph is used basically. So what would happen once the human actually approves a particular draft? Okay, so the control flow comes back to the head of content agent, and then it looks for all the other subordinates, and it looks at the social media publisher agent. So this agent actually can go ahead and post that particular LinkedIn post to LinkedIn. So it's coming right here. It already has tools. If you don't know what tools are, they're basically just functions, Python functions, right? They're special Python functions. And first tool could be having the Twitter endpoint to post a particular tweet, and the second tool could have the endpoint to post to LinkedIn, right? So this agent has these tools, and depending on what the instruction is coming from the head of content, it can use the LinkedIn tool and then post it as well. So you can actually imagine how disruptive this technology could be. The user just has to speak to this one agent, and the agent is going to speak to other agents under it, like a hierarchical structure, and then get a particular task done, right? All right, so let us move on. So this is a diagram that is present in the LangChain documentation as well, the levels of autonomy in LLM applications. And this is what we saw just now. So we have the code right here. We have to decide the output of each step. We have to decide which steps to take. We have to decide what steps are available to take. All right. So in the LLM call, the output is decided by the AI, but the rest of the two things we have to say. Right? The chains are also very similar, but in a router's case, it can actually make decisions on its own, right? It can actually, we still have to specify what are the available outputs. Like we still have to specify the Twitter chain and the LinkedIn chain and the blog post chain, but which chain it needs to go to it can be decided by the AI. So that is why we have the AI right here. But then we also saw that there was a drawback. We saw that we had no cycles. There was no way to come back and then refine a particular thing, right? So that is why it says no cycles right here. And the fifth one is what is called agent executed. The AI takes care of, it decides the output of the step. The AI decides which steps to take as well. All that we have to do is decide what steps are available to take. Okay, and also it can actually loop through and sort of refine it, and there are cycles available in state machine as well. And then we have the sixth one, which is completely autonomous agents. All these three columns, you can see that the AI is doing it, and we are not really there yet. There's a lot of startups out there that are already trying to build this. You can check out Baby AGI. I think AutoGPT is doing that as well. So you can actually check it out. But we are not really there yet. The technology is not really there yet. But there is one more thing that I want you to notice in this particular diagram. Here you can see that the first 4 points, we have something called human driven, whereas in 5 and 6, it says agent executed. So what actually is the difference between human driven? Why is this coming under agent executed? So let's actually dive deeper into it. So we'll see what is the difference between chain or a router versus an agent. So a very simple definition, a chain or a router is just one directional. Hence, it is not an agent. That's it. Very simple. Whereas in a state machine, we can actually go back in the chain, have cycles, and the flow is controlled by the LLM. Hence, it is called an agent. So in the previous few diagrams for router and chains, we saw that it starts from the left side and then it just keeps on going to the right side until the end node is reached, right? So there is no real intelligence happening, and that is why chains and router are not considered as agents. Okay, but when we talk about state machines, you can see that there is loops happening, there is time travel happening, there is human review happening, there is a refinement of a particular, the user can critique a particular post and then the post is again critiqued and generated again, and then it comes back, and then the loop can go on several times. So there is actual intelligence happening, very similar to how you would do things in a real world as well. Let's say if you have a content writer under you, the same thing happens. There are multiple iterations happening. The same thing for UI UX designers as well, right? So that is why the state machine side is going to be called agent driven, whereas chains and router is going to be sort of dumb, right? Even though there is an LLM involved, it is still considered to be dumb because the LLM is not actually deciding, the control flow. All right, so that is it for this section. In the next section, we will actually deep dive into what are AI agents. So I'll see you there. Quick pause. I wanted to let you know that I offer a premium version of this LangGraph course that takes your learning experience to the next level. While this free tutorial covers the essentials, the paid version includes structured learning path with comprehensive modules, hands-on assignments to reinforce your skills, quizzes that you can test yourself on, detailed notes and slides for every single module, and finally, regular updates whenever LangGraph introduces new features or breaking changes. Unlike this YouTube video, which remains static, the premium course evolves with the technology. I've priced it to be accessible for everybody serious about mastering LangGraph. If you're enjoying this content and you want to deepen your expertise, check out the link in the description. Your support helps me create a lot more content like this. So let us get back to the tutorial. Alright, so in this section, let us understand AI agents. So you can think of agents as the problem solvers of the AI world. Agents are capable of thinking on their own. So in other words, it's AI that can make autonomous decisions. In the case of chains and routers, they follow our specific instruction, but with agents, they actually take it a step further. They can decide for themselves what steps to take on their own. But what are tools then? Tools are specific functions that agents can use to complete tasks. Just like a chef's kitchen tool, knife for cutting, oven for baking, blender for mixing, tools are the special abilities we give to AI, like giving a calculator tool or a search engine tool or a calendar tool. So how can we actually create an agent? So let's actually look at a very popular pattern that we use to create AI agents. And the pattern is called React agent pattern. Okay, so this is one of the best known patterns in AI today to build agents. It stands for reasoning plus acting. This is basically a concept that mimics how human beings think. So let us actually look at what this pattern is all about. So you can see here that we first have a think, and then an action, and then an action input, and then we have something else and we have observe. Okay, so what is this all about? Let's get some clarity on what is this React pattern, because this is very, very important to understanding a lot of things. Okay, so it basically React pattern is sort of mimicking how human beings think. Okay, so for example, if we look at a particular problem, first we think about the problem. Okay, so how do we solve this? Okay, what exactly is the problem? Okay, so we identify this is the problem, and then we identify what is the action that we have to do to solve that particular problem, right? So first thinking happens, and that is exactly why we have think right here. And then we have to take action to solve that particular thing, right? So that is why we have action. So what then happens? We take some action and then we observe the result of that particular thing. Okay, is it solving it? Is it giving some other answer? We actually do that observation, right? So that is why we have the observe right here. So we basically, humans, we observe the result of it and then we tweak it. If we get the answer, that's it. It's over. The cycle is over. But if we don't get the answer, we again, think, okay, what happened, right? So that is why we have think, action, observation in loop until we get the final answer. So let's actually take it step by step. So first we have think. The LLM first thinks about the user's prompt or the problem. Okay. So next thing is action. Okay. LLM decides if it can answer by itself or if it should use a particular tool. Okay. And then if there is a tool available to that particular agent to solve that particular problem, basically you can imagine it as a Python function, right? Any function requires some arguments, right? Some inputs. So that is going to be the action input. The LLM provides the input arguments for that particular tool. Okay. Now the LLM is just going to decide, okay, this is a proper argument that can be passed into that particular tool. So now the control flow comes back to LangChain, to our system. Okay. So here LangChain executes the tool and then returns the output back to the LLM. Okay. So it's basically like LLM is thinking it is executing the tool, but actually it is just suggesting the input. The control flow is coming back to our system. Our system function is executing that particular tool with the arguments that the LLM suggested. And then the output of that function execution is again sent back to the LLM. So the LLM has complete context of what happened before as well. All the think, action, observation, everything, all the context is available to the LLM. So it is actually looking at the output of this tool, right? So that is what this observe is. LLM observes the output of the tool. So if the output is like, it's enough, okay, I have actually found out the answer to the particular problem. If it has found it out, then it is going to end it right here. If there is some other additional information, right? If this is a complex problem, it is a multi-step problem. In that case, there's going to be another cycle happening. So this cycle is going to keep on repeating. Okay. So that is in a nutshell what React pattern is all about. So here is another diagram that I've prepared, basically to help you visualize, in a very simple way, what makes an agent, right? So whenever there is an LLM, basically the reasoning ability of an LLM, which is the brains, this is the brain, right? Whenever you equip a brain with some tools right here, right? If you equip the brain with the ability to, make API calls or make a Google search or run a Python function, combining both of it together gives rise to an agent. Okay, so that is how you can think about it in a very simple way. So enough theory. I know it's been a little dense. So in the next few sections, we'll actually be coding it out and, so you'll be able to better understand how things work. All right. So first off, what we'll do is we'll build a very, very basic React agent using LangChain. And then we will then look at what are the drawbacks of doing it that way. And then we will then, sort of segue into what does LangGraph do and how does it come into the picture? What is the problem that it solves? All right, so I'll see you there. Hello guys, welcome to the section. In this section, we are going to be learning how to build a React agent using LangChain from scratch. And this is particularly important because this will form the foundation for the rest of the course. Because later on, we'll be building the same thing using LangGraph and you'll be able to see the differences very easily. So let us go ahead and set up the development environment. So the first thing that I'm going to do is I'm just going to create a folder called LangGraph, let's say, and I'm going to open it in my Visual Studio Code. Okay, let's make sure that it is all zoomed in properly. All right. Okay, so to start off with, I'm going to create a virtual environment. If you're used to doing it with Poetry, you can do it, but I like to do it with a very simple virtual environment. So I'm just going to say Python 3-m basically stands for module. So we are using a particular virtual environment module inside of Python. So we can say venv and we can give the name of the folder that will be getting created here as well. These are prerequisites. A virtual environment is basically something where you can have all of your packages contained and you don't want to have it available globally, right? Okay, so now that the virtual environment is created right here, we have to go ahead and activate this virtual environment next. So basically we have to go inside of this bin and then activate this particular file. So I'm just going to say source venv bin and then activate. Perfect. So now you can see that in the terminal, you can see that we have this venv right here. So the next thing that I'm going to do is I'm going to create a folder called 1_introduction. So let's create a file inside of this, and this could be a simple React basic, React agent basic. Okay. So let's talk about the dependencies that are required to run a React agent. So obviously the first one would be installing the LangChain classes, right? So I'm just going to say pip install LangChain. And the second thing, since we're building a React agent, basically if you remember what agents are, they're basically the reasoning ability of an LLM plus tools, right? So we might also have to install LangChain community, because community, in the community package, there are pre-built tools that we can easily use. So we'll be using one of that. And in this particular section, we'll also be building our own custom tool as well. So you're able to see the full extent of what is possible. So let's actually go ahead and install LangChain underscore community. And the next thing that I want to install is a chat model, and more specifically, Google's chat model. If you do not know what chat models are, they are classes that LangChain provides out of the box, which lets you, interface or rather communicate with LLMs very easily. So I'm going to be using the Google's chat model because it is free, and I want to make this particular course accessible to as many people as possible. So you can just come to Google if you want to know what is exactly the package that you want to install. You can just say LangChain and Google chat model, and that is going to give you the exact document right here. If you want to switch to OpenAI for some reason, you can just say OpenAI right here, and this is going to give you another chat model. But right now we are interested in the Google generative AI chat model. So let's click on that, and you can see that this is the package that we want to install. So I'm going to add this here as well. And let me think, what else do we need? So we might also, for this particular chat model, we might also have to have environment variables, right? And then we have to make that environment variables available in our Python file. And for that, we might need the Python dash.env. All right. So since there's quite a lot of packages, it might take a while. All right, you can see that everything is installed right now. Great. So let's actually go ahead and start importing our first chat model. So I can just say from LangChain Google Gen AI import chat Google generative AI. Okay. And I just want to test if everything is working fine. So I just want to make a simple LLM call, something very silly, and make sure that everything is working fine. So I can just say LLM, and I can just initialize this particular class. So we have the model right here, and I can say invoke on it. If you do not know what we're doing right now, I've made a separate, again guys, I've made a separate LangChain crash course where I'm going in depth on chat models, but we're not going to be deep diving into that. So we have the model right here, and we are going to be invoking on it, and we can just say something like, give me a fact about cats. I don't know, right? Something very simple. So we are going to be getting the result right here. We can just go ahead and print it. And before I run it, you can imagine that it's not going to work because we haven't really provided any API key, right? So let's actually go ahead and create a .env file right here. And I'm not really sure, what property to put here. So I'm just going to go back to the documentation. Let's click on this. And you can see that this is the key that the class requires. So I'm just going to put this here. And as for the key itself, I'm going to go to aistudio.google.com and basically just log in, and you can see that we have the get API key right here. And I've already created a couple of these things. I'm just going to create another one. So I'm going to choose this particular project, create API key. All right, so the key has been generated. I'm going to copy it, put it right here. And now the second step is to actually have this environment variable be available inside of this particular file, right? We need to load the environment variables. And for that, we already installed a package. So I'm going to say .env, and then I'm going to import the load.env. So I have to call this particular method right here. And now basically everything that we have inside of here is going to be available in this file. All right, so now everything should work fine. So let me actually go ahead and run this file. Okay, so the reason why this is not working is because we have to provide a model right here. Okay, so I'm going to say Gemini dash 1.5 Pro. Okay, so this is the model that I want to use. All right, so let's go ahead and run this again. Perfect. You can see that it returns the content, which is cats can jump up to 6 times their height. All right, great. So now that we know that everything is working fine, now I want to go ahead and give a slightly more complicated prompt that the LLM itself would not be able to answer. So for example, we know that LLM is just the brains, right? It does not have any capability to access real world information. Like it cannot go and make a Google search. It cannot actually, hit APIs or anything like that, right? So I want to force the LLM to answer something that it cannot answer by itself. So, I'm going to think something funny. I'm going to say, uh, give me a tweet about today's weather in Bangalore. You can imagine that the LLM couldn't possibly give an accurate answer because it cannot access today's information, because it cannot access, the Google search API or anything like that, right? So let's actually go ahead and let's see what happens. All right. So you can see that it says Bangalore weather today, pleasant with a mix of sun and clouds. Expect a high. You can already see that it has placeholders right here, right? And a low of might feel a bit humid. You can see that this is not really accurate. The what is essentially happening is the LLM is sort of hallucinating an answer, an accurate answer. It is thinking that it is giving an accurate answer, but it is actually not. Okay, so this is exactly why we need to provide tools to the LLM so that it can actually use those tools and then call those particular functions and get accurate answers. So let us see how we can actually go ahead and create an agent. So I'm going to comment both of these lines out, and I'm going to use a method that LangChain provides out of the box, which is called initialize agent. So I'm just going to say langchain.agents. I'm going to use the agents module, and from that I'm going to use the initialize agent method. And this is a very convenient method that LangChain provides that lets you create an agent very quickly. So I'm going to say agent, and then I'm going to use this initialize agent, and this takes in a couple of properties. So the first one is it takes in the list of tools. We don't really have any tools right now, but we will build it later on. And secondly, we have to provide in the LLM here as well. So we can say LLM equals LLM. And the next thing that I'm going to provide is the agent type. So you can see that if I were to hover over this, you can see that we have to provide the agent type here. Okay, so I'm going to provide the zero shot React description. So I know that we haven't actually looked at the exact prompt, the React prompt yet, but we will look at it in a minute. But we already know that, it follows the thought action observation loop, right? So we will look at the actual prompt later on. It is baked inside of this particular method. Okay, so if you're wondering also what is this zero shot, it basically means that you're prompting the agent is doing something without any prior knowledge. You're not actually giving it examples or anything. It is doing it based on its own reasoning ability from scratch without any prior knowledge that we are giving it. All right. And finally, I'm also going to provide verbose equals true. So that, every time something is happening inside of the agent, we'll be able to see exactly what it is thinking, what it is observing, everything in the console right here. All right, cool. Now let's actually go ahead and invoke the agent. And now we can provide in our prompt right here. So I'm going to copy the same prompt that we put in earlier, and let's see what happens. We don't really have to return a particular result and then print it out because the verbose is true already. Okay, so let's actually go ahead and run this file. Let's clear the terminal and run this file. Okay, so it says that got no tools for zero shot agent. At least one tool must be provided. Okay, so if you get this error, just make sure that there should be at least one tool provided in this particular list right here. So right now you must think about what is that tool or tools that we have to provide to this React agent in order for it to use it and then solve this particular problem of giving a tweet about today's weather in Bangalore. So you can imagine that we need the Google search tool, right? So for this, there is a pre-built tool. We are going to be using a pre-built tool first, and then we'll also see a case where we can write it by ourselves as well. So I'm just going to go ahead and say LangChain community.tools And from this tools, I am going to use the Tavili search tool. So if you're wondering what this Tabili search is, it is basically a tool that is specifically written for what we're building, which is the LLM applications. And under the hood, it basically makes a Google search. Okay, so I'm going to go ahead and say search tool. Okay, let's say search tool, and let's go ahead and initialize this particular class. And also regarding the arguments that we have to send inside of this class, you can see that we already have plenty right here. We can leave most of it as default, but the one thing that I want to change is the search depth right here. You can see that the search depth is set to advanced. We don't really want advanced for this case. Advanced basically means that it is going to collect a lot more information, a lot more data from the search results. But the query that we have right here is going to be a very simple query. So we don't really need that much information. So I'm going to set it to the search depth. I'm going to set it to basic. All right. Now I can say tools right here. I can basically just move this outside and I can provide this down here. All right. So let's actually give this a whirl again. Let's see what happens. Okay, so you can see that it says the Tabili API key is not provided, because you can imagine that making a Google search is also something that costs somebody else money. So I mean, but Tabili it provides a free tier as well. So I'm just going to go ahead and say Tabili API key. Let's go in here and let's create an API key quickly. So if you haven't logged in, quickly go ahead and log in. All right, you can see that I've already created one thing. Let's create another one right here. So let's call it LangGraph Crash Course. So you can see that this is also free. It is rate limited to 100 requests per minute. So let's go ahead and create it. So I'm just going to copy this key, come down to the environment. And what is the name that we have to provide? You can see that it requires the Tabili API key. So let's put it before this. Let's save the file. And also before I run it, let's make it a funny tweet. All right, so let's go ahead and run this file. Let's see what happens. All right, you can see that it is entering the new agent executor chain. This is a class that lives inside of this particular initialize agent class. All right, so let's see what happens. Remember what would happen first? It would think about the question and then action and then observation. Think, action, observation. All right, you can see that everything is done right now. Let's actually go through the steps that the LLM took in order to arrive at this final answer right here. So this is going to be very interesting. Let's take it one step at a time. All right. So you remember that the React pattern is all about think, observation. Think, action, observation. Think, action, observation. Right. So that is exactly what is happening right here as well. So initially we have the question. This is the question that I gave it. This is the prompt that I gave it. Give me a funny tweet about today's weather in Bangalore. Now the LLM is thinking, what do I have to do first in order to solve this particular problem? So it is saying, I need to find out what the weather is like in Bangalore today. Then I can try to write a funny tweet about it. Okay, so this is the first problem that it identifies. Also, the next thing is taking action, right? So it is actually looking at all the tools that are available to it. If you are curious how the LLM has access to, what are the tools that we provided here? So this initialize agent method is doing a lot of magic under the hood. It is providing the description of this particular tool as well as the, basically the contents of that particular function to the LLM. Okay, so that is why the LLM is able to make a guess that this is the tool that I want to use. Okay, so it is saying I want to take action on this Tabili search results JSON tool right here. So right after it identifies that, this is the tool that I want to use, it is suggesting an input to that particular tool. So basically tools are like functions and functions require inputs, right? So it is actually suggesting this search term right here, weather in Bangalore today. So as soon as the LLM suggests this particular thing, and as soon as this observation, basically it's streaming, right? The LLM is streaming information. As soon as this information keyword is encountered by this particular tool, this initialize agent method, the control flow is stopped. and the control flow basically comes back to our LangChain environment. This is very, very important. Okay, so up until this point is where the LLM is in control. So right after this observation keyword is hit, this initialize agent is going to sever the connection with the LLM. Okay, and it is going to come back, and at the same time this initialize agent also has access to, okay, this is a tool that the LLM suggested me to execute, this is the input. So this particular tool is going to call this particular stabili search results tool. Okay, I really hope that you understood this particular part. This is very important. If you don't understand it, you can rewatch it. Okay, so our LangChain, it is going to execute this tool with the input that the LLM suggested, and this is going to be the output of the tool. And now as soon as the output of the tool is received by the LangChain, it is going to send the result again to the LLM. Okay, so the LLM is thinking that, okay, this is the observation, this is the output of the tool. It is basically looking at the entire this thing. So you can see that it is using the weather API, the tool, basically this is the output of the tool, right? So it's got a lot of information. It's got a lot of information about today's weather in Bangalore. And then the LLM is basically looking at all of that information, and then it's thinking to itself, it seems the weather in Bangalore is sunny and warm around 27 degrees Celsius. That's good information for a tweet. Okay, so it now has the answer to the problem. It used a tool, it function called and got the output. It is real world information, and now it has that information. So the final thought is going to be, I can now write a funny tweet. Okay, so right after the thought, action, observation is done, it is again thinking. It is thinking to itself, okay, now I have every information that I need. So the final answer is going to be, Bangalore weather is so perfect today. I almost forgot I have responsibilities, almost. Bangalore weather, sunny side up. So this tweet is actually very accurate and is grounded in reality. So this is a very simple example of an agent using tools and using the brain power of an LLM to achieve a particular output. So now you might have a small question. How exactly is this thought action observation is happening? So to do that, that is basically just a prompting technique. React prompting technique is just a prompting technique. Let's actually take a look at what it is made of. So to do that, I'm just going to say React hub. Okay, so just go to this particular URL. This is the particular prompt that the initialize agent method is using inside under the hood. Okay, so this is the prompt. Answer the following questions as best you can. You have access to the following tools. So the list of all the tools are provided to the agent in a different format that it can understand. So we are also instructing the LLM, use the following format. Question, the input question you must answer. The thought, you should always think about what to do. All of this we've already seen, right? Action, the action to take should be one of the tool names. And that is exactly what we saw in the terminal as well. And then action input, the input to the action, right? The input to the tool. And then finally, our observation, observing the result of the action. And then this thing goes on and on and on n times until all of the problems are solved in order to give the final answer. Okay, so finally, we are saying thought, I now know the final answer. And then finally, we have the final answer to the original input question. So the actual user question is provided right here. And this agent scratchpad is very important. So I told you in the past few sections where, the LLM has complete context about everything that happened before. Thought, action, observation, thought, action, observation. All of that history is maintained by that initialize agent method that I told you about. And every time there is a new LLM call being made for the next iteration, all of that is provided in this particular placeholder. The context, the history context is provided right here. I hope that makes sense. If it does not make sense, rewatch it. Try, reading some different blogs, attack it with different directions, and I promise that it will make sense. So now that we have a React agent set up right now, I want to push it a little bit further. I want to challenge the agent, and I want it to be able to use a few more tools in order to solve a particular problem. So right now we know that we've provided it a Google search tool. So I want to think of a problem that would make it ask for another tool. Okay, so let's say a couple of days ago, I noticed that SpaceX launched a rocket. Okay, so I'm going to, say a tweet like, let's say, when was SpaceX's last launch and how many days ago was that from this instant. Okay, so basically what I'm trying to do here is that, just knowing, how many days ago or when the SpaceX launch was, that is not enough. The agent also needs context about what is the current time of my particular system right here. I'm currently in India, right? If somebody else were to, run the agent, it's going to show a different time. So our agent not just needs the Google search facilities, but at the same time, it also requires the current system time, which we have not provided as a tool just yet. Okay, so we will be providing that later on. But for now, I just want to run it and let's see what we actually get. So I'm going to run this. Let's clear this out. Let's see what happens. So again, you can see that entering new executor, agent executor chain. Okay, so the question, when was SpaceX's last launch? This is what I provided. And you can see that it is thinking. I need to find the date of the most recent. Okay, let's actually scroll up. It is going to think for a while, but let's actually make sure that, we understand what is happening right here. So it is thinking to itself, I need to find the date of the most recent SpaceX launch and then calculate the difference between that date and today. I can use the Tabili search results tool to find this information. Okay, so this much, it is first figuring out first part of the problem, which is when did the SpaceX's launch happen. So it is actually providing the input to the tool, which is SpaceX most recent launch date. And this is going to be the result of the tool. It is again being sent back to the LLM and then fine, let's see what happens next. So it is thinking to itself, the search results indicate the most recent launch was a Starlink mission on January 1, I think it's 18th, 2025. And now I need to calculate how many days ago was that. Okay, all right. So you can see that this is the second problem that it needs to solve. And now it is taking an action, calculate days since, right? So the action input is going to be this thing. You can see that this is not even a valid tool, right? We haven't actually provided a tool like this. It is actually starting to hallucinate a tool, sort of trying to fit its own flow, right? But it's not going to work. It is actually saying the observation, calculate day since is not a valid tool. Try one of these particular tools. And it's saying that I can't calculate the days since the date using the available tools. I'll try searching for the number of days between this and this. I'll need today's date first. And then it is doing another, it's actually trying to figure it out using the one tool that it has, guys. This is amazing. So you can see what is today's date, right? And then it is making another API call. Today's date is February 7th or February 8th, depending on the source and the time zone, right? Right now it's actually neither, right? Right now it's neither. Currently it's 9th where I am right now, but it is not accurate because we are not really providing the current system time. So you can see that there's another observation and then, it's not working. This is an endless infinite loop problem, right? If we don't provide the right tools, there is an infinite loop happening and we get problems like this, which is not going to work. Okay, so which is why this actually brings us to another problem, which we'll look at later. This is one of the issues that we can run into when we try to work with React agents if we do not provide the right tools. So let's deal with that later. But for now, I'm going to provide a current system time tool so that the agent can actually make use of it, get my current system time using a Python library, date time library, and that should, it should be able to solve it very easily. So to do that, I'm going to paste a tool that I've just written. Okay. So this uses the date time module. I'm just going to quickly import the date time module right here. Okay, so let's walk through what is exactly this particular function. Okay, so this function basically just returns the current date and time in this particular specified format. Okay, so this just makes use of the date time module and then it formats it based on this particular formatting right here. So if the LLM in the future needs only the time or the minutes or the years or something, it can actually modify this particular input argument. But for now, we're just having a default argument right here, which we're providing, and this is just going to return the current system time. So now let's actually make this tool available to the agent. So to do that, we can just put it in this particular array, and that is it. But if you run it, it's not going to work because there is one more thing that we have to do, which is we have to explicitly let LangChain know that this function is a tool. And to do that, we can just go right here. We can just use this tool, this thing, and then we can use this particular notation. And this is going to make it apparent to LangChain that this is going to be a tool. So accordingly, it is going to format it and send it to LLM, right? All right. So now it should, so now to solve this particular problem, the agent has all the tools required. So let's actually give it a whirl again, and we should be able to get the final answer. Let's try it. And also guys, you can see that it says LangGraph. It's already suggesting that, this is deprecated, use LangGraph, right? Because that is the direction that we are also going in this particular course. But for now, let's actually learn how React agents work first. Entering new agent executor chain. Let's wait for a while. All right. So the question, this is my question. Thought I need to, okay, let's scroll up. So thought I need to find the date of this thing. This we've already seen the last time. It's searching this thing. It's sending this particular keyword to the search tool. The search tool is, calling, and it's outputting this particular result. Coming down, it is again thinking, it seems the last confirmed launch is January 15th. I need to get today's date to calculate the difference, right? So it is saying this, and now it is properly going and looking at the tool that we've provided, which is the get system time tool. It is also providing the input that the LLM wants the tool to execute with. Okay, so instead of this hours, minutes, and seconds, it is only providing years, months, and date. Right? It is actually making an intelligent decision right here. And again, the control flow comes back to LangChain, and then this particular tool is executed by LangChain, and then this is the observation, which is again sent to the LLM, and then thought. Today is February 9, 2025. The last launch was around January 15th. That's roughly 25 days ago. So the last SpaceX launch was around January 15th, which is approximately 25 days ago. So this is an accurate answer that is grounded in reality, and that the agent is actually making use of real world APIs, real world functions, real system time in order to calculate this thing. And that is the power of React agents. But a couple of minutes ago, we saw that we ran into the infinite, iteration problem, right? Because if we do not pass on the right tools, then, it can actually misbehave. So that is one of the disadvantages, but there's also a few other disadvantages. So I hope that this was clear. In the next section, we will actually look at what are the disadvantages when it comes to using React agents, and how does LangGraph actually solve those problems. So I'll see you there. Hello guys. So in the previous section, we went ahead and built a React agent using LangChain. In this section, we'll actually go ahead and look at what are the drawbacks of using React agents using LangChain, and where does LangGraph actually come into the picture. So let's look at an advantage actually of React agents. So we saw that the React agents are flexible, right? Any state is possible right here. Okay, so what we mean by that is we start the execution, and if we have the first tool, it executes the first tool and comes to an end. If there is a tool 2, it executes a particular tool 2 to figure out the problem and comes to an end. And there is also situations where the tool 1 could be executed first and the tool 2 could be executed first. And it could also be the opposite. Okay, so in the previous section, we saw it executed two tools, right? First, it used the Tavili search tool to make a Google search and then figure out, when was the SpaceX launch was, and then it figured out the current time. It could have also done it the opposite way. It could have also figured out the current system time and then went ahead and did the Tavili search as well. So that is what we are seeing right here. Okay, so React agents are very, very, very flexible. But high flexibility can also mean less reliability. Okay, so this is an example that we saw as well, wherein the tool one keeps on getting called again and again and again, and it goes on till infinity. Thankfully, Google Gemini, it stopped it right there. But infinite loops are a pretty big problem with React agents. There could be a couple of reasons why this happens. We see that we did not define the tools correctly, the LLM is not capable enough, or the prompting doesn't define a clear end condition. Okay, now basically we have the chains on one hand, we have the React agent on the other hand. So this is what we saw just now. The React agent is very, very flexible, but it is less reliable because it is not really in our control completely. All right. And on the other hand, we have chains right here. We saw that chains are like a fixed assembly line, right? It is not really flexible, but it is more reliable, right? So we need something that has the best of both worlds. We need something that is going to be flexible, but at the same time reliable. And that is exactly where LangGraph comes into the picture. Okay, so it is going to be flexible as well as reliable. So this state machine that we see right here, this is where LangGraph comes into the picture. All right. So what is LangGraph? Let's look at the textbook definition of what is a LangGraph. It is a framework for building controllable, persistent agent workflows with built-in support for human interaction, streaming, and state management. It uses graph data structure to achieve this thing. So this is a very simple preview of how the graph data structure looks like and how we can actually build agents. So we have the start node right here, and we have the agent right here. There is an action that agent takes, and then it can continue this particular thing. And then once it has reached the end point, it comes to an end. Okay. So I don't want you to think too much about what this is, but just know for now that this is how the structure looks like. So let's look at some of the key features of LangGraph. So the first one is looping and branching abilities. We've already touched upon it in a few sections ago, but let's look at it again. It supports conditional statements and loop structures, allowing dynamic execution paths based on state. State persistence. Automatic saves and manages state, supporting pause and resume for long-running conversations. Human-machine interaction support. It allows for inserting human review during execution, supporting state editing and modification with flexible interaction control mechanisms. Let's look at the fourth one. Streaming processing. Supports streaming output and real-time feedback on execution status to enhance user experience. Seamless integration with LangChain. Reuses existing LangChain components, supports the LangChain expression language, and offers rich tool and model support. And now you might have a question, why do we use the graph data structure for building LangGraphs? Why not use some other easier data structure to handle it? So the answer is that you can see that a lot of the papers, a lot of the research papers that have been published to solve difficult problems, they all use the graph data structure because it is flexible, but at the same time it is controllable. It gives you a lot of flexibility, but at the same time we can actually have a lot of autonomy, a lot of autonomous decision making baked into those data structures. And that is it for this section. In the next section, we will see what are the core components of LangGraph. So I'll see you there. Hello guys, in this section, we will look at what are the core components of LangGraph. So you can see that the core components, there are 4 core components. We have nodes, edges, conditional edges, and state. So I'll give you a very simple example to understand these different components. And that example is the reflection agent pattern. This is something that we will be looking at sort of deep diving into the later part of the course. But for now, I'll give you a very small overview of what this is capable of. So whenever we talk about a reflection agent pattern, we're always going to have something that is going to generate something. And we're also always going to have something that is going to critique that particular thing. Basically, this is not good. This is not right. We have to make this better. So this is the criticizing component, and we have the generation component. So as a whole, what this is doing is one agent is going to generate a tweet. Okay, so this agent's only primary job is to generate a tweet, and anytime something else criticizes that particular tweet, it is going to make the tweet better. So this only focuses on generation, and this LLM's only job is to criticize a particular tweet. It is going to say, okay, To make this viral, you have to make this short, you have to make this punchier, you have to add a call to action. Okay, so that is what this does. So basically, whenever a graph is going to start, we are always going to have the start node right here, and then right after the start node is executed, the control flow is coming to the generation tweet LLM. Right after the tweet is generated, there is going to be two different options. Okay, so there's going to be two different options. It can either go to this particular criticize tweet LLM, or it can end the process right here. Okay, so it is, let's say it is going to come to this particular node. In that case, this LLM is going to look at the tweet that this LLM generated, and it is going to critique it, and that is why we have an arrow pointing right here. Okay, so this can loop through several times to make the tweet really good, to polish it, to iteratively make it better and better and better. And after a certain number of iterations that we specify as developers, it can actually, instead of going to this particular branch, it can end this particular process. And the reason why I wanted to rush through it is because we are just learning the core components of LangGraph right now. So let's look at what are the core components. So these things that you see right here, this start block, this generate tweet LLM block, this end block. So these are what is basically called nodes. Okay, so if I come back here, this nodes that you see right here, these are the nodes. Okay, and let's look at the second one, edges. So what are these edges? So you see these straight, these lines, these are dotted, these are not edges. These lines are the edges. Basically, whatever connects two nodes are what is called edges. All right, let's look at the third one, conditional edges. What does this mean? So I've actually made it very clear that this dotted line is what is going to be called the conditional edge, because right after the execution of this node, it can either go here or it can either go here based on a condition. All right, so that is why we have a conditional edge right here. And finally, we have state right here. So state, it should be pretty intuitive to understand state. Even in this particular simple example, you can sort of imagine that this LLM is generating something, and then this LLM, this red LLM is going to give a feedback, and then this green LLM is going to generate something for that again. So the entire context needs to be maintained, right? So that is why the state is also going to be a core component of LangGraph. So I hope that makes sense. In the next section, we are going to be deep diving into what this reflection agent pattern is, how to build this, what are the, why do we even have to build it, what are the real world applications, and we'll actually be building it from scratch using code as well. So I'll see you there. Hello guys, welcome to this section where we are going to be deep diving into reflection agents in LangGraph. This is particularly important because this is sort of like the entry point for you to start learning LangGraph, and how powerful certain agents can be. Okay, so in this section we are going to be starting to look at what is a reflection agent system, what are the three types of reflection agent systems. We'll do the setup and installations, and finally we will implement a reflection agent system using our code. So by the end of this particular section, the reflection agent, it could go on for a few more sections as well. But by the end of it, you should have a pretty good idea, how powerful this can be and where you can actually sort of apply this type of an agent, this reflection agent in your, workflows. So before we jump into all the nitty gritties of implementing it using code, etc., etc., before that, let's actually just understand the very English word called reflection. Okay, so just like how you're looking at your reflection in the mirror, reflection means looking at yourself or your actions, right? So that's what self-reflection is, right? So for example, after giving a presentation, you're thinking about how it went. After writing an email, you're reading it again just so it's clear, right? And also, after making a decision, considering if it was the right choice, right? So this is what reflection is in a nutshell, right? So it's basically like having a mirror in front of you and looking at, basically could have done something better, thinking to yourself about, what you've done in the past, right? So now now that we know what reflection is, let's dive into what is a reflection agent. So what is a reflection agent pattern? A reflection agent pattern is an AI system pattern that can look at its own outputs and think about them or make it better. Just like how we look at ourselves in a mirror and self-reflect, making ourselves better. A basic reflection agent system typically consists of a generator agent and a reflector agent. So here's a diagram that I've prepared about, this is a very simple application that we are going to be building, which is a very good example of a basic reflection agent pattern. So in the previous slide, we saw that every reflection agent pattern is going to have a generation agent and a reflector agent. So we are going to be using that dynamic to help me create the best tweet possible, the best viral tweet possible. Okay, so this is a very simple graph. So we have the start node right here, and then we have the tweet generation agent. Okay, so this is going to be the first agent, which is going to be the generation agent. And then as soon as the tweet generation agent is done generating a particular tweet based on my input, based on my topic that I'm providing it, what ends up happening is that this is a conditional edge, right? So it is coming to this tweet critiquing agent. Okay, so what this tweet critiquing agent's role or a responsibility is that it looks at a particular tweet. Okay, basically the prompt of the critiquing agent is something like this. So you are a critiquer of tweets, and you critique such that the tweet can be made viral, something like that. So basically just looks at a tweet, gives suggestions. Okay, this is too long, you have to make it short, you have to add a CTA, you have to add a punchy intro, a hook, right? So add these hashtags. So this agent just like critiques it. So as soon as generation is done, it critiques it, and the critique of that thing is going to be passed to the generation agent, and then the tweet generation agent makes it a little bit better and then sends it to the critique agent again, and then the loop continues on and on and on for a few times, like 4 or 5 or 6 times that we set it. But you can imagine that with every single iteration, the tweet gets better and better and better, and it comes close to a very viral tweet, right? You can actually think of an application or a product where you can actually add this as a feature, and your clients, your customers would love it, right? This is another example that LangChain website, the documentation provides, where it sort of explains what a reflection agent pattern is, right? So the first system that you see right here, this is not the reflection pattern. Okay, so system 2 is the reflection pattern. So let's look at what are the differences between the two. So system 1 is basically how you would normally use, ChatGPT or Claude, right? You just put in a prompt. Let's say, hey, agent, your responsibility is to make a viral tweet. Write me a tweet, and this is going to be the topic, right? So it's a very simple prompt. It's going to do it in one shot, right? So that's going to be system 1. It is going to be very fast. It is subconscious, meaning it's not really thinking like actively thinking about it. It's just passively, with its own reasoning ability, it is going to generate something, right? It is also automatic. It is everyday decisions. It's really good for everyday decisions, and error prone. It is a little bit error prone as well, because it's not really deeply thinking about something. I hope that makes sense. This is what is called system 1, right? But this is what we are interested in, which is the reflection agent pattern, where it is going to be a little slow. If you think about it, since we have two agents right here, one is generating, one is reflecting, and then they are sort of like, working together to make the tweet better, like in a loop, right? So in that case, you can imagine that it is going to be a little slow. It's not going to be as fast as a one-shot prompt. And you can also imagine that the system 2, which has two different agents, it's going to be a little bit more conscious as well, collectively together, right? And it is effortful, right? Complex decisions, right? There could be certain situations where the decisions have to be really precise and not just like, just subconscious, but rather it needs to be actively thought out, right? So in that case, if you want it to be reliable, you can go for this reflection agent pattern right here. So this is another simple reflection loop diagram that the documentation provides. So first, whatever it is we're first generating, you don't really have to think about tweet. You can think about pretty much anything out there, right? So it is generating something. This is going to be the initial response, and then another brain, another LLM or another agent is going to reflect on it. Reflecting as in like it's going to give some critiques, merits. Okay, this is what went right, this is what went wrong, right? So it is going to provide all of that, and again, it's going to the first brain, the generate brain, and that is going to incorporate all of these, critiques, and then it's going to, make the post better. It's going to revise the existing post better based on these things, and then this loop is going to go, repeat n times, which is put right here, and then after a certain, iteration loop is reached, it is then going to go to the user. So we'll also look at the types of reflection agents in LangGraph. So we have three types. We have the basic reflection agents, which we saw in the previous slides, wherein there is this reflector chain, the reflector agent and the generator agent working together, and that is the basic type. We also have the reflexion agents. That is something that builds on top of the basic reflection agents. We'll look at that after this section. And then we also have the language agent, tree search or LATs. So basically, I want us to first get really comfortable with this first basic reflection agents, so that learning the other types is going to be very simple for us. So let's actually go ahead and implement a basic reflection agent using LangGraph. So I'll see you in the next section. Hello guys, in this section we'll be going ahead and building a very basic reflection agent using LangGraph, and this is going to be the first section where we're actually going to be touching on LangGraph. So I'm pretty excited. We also have a condition right here, okay, should continue or not. So basically in this should continue node, we have like an iteration, only after 4 iterations you can go to end. So until that 4 iterations is reached, always go to the reflect node, and then the reflect node is going to give some critique. It's going to be passed on to the generate node, and then the generate node is going to generate something else, and then it's going to come back here. Now the should count is going to be 2. So you can imagine that it allows for, let's say, 4 more iteration cycles. So the first thing that I want to do is I want to build out the generation chain and the reflection chain alone. And once we've built both of those chains, then we will, in the next section, we will go ahead and create the graph and put it all together. So let us do that. We will go back to our Visual Studio Code. So I am in my VS Code. What I've basically done is I've created a folder right here called the basic reflection system, and then inside of which I've created a file called chains.py. So this is basically the file where I want to sort of put all of my the chains alone together. This is not the file where I want to create the graph. I'll export the chains into the graph and then I'll start using it. So right now we just want to create 2 chains. We need one chain for the reflector chain and then another chain for the generator chain, right? So in this file, I've imported 2 things, chat prompt template, messages placeholder. If you're familiar with LangChain, then you should probably know what these things mean. If you do not know, basically, chat prompt template is basically like you create a template and then dynamically you sort of input different values. So for example, you are a helpful AI bot, your name is this thing. So in the future, if you want to use this particular prompt, you can just pass in the name to be Bob and the user input to be what is your name. And then this is going to dynamically replace these placeholder values. Okay. So below this, I'm just going to copy paste the generation prompt. So this is going to have a simple system message. Okay. So basically what it says is that you are a Twitter techie influencer assistant tasked with writing excellent Twitter posts. Generate the best Twitter post possible for the user's request. If the user provides critique, respond with a revised version of your previous attempts. Okay, so you can imagine that the first system, the generation system's only job is to generate a particular tweet. And if at all the other system, the other agent provides a critique, it needs to respond with a revised version of your previous attempts. And that is exactly what we're specifying right here. And what is this message placeholder? Basically, in the future, we are not going, this alone is not going to be helpful, right? There needs to be a lot more messages like, this would generate something and then there would be a reflection, there would be a generation, there'd be a reflection. So you can imagine that there is going to be a good amount of, history getting generated, and whatever history is getting generated at that point, we will input all of this inside of this particular area. So that is what this placeholder is for. And we have the name for that as well, which is called messages. All right. So let's also go ahead and create the reflect prompt. So this is going to be the reflector prompt. So you can imagine that basically the reflection agent's only work is to look at a generated tweet and then make it better, right? Okay, critique it, right? So that is exactly the prompt that we provided here. So the system message is going to be, you are a viral Twitter influencer grading a tweet. Generate critique and recommendations for the user's tweet. Always provide detailed recommendations, including requests for length, virality, style, etc. Okay, so this reflection prompt's job is to make the tweet better by criticizing it. Like really, like this is bad. Okay, do it better. So Now let's go ahead and create chains out of these prompts. Okay, we have to create chains out of these prompts so that we can export it and use it inside of our graph later on. So to do that, I'm just going to use the same chat Google generative AI model, and then I'm going to use the LangChain expression language to actually go ahead and generate a chain. So I'm going to call it generation chain equals, and let me just put it right here. I'm going to pipe it with this LLM. That is it. Very simple. Okay, and then I'm going to do the same thing for the reflection prompt as well. So let's call this chain reflection prompt and then LLM, and that is it. Okay, so now we've got two different chains right here, and that is what we are going to be importing into our graph and then connecting it all together in the graph. So I'll see you in the next section. Hello guys, in this section we are going to be building our own very first graph, and we are going to be building the reflection agent using some of the chains that we built in the previous section. So you can see that I've already gone ahead and created a simple file called basic.py alongside with the chains.py that we created in the last section. And also you can see that I've imported a few things. Before you start importing it in your own code, just go ahead and make sure that you've installed this particular package, LangGraph. Okay, so this is going to be the command, very simple. Just do that and you should be able to import some of these things. All right. So let me walk you through what are the things that I've imported. So we have the from typing import list sequence. This you can think of it like a very simple type checking class, like very similar to TypeScript. Not really important for the actual execution of the graph, but it helps us make sure that there aren't any errors. And then secondly, we have the .env, which we know, it basically just like loads up all the environment variables. And then we have the messages classes, the base message and the human message. I think if you've worked with LangChain, you should be pretty comfortable with it already. And then this is what we are going to be doing a little bit new. So we are importing from LangGraph.graph. We are importing the end class and the message graph class. Okay, so this is pretty important. We will come to this in a minute. And then finally we have from chains, and we're importing these two chains that we have written in this particular file right here. Okay, very, very simple. So let us quickly take a detour and really understand what this message graph is all about so that we can confidently proceed forward with the rest of the code. So let us see what is a message graph. So it is a class that LangGraph provides that we can use to orchestrate the flow of messages between different nodes. So this graph that you see right here, this is going to be a message graph that we are going to be using. So the example use cases are simple routing decisions, simple chatbot conversation flow. And what we are doing is something that is very basic. So we are going to be going with the message graph. So if you just want to pass messages along between nodes, then go for message graph. Okay, so we will look at what this means in a few minutes. And there is another type of graph, which is a state graph. And if your app requires complex state management, then we can go for state graph. We'll look at more of this in the future. But for now, for this particular use case, we can actually use the message graph. Okay, so let's actually dive deeper into it. So to put it simply, message graph maintains a list of messages and decides the flow of those messages between nodes. So every node in message graph receives the full list of previous messages as input. Each node can append new messages to the list and return it. The updated message list is then passed to the next node. So basically each of these nodes receive as the input all the previous exchanges that happened, and then each of these nodes can actually receive the entire list and then append another output, a response, and then send it to the next node. And then the next node can do the same thing. It receives the entire input and then it can use that and generate a new response and then append it to the list and then pass it back to generate and then reflect and then generate. So that is a very simple workflow, and that is exactly why we are going for message graph. So let us actually now go ahead and start building our own graph. So to do that, I'm just going to come down here and then I'm going to invoke the message graph class. So I'm going to call it graph, message graph, and then I'm going to invoke it. Perfect. So we have the graph ready. Now there's a couple of things that we have to do. So the graph is currently empty, right? So I'm just going to first go ahead and create the generate node. and then I'm going to go ahead and create the reflect node. So once I have all the nodes ready, I'm going to add it to the graph, and then I'm going to connect those nodes together. Okay, so it's very much like drawing a diagram and then controlling the flow of the control flow between nodes. So first off, I'm just going to name the nodes properly. So we have the generate node and the reflect node. So to make it easy, make our lives easier, I like to usually go ahead and create a constant like this. So reflect and then generate, right? Generate. All right, perfect. So now let's go ahead and create the generate node, and that is nothing but a simple function. All right. So I'm just going to say generate node, and if you remember from the previous slides, we know that every node receives the entire state, right? And then we are invoking on that state using the chain that we've created in the previous section, and then we are appending that response to the history. Okay, so that is what we are going to be doing. So this is going to be the state. You can basically think of it as a list of messages that happened in the past. Okay, so this is going to be the list of messages, and then this we can actually make use of the generation chain, and then we can invoke on it. So basically whatever state has been generated or accrued, all of that we need it to sit right here. Okay, so we have the messages placeholder. So let's actually go ahead and say messages, and then we pass in the list of messages, and that is it. So what this is going to do is it is going to generate the tweet based on whatever is existing in the past. So later on, when we actually invoke this graph, we will provide the prompt, the main user prompt, and that is going to be what is appended, and it's going to be provided right here. Oh, and also don't forget to return this particular thing. So whatever is going to be the returned object of the LLM, it is just going to extract the content property alone, and then it is going to append that message to the existing state right here. Okay, I hope that makes sense. Let's now go ahead and create our next node in our system, which is going to be the reflect node. So I'm going to say reflect node state. So here we are going to be doing something very similar. So here we are going to be using the reflection chain, and then we are going to invoke the messages, and then finally the same state. Okay, perfect. So I hope that makes sense. There is also one more thing that I want to do. So we have the generate node. Obviously, the generation is being taken care of by the AI, and whatever is returned is considered to be the AI message. But usually in real life, the reflection is being done by a human, right? So we can actually trick the system into thinking that the message that is being returned is by a human, right? So we can also do that. So I'll tell you how. So we can actually call this to be the response, and let me just paste something here, return response. Okay, so we can also do something like this. So the previous version, that is perfectly fine as well. First AI is generating, the second AI is critiquing. The first AI is generating, the second AI is critiquing. That works perfectly fine. But for readability, for tracing using LangSmith, etc., sometimes it might make sense if the reflection is actually if we are tricking the system into thinking that the reflection is being done by a human. So in that case, we can actually return a list, and we can just pass in the content right here, and this content is going to be appended to the existing list of messages. Okay, so this is also a possibility. I'm just giving it to you. But if you don't want to complicate your system too much, we can just leave it as it is as well. Okay, all right. So we've already gone ahead and created both these nodes. Let's now go ahead and add these nodes to the graph. So to do that, it's very simple. I can just say graph, add node. And in this node, the first one is going to be the name of the node, and then the actual function, the generate node. And then secondly, we also have, let's also add the next node. So we can just say reflect, and then reflect node. All right, perfect. And also we can, specify the entry point. Okay, so there is always going to be an entry point. So in this graph, if you look at the entry point, it is going to be this generate. You might ask, okay, why is it not start, right? So the answer to that is start is something that is like, inherently sort of assumed to be the entry point. So it's not really considered, explicitly considered, it's more like implicitly considered. So let's actually use the generate node, which is going to be the first node where the entry is going to happen. So I'm going to say the entry point is going to be this particular generate. Okay, so let's come back to the diagram. Let's see what else is there. So we now need to create this particular should continue function. Okay, so this should continue function is basically keeping track of how many iterations have happened. And if, we can actually set, okay, after 4 iterations, we stop the cycle, go to the end, give the user the end output, which is the more refined tweet. So until then, just like, after the generate, come here, go send it to the reflect instead of the end. So it just does this 4 times and then it is going to go to the end, right? So let's actually go ahead and write this should continue function. So to do that, I can just say should continue, and this again is going to get the list of messages. And here I can say if the length of the state, if that were to exceed 4, okay, in that case, I want the graph to end, right? So I can just say end right here. And you can see that I've already imported this thing from the graph, right? It is a pre-built constant. And then if that is not the case, I can just return the reflect. Okay, I can say go to reflect. Okay, so far we've created the generate node, the reflect node, the should continue node, right? We've also specified that this generate node is going to be the entry point as well, but we haven't really done any sort of connecting yet. So the first connection that this is going to be the connection, right? So these edges are going to be the connection. So the first thing that I'm going to do is I'm going to say add conditional edge. Okay, so the conditional edge is going to be this thing right here. Okay, so right after this should continue, it can either go to the reflect or it can either go to the end, right? So this is going to be a conditional edge. This is not going to be a normal edge. So what you see right here is a normal edge. What you see right here is a normal edge, but this is going to be a conditional edge. So what I'm going to do is I'm going to say right after the generation is done, right after the generation is done, this should continue node is going to actually, branch off to 2 different things. Okay, so that is why we are putting this add conditional edge right here. Okay, I hope that makes sense. So far we've done this particular connection. The should continue should go to reflect or should continue to go to end. But if it were to go to reflect, then there is only one option, which is to go back to the generate, right? So let's actually connect an edge between the reflect and the generate. So to do that, I'm just going to add a very simple edge. So this is called add edge. Okay, this is not going to be the add conditional edge. So the first one is going to be reflect. So this is going to be the from node, and then we are going to have the to node. So you can imagine that this is very much like just drawing a diagram, right? So we've connected these 2 lines. Now the reflect is going back to the generate. So what else is left? All right, guys, looks like everything is done. So let's just go ahead and compile the graph. So I'm just going to give it a constant named app, and then I can just say graph.compile, and this should compile the graph. So before I actually, provide a topic for the tweet or provide an existing tweet and ask it to make it better, before I do that, I just make sure that, the graph is looking exactly how I expect it to, just to get ahead of any problems that may happen, right? So to do that, I'm just going to copy paste a few lines of code. So basically what this is doing is that, this is going to give you a mermaid diagram and an ASCII diagram. Basically it's like a very simple visualization of the graph. So right here, everything is like neat and tidy, but we just need to make sure that it is the same thing that is being replicated right here as well. And just one more thing, guys, if at all you get stuck anywhere, you've got 2 options. I'm putting this repository in the description below, so you can always go pull the code and then run it yourself, and that is sure to work. And if at all, despite that, you're getting some clarifications, I'm more than happy to answer questions in the comment section. So just go ahead and shoot your questions. So yeah, so as I said, this is going to give you the mermaid diagram, and this is going to give you the ASCII diagram as well. So let's go ahead and run it. And if you go ahead and run it, there is going to be one additional package that it might require you to install, and that is going to be this pip install grandalf. Okay, so just go ahead and install it, and you should be able to run it without any problems. So let's go ahead and run it, and let's see what happens. All right, so perfect. So this is going to be the this first one is going to be the mermaid diagram. So as you can see, we've got the start is going to the generate, right? The start is going to the generate, and here there's going to be a simple edge, whereas the reflect going to the generate is also going to be a simple edge right here, right? So these are the two simple edges, whereas this generate going to the reflect is going to be a conditional edge, and that is exactly why we have the dot in the middle of this particular arrow. The same thing for the generate going to the end as well. So it is looking pretty well. And also you can see that we've got this other diagram as well, where the start is going to the generate and the generate is going to the reflect and the end. So everything is looking fine. So now what I'm going to do is I'm going to provide it a tweet, right? I'm just going to, basically this is a system that really helps me churn out really viral tweets really quickly. And I just need to provide it a topic or some context, right? So what I'm going to do is, so we have the app right here, and what I'm going to do is I'm just going to say app.invoke, and inside of this I'm just going to pass in a human message. Okay, so basically whatever we pass in here, it is going to be added, rather appended to the existing list, the message history list that I told you about, right? So this is going to basically, let me just type it out and let me explain it on the way. Okay, so the content is going to be, I want there to be a tweet written on AI agents taking over content creation. So I'm just going to say AI agents taking over content creation, and I'm also going to, assign it to this response and then print it out as well. All right, so let's hope that everything works fine. So essentially, if I were to hit play, what would happen is that this human message is going to be, that the entry is going to be the generate node, right? So this state, which is going to be a list of messages, right now it is only going to have one message, right? Which is the human message that we are providing. And that is going to be put in the place of this variable message in the generation chain. So each of those chains would have their own individual system messages, but the history is going to be shared. It's going to be shared between both of those chains. Okay, so this is a confusion that a lot of people get. There is only going to be one message history. Okay, there's not going to be two message histories, just one message history. The system message is going to be separate for each of the chains, and both of those chains are going to share the increasingly getting message histories. I really hope that I'm not confusing it, but if at all you have any questions, ask me, or just go ahead and ask ChatGPT. So yeah, let's actually go ahead and run it. Let's make sure that everything is fine in the chat, the chains as well. Okay, so let's go ahead and run it. Okay, so the diagrams are getting generated. Okay, it's taking a while because you can imagine that, so it's actually here, guys. So you can see that, great. So you can see that the first human message that I've provided is right here. And then there's going to be a lot of other information like, okay, so the AI message is also here, right? So yeah, this is going to be the first creation of the generation chain, right? So we have the AI agents are revolutionizing content creation from automatic tedious tasks to generating creative text formats. They're empowering creators to focus on what matters most, right? And then, what matters most, telling compelling stories, and we've got several hashtags it has provided. So the generation chain has did its work, right? So I'm providing it a title, and the generation chain is doing its work properly. So now what would happen? The reflect chain is going to critique that tweet that the generation chain has generated. So let's see where that is happening. I know this is a little not really that readable, but don't worry, we are going to be deep diving into what is exactly happening in the next section, where we are going to be tracing everything using LangSmith. But for now, you can see that. Great. So this human message is right here. So if you remember, we tried to mimic a human message getting. Basically, the critiquing voice is going to be a human message, because that's how we're doing it, right? This makes it very readable for us. We can put it as an AI message. We can just leave it as it is as default. But because we put it as human message, this is going to be very readable for us. So here, this is going to be the critique, right? So your original tweet was concise, but lacked context and excitement. It presented a statement without engaging the audience or offering any further information. While brevity is good, it needs to be paired with impact. Okay, and it is also providing recommendations. So the length, the revised tweet is slightly longer, providing more context while remaining. You can see that it's providing a lot of different things, right? This is amazing. So if you actually you can just pause the screen and then give it a read, you would be able to see that human message is critiquing it, and then the AI message is again like making it better, and the human message is critiquing it. And let's see how many iterations would it go for. Okay, so right now we've just set it to 2 iterations, guys. So you can actually increase it to, let's say, 4, and let's see what happens. I'm just going to increase it to, let's increase it to 6. I want there to be 3 different iterations, back and forth, back and forth, back and forth. Okay, so if I were to do that, let's see what happens. Usually it's not going to be enough. There needs to be at least like a couple of iterations for the tweet to really become a viral tweet, right? So let's give it a bit, let's give it a while. Okay, so it looks like it gave an error. It is saying that the iterations, this thing has been exhausted. And usually this tends to happen when you're not really paying for the API. So usually, since we're not paying for Google Gemini, they basically rate limit us. So we can only make these many subsequent calls at this particular interval, like something like that. So that becomes kind of an issue sometimes. So what I'm going to do is I'm just going to quickly switch to OpenAI, because that is what I'm paying. So what I've basically gone ahead and done is that in the so basically what I'm going to do is I'm going to go to chains, and I'm going to use the LangChain OpenAI chat model. Okay, so now I want to communicate with the OpenAI chat model, and let's also go ahead and say chat OpenAI, and I'm just going to quickly come down here and then replace the model to GPT-4o. GPT-4o, all right, and let's save this. And I'm also going to provide the environment variable. Okay, so just go in here and then you can see that this is the environment variable that you need to provide. If you do not know how to pay for this thing, just go to platform.openai.com. I think go to the billing section, and then you'd be able to pay a minimum of $5, and that is going to give you access. You can also pay for Gemini, but yeah, this is what I've already paid it, so I'm just going to go ahead and do it with OpenAI. So, all right, so let's now try to run this file again now that I've changed it, and it should hopefully work fine. So I've said GPT-4o, which is correct. Perfect. All right. Now let's try to run this again. So this time there's going to be 3 different exchanges, right? So there's going to be 6. The length of the message list is going to be 6. So there's going to be 3 different iterations. So let's wait and see. Okay, perfect. So looks like we've received the entire thing. Okay, you can see that this is a pretty long message, right? Because there's quite a lot of data that is packed in here. So first off, there's a human message, and then this is going to be our initial message, and then there's going to be somewhere in here you should be able to find the AI message generated. So where is it? Oh, right here. Okay, so we have the AI message generated, and there should be another simulation of the human message that is going to critique it. So yeah, so you can see that there's a human message right here. Your tweet touches an intriguing and current topic, but it could benefit from more context and engagement tactics. So again, there's going to be another AI message. Okay, so I'm not really able to find it here, but this will all make sense, in the next section, where we are actually going to be tracing the entire thing using LangSmith. All right, guys. So in this section, we will actually trace the reflection agent system that we built, just so we can understand exactly what is happening where, so that we'll understand how both of these systems are working together to deliver our final refined viral tweet. All right. So to do that, I'm just going to go ahead to this particular website, smith.langchain.com. If you don't have an account already, just go ahead and create an account. And I'm going to come to this tracing projects right here. I'm going to click on this project, and yeah, I'm going to choose with LangChain. And there's a couple of things that we have to do. So we have to generate the API key, right? So I'm just going to copy this API key, and you can see that it's already being reflected right here. So instead of copying this, I can just copy this entire thing right here, right? I can just copy this entire thing and then come back to my environment file, and I can put it down here. So I don't really have to provide the open AI key because I've already provided it. But yeah, the rest of it should be there. All right, perfect. So now that is pretty much it, guys. If you do not know what LangSmith is, LangChain has very strong support for LangSmith because they all work under the same umbrella, right? So you just need to have the environment variables available in your file, and that is it. So what I mean to say is that, so inside of this, so we have all the graphs and we have the message graph and we have the different nodes and everything. So within all of these classes, it will have support for LangSmith. So once a particular operation is done, if the LangSmith environment variables, everything is like perfect, it will make and stream it to LangSmith so that it will capture it on its side. Okay, so we can actually trace it very easily. All right. So now that we have put all of this in the environment variable, let's now try to run it again. And once we run it again, we should be able to see another project right here. Okay. So let's try it. Let's give it a few seconds. So as it is actually going through each and every single step, the first iteration, the second iteration, the third iteration, after every single operation, there is going to be a call that is being made to LangSmith, and it is actually recording everything right now. So let's just give it a second, and once it finishes, we can actually go to LangSmith. So you can see that everything is available right here. Now, if we come back to LangSmith and refresh this, you should be able to see another project. Perfect. So you can see that we have the new one that is generated today, right? This is 13th, which is today. Let's go in here. All right. So here we have runs, threads, monitor setup. We are only interested in runs because a run is basically running an entire application from start to finish. So if we were to click on this particular run, we'd be able to see traces. Traces is different from runs. Traces is like this particular small component in the system, did this particular thing, right? So it gives you a lot more descriptive, information about what exactly happened. So at the very top, you can see that this entire thing took 46 seconds. This is going to be the complete compilation of what happened. But if you're interested, we can also go through each of these different things just to see what component did what at what point, right? So right now we have the generation agent and the reflect agent. So we can actually see what the generate agent, or we can't really call it as an agent, but what did the generate workflow did first, and then what is the reflect workflow did second. So we can actually see all of that. So this is going to be, as I said, a high level overview of what happened. I said this thing first, and then the AI, which is the generate agent, generated this particular thing. And then this is going to be the human message, but actually it is not the human message, if you remember, right? So this is going to be another AI generated this thing, which is going to critique the first generated tweet. It's saying your tweet touches on an intriguing and a highly relevant topic. However, to maximize its impact and virality, consider doing this: expand with context, engage with a question, use emojis, right? Hashtags, use better hashtags, create a thread, add media, virality, and all of that. Remember, the goal is to be thought provoking and informative. So this reflect agent is going to generate this thing, and then it is going to, now the control is going to go back to the generation chain. So the generation chain is going to generate a completely new revised tweet based on all of the feedbacks that it received. And then once it is done, again, the critiquing agent is going to look at that tweet, and it's going to suggest a lot more, to how to make it better. And taking into account all of that, again, the generation agent is going to make it even more better. And then this thing goes on for a total of six different exchanges, right? So that is what we've done. And finally we have a very viral tweet that is packed with a lot of, you can see there are emojis and there are hashtags, and it's really a pretty well thought out tweet, right? It's not like a one shot tweet, but rather there's going to be a lot of thinking and a lot of refining, and then finally, it gives you this final tweet. And that is exactly how in the real world it works as well, right? There's going to be multiple iterations. So that's what we have right here, guys. So initially there is going to be the generation node. I'm just going to provide this. The generation node is going to generate the first tweet, and then what ends up happening is that there's going to be reflect node, and that is going to look at the generated tweet, and then it's going to critique it, And then finally, again, the generate node is going to be there, and it's going to, again, it has the context about every single thing, right? It has context about every single thing. And then finally, it gives you the output of that, and the same thing happens again and again and again. And finally, we have the final tweet right here. Okay, so I hope that you're starting to understand how reflection agents work and how powerful they are, because they can actually think deeply through a particular thing, and then they can like reflect and generate and reflect and generate. And what I've done is basically a very simple example, which is to generate a tweet, but you can imagine that we can do it for pretty much anything out there, even for complex tasks. And if at all you have any questions, just go ahead and ask it to me in the comments, and I'll be more than happy to help you out. So in the next section, we are going to be looking at the next type of reflection agent, which is called Reflexion agent. And that I believe is going to be even more interesting. So I'll see you in the next section. Hello guys. So before we proceed forward with the Reflexion agent system, there is one more thing that we have to learn about, which is how can we get structured outputs from LLMs. This is something that I did not get a chance to cover in my LangChain course. So let us actually take a look at it, and let's look at some slides right now. So it is often useful to have a model return output that matches a specific schema that we define. So if you can imagine, this is what software engineering is all about, right? So we're always going to be dealing with structured data. So there's going to be some object or in a JSON format, there are some properties that we extract and we do some manipulation. The way we put it in the database is going to be in some structured format. But so far we've only been dealing with LLMs that just give out some random string that we can't really do anything solid with, right? So that is something that we can change. We can actually tell the LLM, give it in a structured format, give it in a JSON with these exact properties. So we can actually do that. Okay, so I'll give you an example. So let's say, I'm saying, okay, tell me a joke about cats. Okay, so the LLM normally, without any structured outputs, what it's going to do, it's just going to give a string saying that, okay, here's a joke, right? But what if I tell the LLM also, give it to me in this particular output? Okay, so I want a JSON. In that JSON, I want a setup punchline rating, and I want these values. Not exactly these values, but this is what the output of the LLM is going to be. Okay, so why was the cat sitting on the computer? This is going to be the setup of the joke. The punchline is going to be because it wanted to keep an eye on the mouse, right? Okay, this is funny. And also, I'm also telling it, give a rating as well, and give it to me in this exact format so that I can take that object that you give, the LLM is going to give, and let's say put it in the database, or do something with it, or show it to the user, right? So we have it's not just this, we also have options to get outputs in formats such as JSON, dictionary, string, YAML, HTML, right? Okay, so there's a bunch of different formats that we can actually force the LLM to provide value, provide the content in. Okay, so that is what we are going to be learning how to do that in this particular section, because this is an important thing that we have to understand so that we can easily learn the Reflexion agent architecture pattern. All right. So there's a couple of types. There's a couple of ways in which we can actually, force the LLM to give structured outputs. And the first one is going to be using pydantic models. Okay, so if you're somebody who's new to Python, I'll quickly go through, what pydantic models are and how it can be actually used in the context of LangChain and LangGraph. So a pydantic is a Python library that helps define data structures. It acts like a blueprint for data. It uses Python's type hints like string, integer to enforce correct data types. So how does it work in LangChain? So we basically define a class with the fields we need. So let's say we need name, property, capital, and language. We also specify, give some description for each of those properties. And we can use this particular method. This is going to be the magic method. So we can use this with structured output to tell the LLM to follow this particular format. So let me give you a quick example as well. So yeah. So you can see that initially I have imported, the base model and the field from Pydantic. Okay. And we've also initialized a model. You don't have to use OpenAI. We can always use other chat models as well, and it is going to work perfectly fine. Later on in the course, we are going to be switching between a bunch of different models. We are going to be using, Grok. We are going to be using we are going to be using llama models and a bunch of different things, but no difference. All that you have to do is swap this chat model with another chat model. That is it. All right. So now that we have a model initialized, we are going to be defining a pydantic model. Okay. So let us say, the question that I want to ask LLM is tell me about France. Okay. Something very dumb, but the point that I want you to take away from this is, let's say this is the question that I want to ask the LLM, and I don't want the LLM to just give a string response. I want the LLM to give a response in a structured format. So I want the response to have a name, a language, and a capital. Okay, so in this case, the name is going to be, I'm going to give a description as well using this field class. So I'm saying name of the country. I'm giving additional information to the LLM. So language is going to be the language of the country, capital, the capital of the country. Okay, and also we are going to be giving additional information at the top right here. Okay, saying information about a country. So these are all very important. I'll tell you exactly how these actually play out in the API call that we make to the LLM in just a minute. But this is how we actually define the pydantic model. Okay, so we have the name, we are importing the base model, the description, we are also giving descriptions for each of the properties and also the data types for each of those properties. All of these are very important. So now that we have the pydantic model, we are going to make use of the with structured output method that is going to be available in the LLM, and we are passing in this thing, and that is it. So now we have a slightly supercharged LLM that we can invoke on. Okay, it's not going to be a normal LLM. This LLM now has internally what is happening is this is going to be considered as a tool. Okay, so this is going to be considered as a tool for the LLM. Now this tool is basically made available to this particular LLM, the structured LLM, and we are also forcing the LLM to only use this particular tool. Okay, so if this does not make sense, don't worry, we are going to be deep diving, we're going to be learning all sorts of different things about tools and tool calling and all these different things. But for now, just know that this is a tool that we are providing to the LLM using this particular method, and we're also forcing the LLM to only use this particular tool. Okay, so now we have the structured LLM, and if we now were to invoke and pass in this string, we are going to get back in a very structured way. Okay, the response is going to be very structured in this exact thing. So let me go ahead and run this block. So right here you can see that we are getting a runnable binding, and in this runnable binding you should be able to see, this is not really necessary for you to know right now, we don't want to complicate it, but we can see that we have this output format, we have the schema, right? So if I were to invoke this, run this, now this is going to be the response from the LLM. So now you can see this is going to be a pydantic model, and inside of which we have the name, language, and capital. Okay, so next up, let me also show you how the request payload looks like when we make the call to the LLM, and also the response payload. All right guys, so this is going to be a very simple sample request payload. Okay, so this is what LangChain sends to the OpenAI API. So you can see that we have the messages, this is what we provided, no difference. But in addition to this, there are two other things, okay, that are going to be sent. Okay, so in this tools we are providing, okay, so you can see that this is a single object. So if you remember this pydantic model that we wrote, that is going to be available as a tool to the LLM for the LLM to call. Okay, so this tool is going to have the type function, and the name is going to be country. Okay, so it is basically going to take this is going to be considered as the name of the tool, and whatever we provided here is going to be considered as the description of the tool. That is how the LLM knows we have to use this particular tool. Okay, and now we have this important property called parameters, inside of which we have these properties. This is very important. Okay, so we are basically saying we absolutely need this name. Okay, so the name is going to be type string, description is going to be this, same thing for language and capital, and we're also specifying that these three things are required as well. Okay, so this is how, so basically whatever we write here, this is how it is going to get converted, okay, when we actually make the API call to the LLM. All right, so perfect. And we're also finally, Okay, so let me close this. So now we saw that we are making this particular pedantic model as a tool and we're making it available to the LLM. That is one thing. Secondly, we are also, saying the tool choice absolutely have to be. So when we say tool choice, what it means is you don't have a choice LLM, you have to use this particular tool. You have to use this particular schema, and whatever response you're getting, you have to absolutely use it. So that is what this means, and we're just giving the same name so that we can the LLM can refer back to it. That is it. Okay, so perfect. So now that we know how the sample request payload looks like, this is how the response is going to look like. Don't get confused about all of this, but this is how you are going to get the response. Okay, so you can see that the response from the LLM is going to be a JSON as well, but it is going to have the name, language, and capital. And what ends up happening is after LangChain, LangGraph, our application, right after this, this information is received by our application, it is going to parse it. Okay, so all of that is going to be taken care of by this particular method. Okay, so it is going to parse it, it's going to convert it into a pedantic model, right? It's going to validate as well. Okay, so that is one thing that you have to remember when we're dealing with a pedantic model. So, during the conversion process, it is also going to validate if each property is actually present and all the data types are all matching and all of that. It's just going to make sure that, name is present, language is present, capital is present, and also, is this a string, is this a string, is this a string as well. So it's going to do all of the validations. If at all the validations fail, it is all automatically going to throw an error that we can easily catch and then do a fallback with it. Okay, so this is the first way of doing it. Okay, so I hope that was clear to you. If at all you have any questions, let me know in the comments, or you can just go to Google, type structured outputs LangChain, and you can go through the documentation as well, and it would make complete sense to you. Okay, so this is the first way of doing it. So what if you don't really want the validations part, right? Okay, so you just want to tell the LLM, give the response to me in this particular schema. So in this case, if you don't want the additional validations, you can always go for coming down, you can always go for type dict. Okay, so before we use the base model from the pedantic, but this time we can always use the type dict. So basically type dict is a Python class. You're basically creating a schema for a dictionary, and you're saying, okay, this is the data type of this property, this is the data type of this property, etc., etc. So right here you can see that we are defining the schema, this time using the type dict. It's going to have, okay, this is going to be a joke to tell the user. We have a setup, punchline, and rating, and this is how we give additional information. So we can actually use the annotated class from typing, and we can use this to provide additional information about this particular property. The first, this thing that we are providing is going to be the data type. The second argument is going to be the default value that we assign to this particular property in case the LLM does not generate a property. Okay, so in this case, we are not providing a default value. The third one is going to be the description. We are giving more information about this property so that the LLM knows exactly what this property should hold. Okay, what value it should hold. I hope that makes sense. So this is one way of doing it. Okay, so we can also, for the punchline, we are doing the same thing. For the rating, we are basically just saying that, this is not absolutely important. Rating can be like omitted. So in this case, we are making this int as optional. We're giving a default value of none. And we're also saying how funny the joke is from 1 to 10. Okay. And finally, now that we have the class ready, we are providing the same thing here, and the structured LLM is going to invoke it. And now when we run it, let's give it a few seconds. Okay, great. So you can see that we are getting the exact same thing. Okay, so we are getting setup, punchline, rating. Perfect. Okay, so this is the second way of doing it. Okay, great. So let us look at the third way of doing it, and that is basically just by providing a JSON schema. So we have to give a title and a description. So these are the three properties that we need in the final dict that it provides. So here we have the type string, description, punchline to the joke. So this is actually basically the equivalent to what we're doing here, but without the class. And we're also saying these are the two things that are required. The rating is not required. So if we pass it the same thing here, if I run this, I should get the same thing. Okay, so why was the cat sitting on the computer? Punchline is going to be, okay, because it wanted to keep an eye on the mouse. Okay, rating, perfect. Okay, great. So now I hope that you understand how we can actually use this pedantic model, how we can use the JSON schema, or how we can use the type class to actually tell the LLM to provide its output in a structured way. So this is particularly important because in the next section that we are going to be dealing with, where we will be building the Reflexion agent system, there we will actually make use of the first type, which is going to be the pedantic model. Okay, so there I might not be using this particular method. I might be explicitly providing the tool. Okay, this I'm going to consider this as a tool. I'm going to be providing it to the LLM directly like this, but the underlying mechanism is the absolute same thing. So if you recall the request sample that we looked at, it is going to be the same exact thing, no different. Okay, so I hope this made sense to you. I'll see you in the next section. Hello guys, welcome to the section. In this section, we are going to be looking at a brand new system called the Reflexion agent system. I hope that is how it is pronounced, but this system basically sort of addresses some of the drawbacks that the reflection system that we saw in the previous section tends to have. So we'll do a quick recap of what we saw previously. So we saw that the reflection agent system, right, the previous system that we saw, consists of the generator and a reflector component. Although iteratively making a post better is significantly better than just prompting ChatGPT, the content generated by the reflection system is still not grounded in live data. It could be a hallucination or outdated content, and we have absolutely no way of knowing. I'll give you a very simple example. Let's say I'm a marketer and I want to write a blog post on, how is AI helping small businesses grow, right? So that could be a blog post, right? If I were to feed it to a reflection, basically the basic reflection system that we saw in the previous section, what it might do is it might actually write something, but it is based on whatever the model has been trained, last year or something like that. It tends to have a cutoff date, right? But if in order to write a really enriched blog post, it's very important that we need to provide it a lot more recent news that happened, or we need to provide the system the ability to make API calls, Google search, if that is what it's needed, right? So that is how, having citations instead of the blog post, like, this is the URL that I referred, this particular data from. So all of that is what makes a blog post really enriched, right? And that is something that this reflection system is not really capable of, because we are not really making any tools like Tabili search tool that we saw, right? We're not making it available to the reflection agent system. Okay, so that is a drawback of a reflection agent system. So that is exactly why this Reflexion agent system, it addresses this particular drawback. So let us look at what is the Reflexion agent system. The Reflexion agent, similar to reflection agent, not only critiques its own responses, but also fact checks it with external data by making API calls. In this case, internet search. In the reflection agent pattern, we had to rely on the training data of LLMs, but in this case, we are not really limited to that. So the main component of a reflexion agent system is the actor. The actor is the main agent that drives everything. It reflects on its responses and re-executes it. It can do this with or without tools to improve based on self-critique that is grounded in external data. So let us look at some of the main subcomponents that are involved in this particular system. So we've already seen that this actor agent is going to be at the very top, right? It is what is going to be driving everything. Underneath it, we have all the subcomponents. So the first one obviously is going to be tools or tool execution, right? In order to ground a response with live data, we need tools like Tabili search tool, which is going to make API calls and understand, what is exactly happening. And then the first sub agent, you can think of it as a sub agent, and that is going to be the initial responder, okay, or the responder agent. So basically the responder agent's job is to generate an initial response, and it is also going to do some self-reflection. Okay, later on we'll look at the diagram and it would make sense. So we've got tools, we've got the responder agent, and we've got the revisor agent finally. Okay, so the revisor agent's job is to re-respond and reflect based on the previous reflections. And also the reflection agents are thought to have episodic memory. In the context of reflection agents, episodic memory refers to an agent's ability to recall specific past interactions, events, or experiences rather than just generalized knowledge. This is crucial for making agents feel more context aware, personalized, and human-like over time. So here is a very simple diagram that the documentation provides about what is a reflection agent system. Okay, so for now you can actually see that we have the actor right here, right? So this is going to be the high level. This entire thing can be thought of as the actor, inside of which we have the responder agent, we have the revisor agent, and we have the execute tools, right? We have the tools right here. So let's actually take things one step at a time. Let's understand what this responder agent is actually going to do. Okay, so let's say this is the user. The user wants a 250 worded blog post on the same prompt, right? On how can businesses utilize AI, or rather small businesses utilize AI to increase growth or something like that, right? So in that case, that user request is going to the responder agent, and the responder agent will basically output something like this. Okay, so this is going to be the initial response. So this, you can think of it as a JSON structure, and the JSON structure is going to have three different properties, and the first property is going to be the response, right? So the response is basically just a 250 worded blog post that the LLM thinks that this is what is the right thing. And along with the response, it is also going to attach another property which is going to have critique. So essentially it's like writing its own blog post, and then it is actually looking at the blog post that it has written, and then it is actually critiquing it. Okay, so the LLM is doing all of that in one shot. This responder agent is doing all of that in just one shot. Okay, so it is thinking, okay, this could have been better, this could have been shorter, this could have been, there's a lot of redundant, excessive information that nobody really wants to know. So it's actually critiquing itself. And depending on whatever it has written, it is also going to suggest some search keywords. Okay, so it's also going to suggest some search keywords. So basically, let's say the LLM is going to write the blog post, and then it feels like it would write it better if it could have latest information about certain things. So it is actually suggesting those list of search keywords right here, okay, in this third property. I really hope that this makes sense. So what is next? So the next thing, you can see that the control flow is coming to this tools component right here. So essentially, whatever search keywords, the list of search keywords that the responder agent generated, this tools component is actually going to, the Tabili search tool. If you remember, in the first few sections, we looked at what the Tabili search tool does, right? It's basically just a tool that goes into the internet, searches for these particular keywords that the LLM suggested, and then get the responses and then send it back to the next component. That is exactly what the execute tools component does. So what do we have so far? So far, we have the initial response with the response, critique, and the search terms. We also have the results, the internet search results of the search terms as well ready. So we have both the initial response as well as the new data, the live data ready. Now, both of those information is now fed into the second subcomponent, which is going to be the revisor agent. Okay. So this revisor agent is going to get both those information, and then it is going to look at, these are the existing things, these are the new information, and now it is going to generate a revised response. Okay, so it is going to generate a revised response with a revised response, a revised critique, a revised search term list, right? And it is also going to add something else called citations. You can see that it is the first three properties are very similar, right? It's got response property, it's got the critique property, it's got the search property, right? Except since this is the revised response, the content is going to be the revised content, the critique is going to be the revised critique, and then the search is going to be the revised search. And additionally, there is going to be another property that is going to be added, which is called citations. So basically, any research paper that you look at, the content itself would have like 1, 2, 3, 4, and then clicking on it, it is going to take you to the citations link where that actual fact has been taken from, right? So that is what is called citations, and we are also instructing the revisor agent to add the citations as well. So all of this content is going to be revised. All right. Now you can imagine that after the revised thing is done, the LLM might think, you know what, okay, now I have extra information, but I want even more information based on whatever it is that I've written. So in that case, the search list is going to have new keywords, right? 1 or 2 or 3 new keywords. And again, the execute tools is going to go fetch that information, and then it's going to come back to the revisor, and this loop is going to keep it's going to go on for a couple of times. I hope that makes sense. You can actually imagine how powerful this could be, because with every single iteration, there is new information getting fetched from the internet, and it enriches the content a little bit more every single iteration, right? It's going to ground all the content with live data, right? And also, don't worry that the length of the content is not going to keep on increasing or anything, because we will also tell it, okay, only keep it to 250 words. So you can imagine that that content is going to get more and more enriched with live recent information, and it would make for a really good blog post, right? So after it sort of repeats for a couple of times, it is then obviously it's going to go back to the user. So this is what is called a Reflexion agent system. If this sounds too much for you, don't worry. We are going to be taking it one step at a time. We are first going to be building out this first component right here, and then we are going to be building out the revisor component, and then we are going to be building out the execute tools, and then connecting it all together using LangGraph. So by the end of this particular series, this section, you should have a pretty good idea. So in the next section, we are actually going to be implementing this particular system using code. So I'll see you there. Hello guys, in this section, let's actually go ahead and build out the first component right here, the subcomponent of the actor agent right here, which is going to be the responder agent. Okay, so the reason why we call both of these agents as subcomponents of the actor is because the base chat prompt template, the prompt template is going to be of the actors, and both of these subcomponents are going to use the same, basically reuse the same prompt as that of the actor. If that does not make sense, don't worry. Let me just quickly copy paste some code right here. You can see that I've already created a folder called Reflexion agent system. I've created another file called chains. So this file is what is going to house all of the different chains that we are going to be building. All right. So let me copy paste something right here and let me walk you through it. All right. So all that I've done here is that I've just called it the actor agent prompt. And then I've imported, chat prompt template and the messages placeholder, no different to what we've done in the reflection agent in the previous section. All right. So let's actually go back to the diagram. Let's see what is the, goal of this responder agent. So we know that the goal of the responder agent is to finally, after so many processing, finally we need a response like this, right? Let's keep it very simple. Let's keep it very high level for now. The responder needs to output a JSON, and the JSON then needs to be converted into a proper Python dictionary that is going to have this particular structure, right? So the initial response should have the response, the content of the blog post, the critique of the written blog post, the search keyword terms, all of that needs to be available, right? So this is exactly the goal, and that is how we are going to be writing the prompt as well. So let's actually go look at the prompt of the actor. All right. So you can see that we have the system, which is going to be, you are an expert AI researcher, and then we are also providing the current time right here. Why do we need the current time? It's not really super important to understand this, but to give you a very high level, let's say you're giving a task to the agent to talk about something that happened recently, current affairs or something like that. It having access context of what time it is can be important, because accordingly it can make Google searches and then figure out if it actually needs to do something or not, if it actually needs to look at Google or not, right? So we have the first instruction right here. This first instruction, basically we've got 1, 2, 3. These 1, 2, 3 corresponds to these things right here. Okay, so we've got the response, critique, and search. This is going to be for response. This is going to be for critique. This is going to be for searching. Okay, so we will dynamically import this later. This alone can change depending on whether you're building the responder agent or the revisor agent. But for now, since we are only focused on building the responder agent using the actor prompt template, so we are going to have it as a placeholder right here. I hope that makes sense. This will later on, write a 250 word blog post right here. Okay, that would be the instruction. Let's look at the second one. Reflect and critique your answer. Be severe to maximize improvement. Right? We want it to be really severe about what it has just written. It is all going to happen in one single, to and fro, right? After the reflection, list 1 to 3 search queries separately for researching improvements. Do not include them inside the reflection. Okay, so we're also providing, instructing it to provide the search list of search queries as well. And then finally, we also have a messages placeholder that could be, this could be the place where the actual human message would come and sit. So the human message in the future, when we actually run it, it's going to be something like, I want to blog post on, this particular topic. So that human message is going to come sit inside of here. And then finally, we have another system message, which is just to, we don't really need it right here, but the reason why we provide, this answer the user's question above using the required format, the reason why we provide it at the bottom as well as the top is because LLMs tend to, pay a bit more attention to what happened at the start and what happened at the end. So we just just to make sure we are providing this. So this is going to be the prompt template. This is not really something that I wrote. This is a prompt template that is very standard for the Reflexion agent system. I pulled it from the internet. So yeah, that is what I've done here. So let's actually go back to the diagram. So you can imagine that, if I were to, use this prompt template, and if I were to, invoke that particular chain, send it to the LLM and invoke that chain, it is going to give you, a response with this particular response. It's going to give you a critique, it's going to search. All of it is good. But at the end of the day, we want something concrete like this. We want a Python dictionary. We want a proper dictionary or like a model that we can actually access the values from, so that we can extract those things and then send it to the execute tools and do a lot of other things, right? But you can imagine that LLMs are a little messy. They sometimes don't provide the right properties. They sometimes, tend to mess up as well. So it's a tricky thing, but we actually have a solution to basically force the LLM to ground the LLM to provide a response in a particular schema. Okay, so that is going to be the main takeaway in this particular section. So let's actually look at how the exact processing is done. What are the different what are the different steps that we have to take to ground the response of an LLM to provide a JSON structure in a very, we are forcing the LLM to provide a schema. We're forcing the LLM to provide the response in a particular schema. Okay, so let's actually look at how that is being done. So I'm calling it the LLM response parser system. So let's actually understand the theory behind it, and then we'll jump into the practical stuff. This system converts unstructured LLM outputs into well-defined Python objects through a series of structured parsing steps, ensuring data validation and consistent formatting. So what are the key components? We have already written the actor prompt template. That part is done. Let's look at the next one. Function calling with a pedantic schema. And then the third one is going to be something called a pedantic parser. So since we already understand chat prompt template, let's actually move on to the second one, which is going to be the function calling with a pedantic schema. So we already know what tool calling or function calling is, but just to give a refresher, similar to how we make tools available to the LLM, we can also send a schema to the LLM and force it to structure its JSON output according to the schema. But what is pedantic right here? So we already understand the function calling, we understand schema, but what is this pedantic? A Python library that defines data structures using classes. It provides automatic validation of JSON data against these class definitions. So to quickly recap, we just defined the schema and then we add it as a tool during our function call to the LLM, and the LLM is going to call that particular tool, structure its output accordingly. Very simple. Let's look at the last one, the Pydantic parser. It takes the JSON output from the LLM's function call. It validates it against the defined Pydantic schema or the class definition. It creates instances of Pydantic classes with the validated data. If the LLM's output does not match with the defined schema, it will throw an error. So this Pydantic parser, you might have some difficulty imagining what it could look like. So basically, the previous Pydantic model that is a tool that we make it available to the LLM, that is basically just going to ground the output of the LLM. Okay, it's just going to force the LLM to structure its output in a certain way. But we also need another line of defense, wherein we also have to validate if the output of the LLM is actually adhering to the schema, to the model, Pydantic model. Okay, so that is what this Pydantic parser does. It takes the JSON output, it validates it, and then it is going to create an instance, a class or a model, and it makes it easier for us to use Python and then extract the stuff and then start working with it. Okay, so these are the steps. So far what we've done is we've written the actor prompt template right here. The next step is we need to actually go ahead, and before we start invoking it, we actually need to go ahead and create a schema file right here. So that is exactly what I'm going to do. So to do this, I'm just going to copy paste some code right here and let me walk you through it. All right, so this could be a lot, so let's take it one step at a time. So what I've done is I've imported from the Pydantic module, I've imported the base model as well as the field. Basically, let's not overcomplicate it. The base model is just giving you the tools to define a schema. Very simple. All right, so let's go back to the diagram. So what are the three things that we need? We want the main response, we want the critique of the generated response, and then we want the search. And that is exactly what we're providing right here. Okay, so we defined a class called answer question. We are providing in the based model right here. And first off, we need the answer, right? So the answer is going to be in a string format, and the field is going to have a description, right? So here we are actually suggesting a 250 word detailed answer to the question. Okay, so not only are we providing the 250 word prompt in the chat prompt template, we're also doing it here. So there is like a double defense where we are grounding the response of the LLM properly. Okay, so we have the response right here. Okay, so the first one, the response is done. The next thing is we can probably provide in the search and the critique, right? And that is exactly what we've done. We want the search queries to be a list of strings, and the description is going to be 1 to 3 search queries for researching improvements to address the critique of your current answer. And then finally, we have the reflection here as well, which is going to be the critique. We can name it whatever we want, but the reflection is going to be your reflection on the initial answer that is going to be right here, right? So that is what it is. And also note that this reflection is also going to have two different sub properties, right? So you can see that we have missing as well as something called superfluous. Okay, so we'll get to what that is in a minute, but missing is, it is a critique of what is missing. So whenever we are, reflecting on, or rather critiquing on a particular passage or something like that, we either think of it in terms of, this could be shortened or this could be made better, right? So that is what we're talking about. Missing is like, what is missing, what could be made better. And then superfluous is what is excessive, what is redundant, what is not needed, right? So a critique of what is superfluous. All right, so this is going to be the base schema that we are now going to use to ground the response of the LLM properly. So let's actually go ahead and do that. So let me come back to the chains. Let's see if everything is done. Okay, there's one more thing that I want to do. I want to do a partial, and I want to pre-populate the time. Okay, I don't really want to do it during invoking. So let me just paste this right here. So basically this partial method is something that you can use to pre-populate placeholders, before even invoking a particular chain, right? So that is what we've done right here. We are making use of the datetime module of Pythons. All right, so now let's go ahead and write the chain for the responder agent. So what I can do is I can call this first responder prompt template. So here I can make use of the actor prompt template right here. And I just want to fill up the first instruction. Okay, so you can imagine the first instruction is going to be a very simple, write me a 250 word blog post, right? So that is exactly what I'm going to fill it up right here. So I'm just going to say first instruction, provide me a detailed 250 word answer. Okay, so the first responder prompt template is now done. Now I'm going to create the chain for the first responder. So I'm going to call it first responder chain, and I can use this particular prompt template, and then I can pipe it with the LLM, right? So when I pipe it with the LLM, remember we also have to provide in that answer question tool that we have written right here to the LLM, so that it can call that tool and then use that tool schema to ground its response. So I'm just going to say LLM dot bind tool. Okay, so we haven't actually provided the LLM yet, right? So let's actually quickly go ahead and do that. So to do that, I'm just going to go to, from LangChain OpenAI, import chat OpenAI, and I can come down here, say LLM is going to be equal chat OpenAI. I can send in the model to be GPT-4o. Okay, perfect. All right. So now the bind tools method is going to be available. So inside of here, I can provide in the answer question schema that we've just written in the schema, this thing. So let's just quickly go ahead and import that as well. So I'm just going to say schema import. The name of this is going to be answer question. So let's import that and let's just go ahead and provide that, and that is it. So we provided this particular tool, and since we are actually confident that this is the only tool that the LLM has to use, right? We don't want it to use multiple tools. We are sure we are mandating the LLM to only use this particular tool. So there is another property that we can actually provide, which is called tool choice, and inside of this, in a string, we can just provide the same thing right here. So this is going to force the LLM to call that one particular tool, structure its output in that particular schema properly. Perfect. So if you remember, we also need to pipe it with something else. So not only is it enough that we get the JSON response, we also have to convert the JSON response into a pedantic class so that we can easily sort of interact with it, extract data out of it. So to do that, I'm going to be using the pedantic parser. So that is going to be OpenAI's pedantic parser. So I'm just going to come up here and I'm going to paste this line. So here, basically from the core package, output parsers, OpenAI tools, and I'm going to be using the pedantic tools parser right here. And I can just come down here and I can instantiate it. So I can just say pedantic parser, and I can just basically call this and provide in the tools as well. So it will know exactly how to extract the information, and now I can provide it right here. All right, so now all that is left is to basically just invoke this chain with a human message. Basically whatever I as a human, I as a marketer want to prompt this particular system. Okay, so I'm just going to say first responder chain dot invoke, and right here, if I come up here, you can see that in the messages placeholder, we have the messages variable, right? So I'm just going to say messages, and this is again going to be a list, right? So inside of this list, I can just put the human message. Okay, it looks like we have not imported it up here. So I can just say from LangChain core messages import human message. Let's copy this, put it here, and then so for the content, I can just say something like, write me a blog post on how AI can, or rather how small businesses can leverage AI to grow. Okay, very simple. Now this is going to give us the response. Let's go ahead and print out the response as well. Perfect. So let me make sure that everything is looking fine. All right, so let's go ahead and run it. Let's hope that everything works fine. Perfect. So you can see that we've gotten the response in the exact same structure that we wanted, which is in the format of the Pydantic class itself. So we have the answer question, inside of which we have the answer right here. And then let's actually go back to the schema. Let's see, so yeah, so we can see that the answer is right here. Okay, there's not really enough space for us to look at everything. Okay, so we've got the answer right here. And then we have the search queries as well. So let me actually copy paste the search queries here. You can see that the search queries is also going to be a list of 3 things. So how small businesses use AI, AI tools for small business growth, AI benefits for small businesses, right? And finally, we have the reflection here as well. And you can see that inside of the reflection class, we have the missing as well as superfluous. So in the missing, it is saying the current answer lacks specific examples of AI tools or services that small businesses can use. And then we have the superfluous as well. Okay, this is basically saying this is overly detailed, right? Make it shorter, right? So you can see that we are getting all the data in the exact format that we needed it. I know that this output in the terminal can be a little difficult to read. So what I'm going to do is I'm just going to go ahead and create a new project. Let's actually generate a new API key and then copy this thing and then come back to our environment variable. Let's paste it right here. We don't really need the API, the OpenAI API key, because we already have this here. Let's come back and let's clear this out. Let's try to run it again. So let's actually delete off all the terminals and then let's run it again. So let's give it a few seconds. All right, perfect. So let's actually go back to our LangSmith and let's see. Perfect. So we actually have something that is generated right here. So let's actually go inside, look at the traces, and right here you can see that this runnable sequence is going to be the high level, overview of what happened. So here we have the human message provided, and here we have the output, right? So you can see that it's a neat list of just one, object, and that is going to have the class, the Pydantic class or the Pydantic model, and you can see that it has the answer, right? Okay, it can be a little bit difficult to read in the terminal, so I tend to come here. So you can see that this is the answer. And then finally, the reflection is going to be, these are the things that are missing. Okay, we're not talking about costs. We're not talking about the technical expertise. So you can see that, it is generating this thing and it is also, critiquing itself. It is saying these are the things that are missing. Superfluous is like these are the things that are redundant or excessive, right? This, mention of AI-driven customer service, it's considered generic, be more specific is what it's saying. And then it is also suggesting some search queries for the next component. Okay, we'll get to that in a minute, but these are the search queries. AI for small business growth, AI tools for small businesses, and then finally small businesses AI solutions. All right, so this is going to be the high level thing. If you further want to look at what were the outputs of each and every single component, we have it right here. So this was the original prompt template, right? So you can see that this is already populated. This was the first instruction that we provided, human system, and then this was the output. Okay, so this, you can see that this is a very simple JSON output. The LLM is actually grounding its response properly based on the Pydantic schema that we've provided. So this is going to be the tool call ID. If you do not know why this is for, we'll cover that in a few minutes. But yeah, this is going to be the output of the LLM, which is a proper JSON object. Perfect. And if you want to know what this Pydantic tools parser did, it basically just took this entire JSON object and then it just basically formatted it in a Pydantic model sort of a way. And this can also be helpful in certain situations. Perfect. So in this section, we wrote the prompt template for the actor agent, and then we used that prompt template to write the responder prompt template, and then we created a chain out of it. And then we also learned exactly how to parse and ground the response of the LLM into the structure, into the structured format that we wanted. And we've learned so much in this section, so that even in your own projects, you know exactly how you can actually ground the response of a particular LLM's output, right? All right, so great. So we are done with these two sections right now. In the next section, what we're going to be doing is we are going to be doing the same thing for the Revisor agent. And once we're done with that, then we'll come back to building the execute tools. So I hope you learned a lot, and I'll see you in the next section. Hello guys, welcome to another section where, this section is going to be relatively very simple. So in the previous section, we basically looked at the responder chain, right? And the actor chat prompt template. In this section, we are going to be building out the revisor chain. Okay, so this is going to be relatively very simple. We already know how we wrote the responder chain, right? So we reused some of the reflection, the actor prompt template. We just changed the first instruction right here, right? So we have the actor prompt template, and to build out the responder chain, we just changed the first instruction alone, and then we created a chain out of it. We provided a tool as well to ground its response. So we are going to be doing the exact same thing for the revisor as well. So this should be pretty easy for you to understand. So what I'm going to do is I'm going to call this the revisor chain, and I'm going to use the same actor prompt template that we've written right here. So, and then I'm going to say partial, and I'm going to pre-populate the first instruction alone. So the same thing that we did right here. So I'm just going to, pre-populate with some data right here, some content. So let me just copy paste the content right here. Okay, so this is going to be the revise instruction. So essentially what we're saying is revise your previous answer using the new information. You should use the previous critique to add important information to your answer. You must include numerical citations in your revised answer to ensure it can be verified. We also ask it to add a references section at the bottom of your answer, which does not count towards the word limit. So at the bottom, we suggested to add these links. You should also use the previous critique to remove superfluous information from your answer and make sure it is not more than 250 words, right? So I hope that makes sense. Whatever the responder is providing, the revisor has to look at all of that based on the critique that the responder provided, and based on the search results, it needs to generate a revised response. Okay, so that is what we mean right here. All right, now let me just copy this and put it over here. Perfect. So the chain is not yet ready yet because we still have to ground the response of the LLM in this particular revised response structure, right? So it's basically very similar to what we did in the responder chain. We had this, let's go back to the schema. So we had the answer question model, right? The pedantic model. So this had the answer, search queries, and reflection. If we come back to the diagram, this also has the same answer, the response, critique, and search. No different. But in addition to that, we just have the citations right here, right? So I'm just going to go ahead and create a separate class for this thing called revise answer. You can name it pretty much anything that you want. And this revise answer is going to inherit all of the base properties as the answer question. So if you remember, there is a lot of overlap, right? So I'm just going to put it right here. And then let me just copy paste some code. All right. So all that this is doing is it's going to inherit all of the answer question, these fields. And then we are saying revise your original answer to your question. And then in addition to all of that, we're just providing the references. So this is going to be a list of strings, and the description is going to be citations motivating your updated answer. All right. I hope that makes sense. Now let's come back to the chain. And very, very similar to what we did in the responder chain. So let me scroll up right here so that you can see. So this is the responder chain. All that we're doing is we are piping this template with the bind tools, and then we are forcing it to only use the answer question tool, responder, right? So we are going to do the same thing here as well. So this is going to be the prompt template. Let's pipe it. So let's go ahead and pipe it with the LLM. So we are going to say bind tools. And then let's provide in the tools, which is going to be an array of this particular revise answer schema. So let's provide that here. Okay, so it is not imported. Let me go up here and let's quickly import it. Okay. Perfect. And we're also forcing it to only use this particular revise answer, which is now going to be a string as well. And that is pretty much it. So let's come back to the diagram. So far we built out the responder chain. We've built out the revisor chain. In the next section, we are also going to be building out the third component, which is going to be the execute tools method, right? So once we have all of the building blocks done, connecting it all together using LangGraph becomes a piece of cake. Okay, so I'll see you in the next section. Hello guys, so in this section, let us now go ahead and build out this particular component, the execute tools component, because this is what is next in line, right? So far in the state, you can imagine that we have the initial human message, right? If you remember the initial human user's message, and then the second item in the list is going to be the AI message that has this information, right? So the AI message is going to have the response, critique, and search terms. The search term is going to have 3 different search terms, right? So the next component, which is this execute tools. So all the execute tools method has to do is take out the last message, which is going to be the AI message, right? It just needs to take that out. And then it needs to look at the search terms that are present. So we are going to now have 3 different search queries, right? So all that it has to do is loop through each of those, and then with each iteration, call the tably search, get the response, compile it all together, and formulate a final one tool message. So we have different types, right? We have human message, AI message. So the initial human message, that is the first item. The second responder chain is going to give out one AI message. And then this execute tools is going to give out one tool message. Okay, and in that tool message, in that content, we are going to have all the information. I hope that makes sense. Let us now see how we can implement it. So let's jump back to the VS Code, and you can see that I've gone ahead and I've written out the code. I've created a file called execute tools inside of Reflexion agent system. So this method is what we need, right? So this is going to be our execute tools node, right? So this state, you can imagine, is going to get a list of messages, the human message and AI message at the initial point when this is executed, right? So we have human, AI, and then when it hits it, we are going to have human and AI message in the state. So we're just going to get the last AI message, and we're going to do a bunch of different things. So before we go through this, let me show you, I've prepared a dummy state that we can actually pass in here just to test out the method to make sure everything is working fine. So as I told you, we have the first item of the list, which is going to be a human message, which has some prompt. And next we have the AI message, right? So this is going to be the bare bones structure that this particular responder chain is going to output. Okay, so it's just going to have the content is going to be empty because this time it is actually making a tool call, right? So in the tool calls, the first object, it is going to contain which tool it called, and the tool call ID. So the name and ID is going to be very important. We've just mocked it right now, and then we also have the args. So inside of the args, this is the schema that we had defined, right? So this is exactly how we are going to get. So if you're curious, you can just go print out, the output from the responder chain, and this is exactly how you're going to get the AI message. Maybe there's going to be a lot more information, but this is the information that we are interested in to test out this method. Okay, so the answer we're not really interested in right now. I've just left it as empty string. What we are interested in is the search queries, these 3 things. Okay, so yeah, that is what I've written here. The missing and superfluous also, we're not really interested right now to test out this method. So yeah, these are the 3, let's say, our imaginary search queries that we need, and this method basically just needs to go through each of those things, call it, and then create a final one tool message. Okay, so in addition to human message and AI message, we are now going to add another tool message inside of this state. Okay, perfect. All right, so let's look at what we are doing right now. We're just going to extract the last AI message, and all that we're doing is testing, checking if the tool calls are present or not. Okay, so if there are no tool call present, it does not make sense to execute those tools, right? Because there are no tool calls to begin with. So that is why we're just checking it. If there are no tool calls, we're just returning an empty array. We don't really need to do anything here, no tools to execute. But in case we do have tool calls, we are going to loop through all of the tool calls that are available. In this case, we only have one, right? So we only have one object right here, which is this one tool call, the answer question. Perfect. Okay, so we are just going to get the tool call ID and the search queries as well. So we are going to get the tool call ID and all of the search queries right here. So we have both of that information here. And now all that we're doing is we're looping through those 3 different items, and then we're invoking the tably search tool that we have right here. Okay, so I hope that makes sense. So if we invoke basically, okay, we're invoking it and sending each and every single query, and that is going to give us 5 different results, right? And then with the results we are getting, we're just putting it in a dictionary, right, with the query. So the way that this is going to be is like, let me just like, quick and dirty, let me just show you exactly how it's going to look like. So we are going to have search term 1, right? So we are going to have search term 2 and 3. Okay, so for each of the search terms we need 5 different, okay, so we need 5 different results, right? So in the first object we are going to have the URL, and the URL is going to have exactly which URL it pulled the data from, so ABC, and then we are going to have content here. Okay, so yeah, this is the content, and the same thing is going to continue 5 different times for each and every single search term. Okay, so there's going to be 5, and similarly this is going to have 5 different objects, and this is going to have 5 different objects. So this is the structure that we are going to be creating using these 3 lines. Okay, very simple. So finally, once we have the entire query results right here in this dictionary, all that we are going to do is we are going to create a tool message, and then we are going to dump all of that. We are converting all of that into a JSON, and then we are dumping it along with the tool call ID. So the tool message is going to be slightly different. Human message, if we are going to create a human message, we just pass in the content. AI message, we already know. In the tool message, along with the content, okay, along with the content, we also need to provide the tool call ID. Okay, so the tool call ID is very important. So the LLM wants to call a tool, it is going to generate a tool call ID, right? So this same tool call ID, we are going to get it from the last AI message. All that we're doing is we're providing it here. Okay, and that is it. So, and then once we have the tool message, we are going to append it in the tool messages. So we don't really need this. Okay, we can just like get rid of this, and we can just return, okay, we can just return it like this also. Okay, so we're just going to return one tool message, and whatever we return, it needs to be in a list format, right? Whatever we return, it needs to be in a list format, right? Because only list and list can be merged in the state that we have, right? In the message graph that we have. So we can do it like this. This should work perfectly well, but I'm just going to do it a little bit more neater. Okay, so I'm just going to, do it this way, and that is it. All right, guys, so I hope that makes sense. That is it for the execute tools component. So we're finally done with, building out the last component in our application. All right, so please, if you have any questions at all, feel free to ask me in the comments, and go ahead, pull the code, run it, try to break it, try to understand what we're trying to do here, and then I'm sure that it would start making sense. All right, so now that we have built out all the components that we need for the system, all that's left is to just put it all together, build the graph, and then run the system. So I'll do that in the next section. So I'll see you there. Hello guys, I hope you're excited about this last section in this particular topic, the Reflexion agent system, where we are going to be piecing together all these different components that we've built into a graph using LangGraph, and then we are going to see it in action. So to give you a quick recap of what we've done so far, we've built out the responder chain, we've built out the revisor chain, we've again built out the execute tools method as well, right? So here's how the message conversation history is going to extend. Okay, I'll give you, it is going to be very, very similar to what we saw in the reflection system that we saw in the previous this thing, right? So initially, as usual, we are going to have the human message as the first item in the conversation history. Okay, so the chains and the system message, they are separate, but the conversation history itself, that thing is going to have human message at the very top, which is going to have my topic. I can say something like, write me something like this, write me a blog post on this particular topic, right? So the first human message, that human message is going to be sent to the responder. That chain is going to be invoked by passing in that particular history, and then it is going to spit out, you can imagine it is going to spit out an AI message. That AI message, inside of the args, you're going to have all the properties based on the particular schema, right? So that is going to be the second step. So the control flow is going to go from the human message to the responder. So right now we have the human message at the very top, and then we have the AI message. Now that AI message is going to be sent to the method, right? The execute tools method that we've written, right? So you can imagine that we've mocked the input and the method is like perfect to accept that AI message, right? So that is going to be the the third step, which is to send all of that, the last AI message to the execute tools, right? So once that is done, the tools is going to output another tool message, right? So the tool message is going to have the content, and that one tool message inside of the content is going to have it's basically going to be an object of three different phrases, and each of those properties, each of those search terms are going to have five of objects, five objects inside of each property, and each of those objects is going to have the URL and the content. So it is only going to be one tool message. Okay, so very similar to what we saw in the reflection system. Every node is going to return an array of just one AI message, of one human message, of not necessarily human message, but sometimes, yeah, we can do that sometimes. But yeah, it's going to return an array usually, and that array is going to be appended to the existing conversation list. I hope that makes sense. And right after the tools, that is going to return an array of just one tool message. That is again going to be this entire thing, this entire history is again going to be sent to the revisor chain, and the entire thing is going to be inserted in the message placeholder of the revisor chain, right? And now we have an option, right? So we can either go back to the execute tools, right? The revisor chain is going to output another AI message with its own search results and with its own critique. So we can either go back to the execute tools, or we can go, end the graph cycle as well. So we can actually set a limit here as well, very similar to what we did before. We can set the limit to 2 this time, right? Because there's a lot of computation happening. There's quite a lot of, tokens that are going to be, not a lot, but a decent amount of tokens are going to be consumed. So I'm just going to set the limit to 2. All right. So I hope that makes sense. So in this section, let's go ahead and create our graph file. And this is going to be relatively very, very simple. It's going to be fun. So let's actually go ahead and get started. So I'm just going to go to our, this particular folder, and I'm going to create this file called, let's call it, a Reflexion graph. All right. Perfect. So up here, I'm going to import a few imports. So basically what I've done is I've imported the list, and I've imported the base message, tool message. These are some things that, basically to strongly type our nodes, I'm just going to, use some of these things. We are using the message graph, and I hope you remember what a message graph does, right? And then we are using the revisor chain and the first responder chain from the chains module. And we are also making use of the execute tools that we've written in the module. Perfect. All right. So the next thing that I'm going to do is I'm going to go ahead and initialize our graph. So to do that, I can just say graph is equal to message graph, and then I can call this, right? That's pretty much it. If you remember, this is exactly what we did previously. All right. So let's actually go back to the diagram. So let's go ahead and first add these 3 nodes. So we have the responder node, we have the executor node, we have the revisor node. If you remember, we just need to say graph.add node, and the first argument is going to be the name of the node, and then the second is going to be the actual node, the function or the chain, right? So I'm just going to say graph.add node, and I'm going to call this responder node as the draft. So you can imagine that it's going to basically, this component is just going to generate the first draft, and this is what is going to actually like make it better and revise it. So I'm going to call it draft, but you can call it anything that you want. You can call it, some random name, and doesn't matter. Don't, just follow what I'm doing. But yeah, so we have the draft right here, and I can just go ahead and put the first responder chain right here. Perfect. So let's actually do the next one as well. So the next one is going to be the this execute tools right here. So for this, I can just use the same name right here, and I can use this method as well. And finally, we also need to add the revisor, right? Okay, so this revisor chain right here. So I'm going to call it the revisor, and I can put in this thing right here as well. All right, perfect. So we've added 3 of these nodes. Let's now go ahead and connect these nodes together. So obviously the first one is going to be, there's got to be an edge between the responder node as well as the execute tools node, right? So to do that, this is going to be another simple edge, right? There is no like, conditional edge or anything. It's going to be a very simple edge. So let's put this draft right here, and then let's put the execute tools right here. Okay, so what we've done is we just drew a line between the responder as well as the execute tools. So the next thing is we need to do the same thing for the execute tools and the revisor. So this is going to be a very simple edge as well, right? So I'm again going to say add edge, and we need the execute tools name and then the revisor, right? Okay, so we want this. Perfect. So we've drew all of the edges as well. Now what happens next? So this line is connected. So the next thing is we have to, right after the revisor, we have two options right here, right? We can either go to the human or we can again go back to the execute tools. So I'm going to write a function, something like an event loop. Basically that function sort of decides, if, two iterations have been done, 4 iterations have been done, it's going to check that. And depending on that, it is going to route whether to go here to the human or it is going to go back to the execute tools, right? So I'm just going to copy paste the method right here, and let me slowly walk you through it. Okay. So here basically what we're doing is in the event loop, again, pretty much every node is going to get the list of all the history messages, right? Human, AI, tool message, human, AI, whatever. The entire thing is going to be received right here, right? So basically here, what I'm doing is I am looking at all these messages and I'm seeing how many tool messages are there. Okay. So we know that, let's come back to the diagram. We know that every time this execute tools component is going to be executed, it is going to spit out one tool message with all the data, right? So if it were to loop a second time or the third time or something like that, the count is going to go up, right? So I'm just going to say count tool visits. I'm basically calculating how many tool messages are there in this particular list. Okay, so that is exactly what I'm doing. I'm looping through it and I'm calculating the sum of it. Okay, and now I am, this is the iterations, and I'm checking if it exceeds my maximum iterations constant. It's a threshold that I'm setting. So I can just go up here. Let's say I can put it over here and I can set it to 2 because that's what we've decided at the very start. You can always increase it as well, but it's just going to take a little bit more time to, fully run the process. Okay, so this is a drawback of this particular section. We'll look at the advantages, disadvantages, and all of that, at the end of the section. But if your product, requires really quick responses for the user, then this system might not be the best thing to do it. But if your users are comfortable with, them taking their, they prioritize quality over, the speed. In that case, we can just go for the Reflexion graph. All right. If the number of tool messages are more than 2, it means that we have to end the graph, or else we can go for the execute tools again. Perfect. So that is exactly what I've done here. So if it is greater than this thing, we are going to the end, or else we are going back to the execute tools node. So I hope that makes sense. Now let's go ahead and add that conditional graph. Okay, so how do we add that conditional graph? We can just say add conditional graph, and then we are basically saying that, right after the revisor, go to the event loop, right? So right after the revisor, go to the event loop. Okay, and then let it sort of branch out into the end or the execute tools. So very similar to what we did in the previous, topic that we saw. Perfect. So I think that's it, right? So we've connected the responder to the execute tools to the revisor. We've connected the revisor with the event loop method that is going to branch off to the end, or it's going to branch off to the execute tools. And finally, if you remember, we have to set the entry point as well, right? So let's quickly do that. So we have to go back and then set entry point to draft. Okay, so because this is going to be the entry point of the graph. All right, perfect. So I think that should be it. Let's go ahead and compile the graph now. So I'm just going to say graph.compile, and finally I can just, create the mermaid diagram as well, just to make sure that everything is looking good. All right, so I'm just going to do that, and also I'm going to invoke the graph as well. So And next up, I'm also going to invoke the graph with my human message. So I can just say app.invoke, and I can provide in my string writer, right, about how small businesses can leverage AI to grow. Okay. So this is going to get the response, and now I can go ahead and print the response as well. So what we have to do is we have to go inside of the response. We have to get the last AI message in the history, which is going to be the AI message. And then we have to go inside of the tool calls. We are not interested in the content, in the main content. We have to go inside of the tool calls. And even that tool calls is going to be an array, right? So we have to go inside of the first array and then go inside of the args. And then we have to go inside of the answer. Okay, I hope that makes sense. If this is confusing to you, just print it out and see how the structure is going to look like, and then it would make sense to you. And why not? Let's also go ahead and print out the response as well, so that we'll be able to see the full unabridged version. Perfect. Okay, then let's actually now go ahead and let's make sure that everything is looking good. All right. Okay, let's go ahead and let's see what we get actually. So I'm going to go back to our graph and let's run this graph. If at all there is any bugs, we'll try to debug it right now. So you can see that this is going to be the graph as well. You can actually pause the video and then look at, if everything is looking good. All right, so we are getting some issue right here. It is saying that, the answer question is not really, the output of the answer question tool call is not really correct. So let's actually go back to the chains. Okay, guys. So this particular chain is not really returning an AI message, right? But rather it is like, going through the parser. So it is not really the AI message, but I just added this thing here for the validation. If everything is working good, I just wanted to test it by adding this parser. So what I can do is I can just remove that. And instead of that, I can put it outside of the chain just to make sure that, the validation is also taken care of. So if at all the LLM is not going to return the schema in the right format, it would still throw an error, but this parser is not going to be a part of the chain. So to do that, I'm just going to say validator Pydantic tools parser, and inside of the tools, I can just provide in the answer question. Okay, perfect. So this is also going to throw an error if at all the output is not really adhering to the schema. All right, perfect. So now the chain is going to be properly ready. It's going to output the AI message, and now it should work. So let me clear it out. Let me come back to the reflection graph, and then let's run it again. Okay, so we'll actually take a look at the LangSmith as well, see what is happening there. But yeah, you can imagine that it might take a little bit of time because the first responder is generating this entire 250 worded this thing, and then it is going to the tool calls are going to happen, and there's like 3 separate search terms that are being called, and then that information is being fed into the revisor, and that revisor is going to loop twice, right? All right, let's see what's happening. Perfect. Okay, so you can see that. Okay, guys, this is a little difficult to read. Okay, let me actually go ahead and search for. Okay, I didn't really put another keyword here for the first print. So I'm just going to come up to the very top. All right. Okay, so you can see that we have, the small business can leverage AI to grow. This is going to be the final revised, the final AI messages, final content. So you can see that the numbers are also here. So you can imagine that at the end of the blog post, we are going to have the URLs as well. So let's make sure that, okay, perfect. So we have the references as well, right? Perfect. And then also we have the unabridged version right here, right? The entire conversation history. You can see that we have the human message, the AI message should be somewhere here, and then another tool message. Okay, let's search for tool message. Okay, so tool message. Okay, it's not really searching. I'm not sure what's happening. Yeah. So we have the tool message right here with the content of the entire, the URL and the contents. We've got everything, and then again the revisor, which is going to have an AI message. So I'm not really able to search for it right here. So let's actually go back to our LangSmith, and then look at, what's happening there. All right, perfect. So this is going to be the latest run right here. Let's click on it and let's look at the trace. So this is going to be the high level. Totally took us 80 seconds. So you can imagine that it might take a little bit of time. So if you don't see anything in the terminal, don't worry, it is going to come. Or if you are worried that something might have gone wrong, don't worry about it. Just pull my code and then just copy paste the code, and then you can debug it later. All right, so here we can see that this is going to be my input, the original input, and it's going to go to the responder chain, right? So this is going to be the output, the first draft. So we have the answer, we have, everything except for the, the references, right? And you can imagine that that is going to be sent to the tool execution. So the next thing you can imagine is going to have the tool message. So if I come down here, you can see that this is going to have the tool message, right? So the name, the phrase, the search term, and then we have the URL and the content. Again, the search term, URL and the content, right? So we have this entire thing right here. And then going down, so what's the next thing? Right after the tool message, we have to send that to the Revisor chain, right? So again, there is going to be the AI message, but this time we will have the references as well, along with the the numbers, okay, the numbers in the content as well. So if I scroll down, you can see that we have the numbers 1, 2, and then at the very end we have the references as well, right? Along with that we have the search queries, and we are looping through it one more time, right? So again it's going to go to the tool, right? So we have the tool right here. Again it's going to fetch, make the internet search, it's going to pull it, and then again it is going to feed the entire conversation history back into the Revisor agent. Okay, so we have a tool message, and then another AI message, and then another tool message. Okay, so totally now we have 3 different tool messages in our list, and right now because it's 3, it is not going to loop through it again, it's going to end it. So that is why we have the final AI message right here, and this is exactly what we need. This is such an enriched blog post. You can see that small business can leverage AI to grow by enhancing customer service, optimizing operations. We have all the references here as well, where exactly it took the data from. So you can actually copy one of these things. These are like properly legit, right? It pull these in real time. So you can actually search for this thing, and you can see that it basically pulled everything from this particular blog post, and it does the same thing for a lot of other things as well. And again, there is going to be search queries, but since we are stopping the looping right here, we're stopping the graph, it is then going to exit out of the graph. So this is going to be the final thing that we want. Okay, so please do go through each and every single one if you don't, if you're not able to understand it. And if at all you have any questions at all, please feel free to ask me in the comments, or Claude, I believe, is going to be very helpful to you as well. ChatGPT is going to be very helpful to you. So that is it for the Reflexion agent system. I hope you learned a lot of things about how to parse, how to ground the response of the LLM, how to parse it, how to put it all together in a graph. And I'm hoping that you are able to see how you can actually customize these systems based on your own use case, right? So the goal is not to just copy it, but rather to understand the fundamentals so that you can actually build out your own systems, right? So I just wanted to end this particular section with the disadvantages and the advantages of the Reflexion system. So you can imagine that if your product or if your company, the customers don't really care about speed as much, then please go for the Reflexion system, because the data is going to be grounded in live data, and also the improved quality compared to the Reflexion system that we saw in the previous section. Okay, so I hope that you learned a lot. I'll see you in the next section. Hello guys, welcome to the section. In this section, we are going to deep dive into state in LangGraph. Okay, so why do I want to do that? So far in the previous sections that we've seen, we have used the message graph, right? It's basically just a list of messages. But in the future, if you build complex applications, complex graphs, complex systems, you might want to keep track of multiple other properties. You don't really want to restrict yourself to just a list of messages, right? So in that case, you might want to you would have to learn about StateGraph. Okay, so that is what I've planned. In the next section, we will look at how to build out the React agent system using LangGraph. That is going to be a little bit more challenging because there's going to be a lot more properties that you will want to keep track of in the state. But before we do all of that, I want us to just focus on state in LangGraph, thoroughly familiarize ourselves with state in LangGraph, and then once we are confident, we'll move on to the next section. So let us look at some slides. State in LangGraph is a way to maintain and track information as an AI system processes data, right? So think of it as the system's memory, allowing it to remember and update information as it moves through different stages of a workflow or graph. So here are some concepts that we are going to be covering. So we will first look at what is StateGraph, what are some basic state structures, and then we will progress to a bit more complicated state structures. And then we will see what are the different ways to update that state. So there is a manual state transformation that we can do, and we can also do a declarative annotated state transformation. So I'm going to go back to VS Code, and you can see that I've already created a folder right here called state deep dive. I'm going to create a new file called, let's say, the first thing I want to start off with something very simple. So I am going to call it basic state.py. So let me show you a simple graph that we are going to be building. So this is what I've planned to explain this. So all that we're doing here, this is a simple counter. Okay, so this is going to be the state, which is just going to have one property called count. Initial value is going to be 0. Okay, so we have the start node, and as soon as the increment node is hit, the count is going to be made to 1. Okay, so once it is made to 1, it is going to go to the should continue method. So this should continue method is going to have a condition. We can set whatever condition that we want, but I'm going to set the upper limit to 5. Okay, so basically I'm saying, okay, keep on incrementing it until 5 is reached. And as soon as 5 is reached, go to the end. Okay, so by doing this, we are going to be able to see how we can actually maintain a state like this. So far we've only seen message graph, which is going to be a list of messages, and we weren't really able to build custom states with that, but right now we are going to learn how to do that. So let's come back. So the first thing that I'm going to do is I'm going to define the blueprint for our dictionary, for our object. Okay, so blueprint as in, okay, this is going to be the name of the property, and this is going to be int, which is going to be the data type of that particular property. So to do that, I can just say class, and I can call it whatever I want. I can call it simple state or something like that. All right. And now we have to import from type dict. Okay. So I can just say from typing import type dict. Okay. So I can actually look at, we can see that type dict creates a dictionary type such that a type checker will expect all instances to have a certain set of keys and the consistent typing as well. So basically it enforces something like this. So here we're saying that, this should be a count and this should be an integer. Okay. So whatever object or dictionary that we are going to be dealing with in the graph, it is going to have this particular structure. So that is what it means. Now let's come back. So let's actually go ahead and build out this particular node right here. So we are going to be following the same structure. We are going to build out each of these nodes, and then we are going to connect it together using StateGraph this time, not message graph. All right. All right. So I can just, let's just keep it very simple. Let's call it increment. Okay. This is going to be the node, and this is again going to get the state. If you remember, every node in a graph is going to get that input. Okay, so since we are going to be dealing with state graph, it is going to get the entire dictionary with this particular structure. Okay, so we can just call it a simple state, and this node is again going to return the same simple state with modified values. That's it. All right. So basically what this is going to do is this is going to return another object, the same object. Whatever this is returning is going to replace the existing global state. So we can say something like count. So this needs to be in strings. So we can say state count, and then we just need to increment it by 1. Okay, so that is how simple it is. So you can see that this is a very important learning. Okay, so any node, every single node is going to get the same state. If it is a message graph, if we are using a message graph, here we will get a list of messages. But since we are going to be dealing with state graph, I will initialize it later. But since we are going to be dealing with state graph, we are going to get a dictionary with this particular property called count. All right, perfect. So what is the next thing that we have to do? So let's come back and let's actually go ahead and build out the should continue node. So I can just say should continue, and this is again going to receive the entire state. And let's actually write the condition right here. So I can just say if state count is less than 5, okay? So if state count is less than 5, we want this control flow to go back to increment, right? So I'm going to say return, and I can say continue, okay? And if this is not the case, then we can return the end right here. Okay, so let's actually go ahead and import from LangGraph.graph end. Perfect. Actually, you know what? I don't really want to use end either. I'm just going to say something like stop. Okay, so I want us to discuss about something else that is also possible. Okay, so I'm going to keep it very pure, this function. I'm going to say continue and stop. Okay, all right. Now that we have this node as well as this node done, let's actually go ahead and create the graph, and let's add these nodes to the graph, and then let's do the conditional edges as well. So to do this, now I'm going to say graph equals state graph. Okay, I'm not going to be using the message graph this time. So let's actually go ahead and import the state graph right here. And in the state graph, we have to provide the blueprint that this state graph needs to create for the object, for the dictionary. So we have the blueprint right here. So let's actually go ahead and provide that. Perfect. So now let's go ahead and add the nodes right here. Okay, so the first node is going to have increment as the name, and then let's pass in the method as well. All right, perfect. So what is next? So now we need to add a conditional edge, right? It can either go here or it can go to the end as well. So let's say graph.add conditional edge, and we're saying that as soon as the increment is done, go to this should continue method. So this is going to do this thing. All right. So let's actually, I'm going to do something here. Okay. So it is going to go to the should continue. So, but here, we're calling it continue and stop. We're not really calling it increment and end, right? So we can also do something like this. So this takes in a third argument. So in this argument, this is a method, this is an object. And inside of here, I can just say, if this should continue returns continue, then it means that you need to go to increment. Okay, so this is what it means. If it is continue, you need to go to increment. If it is, what's the next one? If it is stop, we can go to end. Okay, so I just wanted to add it here because I wanted to provide a bit more syntax exposure for you. But if you don't want to, deal with something like this, you can just go for, saying end right here and saying increment right here and removing this. Okay, so this also should work. So let's actually, go back. This looks perfect. So far we've added the node, we've added the conditional edge as well. And then finally, we just need to add the entry point, right? So we can just say graph.set entry point, and that is going to be the increment node. And now finally, let us go ahead and compile this graph as well. So I can call it app, compile, and then finally we can invoke it. And right now we are going to provide a dictionary. Okay, so the initial state is what we need to provide right here. Okay, so we can just put it separately as well. The initial state is going to have a count of 0, right? So that is something that we can provide in this state right here. All right, perfect. So initially it is going to be 0, and this is going to return the result. We can go ahead and print the result as well. So if I run this file, perfect. You can see that we get count is equal to 5. Okay, so all this other additional, logs that you're seeing, warnings and all, this has to do with LangSmith. Let's not worry about it right now. But right here, you can see that the count has been incremented to 5. So you can imagine that what happened is that it first went to increment, and then it looped 5 different times, and then finally the should continue directed it to the end. But the main takeaway from this particular section is that instead of having a list of messages, we can now define pretty much our own custom state, anything that we want. So in this case, we went with count. Okay, so all that we did was we defined the blueprint. We defined the blueprint right here using the type dict, and then all that we're doing is providing it in the state graph. Okay, so now every single node right here is going to have access to the entire object, the entire dictionary that the state graph is going to create using the same schema, using the same blueprint that we specify right here. So in conclusion, you can actually imagine this state, this object, to be like a global state that is available for all of these nodes to modify, update, right? So if you're a front-end developer, if you're a React developer and you've worked with Redux, let's say, it is kind of very similar to it, right? All right. So very similar to Redux as well. There, we don't mutate any of the values. We actually create a new object and then we update, right? So that is called immutability. And that is exactly what we are going to follow in LangGraph as well. So you can see that here we are actually creating a new object and then we are merging it with the existing object. Okay, so perfect. So in the next section, we are going to increase the complexity just a little bit. We are going to be adding, a second property to the global state, or maybe even a third property. Okay, I'll see you in the next section. All right, guys. So in this section, let's actually, let's go ahead and create another file, and let's call it, let's say, complex state. Complex state.py. Okay, I'm just going to copy paste everything right here, whatever we did in the previous section. So I want to add another property to this blueprint, and basically what I want to do is I want to keep track of the sum of whatever count that the system goes through. Okay, so initially the sum is going to be 0. So let's actually go ahead and put that down here as well. So the initial state, the count, the sum is going to be 0. And so in this particular node right here, so if the sum is going to be 0 and the count increases to 1, the sum is going to be 1. So right now the sum is going to be 1. And if the count were to be increased to 2, then it's going to be 1 plus 2, then the sum is going to be 3. Okay, so you can imagine that if there's 5 more iterations, the sum is going to be 15. So let's actually go ahead and implement it. So in addition to changing the count property in the state, I'm now also going to update the sum property. Okay, so how can I do it? So in this object that I'm returning, I'm also going to update the state. So first off, I need to get the latest sum value, and then I also have to, get the next count value and then add it to the existing sum. Okay, so since we're repeating it, I can just go ahead and say new count, and then I can just move this outside. Okay, so I can also do something like this, and this should work perfectly fine. All right, so let me go ahead and quickly run this as well. All right. Okay, so coming up, you can see that we have count as 5 and sum as 15. So you can imagine that we can add as many properties as we want, and this is the whole point of a custom state. It is completely in our control, right? Perfect. Let's also do another thing. Let's also have a history. Basically, I just want to keep track of, what are the different counts that we've encountered, and I want it to be in a list format, right? So in this case, I can just say it should be a list of ints. So for the list, I can just go here to typing and then, get the list as well right here. Okay, so I can do the same thing. So initially coming down in the initial state, we want the history to be an empty list right here. And now I get access to the history everywhere. So, I can easily get it from here, and then I can update the history as well. So the new history value, we want it to be, we want the latest count to be appended to the list, right? So state history, right? So state.history is going to be an empty array, because if we come down here, that is what we've said right here. Okay, this needs to be an empty array, and we can actually, append two arrays together by using the plus operator. Okay, so we can actually put whatever things that we want here, and then two lists are going to get merged together. So what do we want right here? We wanted the new count again. All right, perfect. So let's actually give this a whirl as well. And if I run it, you can see that. Don't worry about these things, but you can see that we have the count as 5, sum as 15, history as 1, 2, 3, 4, 5. Okay, so that is how simple it is to manually update the state. Okay, so in this section, basically how we've updated the state is that we have updated it using the manual method. Okay, so we're doing all of the calculations right here, and then we are updating it manually. But there is another way of doing it using annotation as well, and that is something that we'll be covering in the next section. Hello guys. So in the previous section, we looked at the manual state transformation, which is where we are basically updating the state inside of the node, and we're doing all of the calculations inside of that particular node. But there is slightly a different way to do it as well. So that is called the declarative annotated state transformation. It is not going to be as daunting as it sounds. So let's actually look at what it is used for. Okay, so in the manual way, we are just dealing with one node right here, and let's say, we are calculating the sum, right? So this is going to be the operation, right? But let's say there's like a 4 or 5 or 100 different, nodes that do the same, summing operation. So you can see that this is going to get repeated a lot, right? So basically, just to cut down on that, there is a slightly more, better way of doing it, and that is through annotation. So I'll show you what that means. So I can just say annotated, and right here we can actually, provide LangGraph, basically give it some metadata and tell it how to update the state in the future. So I can say annotated. Okay, so this thing is going to be the type. Okay, and then in the second option, we can actually provide it how to update the state in the future. So right now what we're doing is we're just summing it, right? So we are taking the previous value, and then we're adding it with this new computed value, right? So all that we have to do is we can just say operator.add. Okay, so we don't really have the operator, so I'm just going to say operator. So now that we've added it here, we can actually go ahead and remove this part. Okay, so essentially what we're saying is this annotated, this thing is going to keep track of the previous value, and then anytime there is a new value that is going to be returned in the place of this property. Okay, so anytime that is being returned, add this to the existing value, and that is what this particular method means. Okay, let's try to do the same thing for history as well. So we have the previous value right here. We don't really want to keep on repeating for other nodes as well. So in that case, we can remove this, and we can actually say annotated. Okay, so annotated. So again, this is still going to be a list, but if there is an existing list that is being maintained, and if there is a new list that is being added, how do we update it? We have to concatenate it now, right? We have to merge it. So we can just say operator dot concat. Okay, so you can see that it provides a bunch of different methods. You can see that call, we've got a lot of different methods. So in this case, I'm just going to use concat. All right, and that is it. So if I were to run this, you should be able to see the same exact thing, no different. So this would have slightly simplified your code a little bit, right? So you can see that, this is a lot more clearer now. And then all the, the actual, intelligence as to how to update the state is maintained here, okay, in this particular annotated, and we're using the operator. So there might be some, some operations that might not actually be available in the operator. In that case, you might have to do it manually right here. But yeah, this is always available for you to use. And the reason why I wanted to cover all of these different patterns is because, we will be using some of this in the next section, where we are going to be building our very own React agent that we saw in the start of the course, and we are going to be building it using LangGraph, and that is going to give you a much more deeper insight as to how things work, and also that is going to give us a lot more flexibility. Okay, so using LangChain's classes, we don't really have a lot of control, infinite loop problems. But if we have the control with us, if we build it using LangGraph, that is going to give us a lot of control, and we eliminate some of the drawbacks of using the LangChain's default classes. So I'll see you in the next section. Hello guys, welcome to another brand new section. In this section, we are going to be building the React agent using LangGraph. Okay, so in the previous section, we learned everything there is to know about state in LangGraph, how to use custom state. So we are going to be employing all of that to build out our React agent. So I know that we did, implement the React agent using LangChain's, out of the box classes like initialize agent method and agent executor classes. But in this, section, we are going to eliminate, the agent executor, and we are going to have full control over the looping that happens between the LLM and LangChain, between LLM and LangChain. We are going to have full control because this time we are going to be using our graph data structure. We are going to be using LangGraph. So before we proceed forward, let's quickly jog your memory about, what is the React agent, what pattern does it follow. So if you remember this particular slide, so you can see that, the LLM first thinks, let's say you're giving the LLM a problem to solve. It first thinks about the user's prompt or the problem, and then we have action. The LLM decides if it can answer by itself or if it should use a tool. So once it decides, once it makes that decision, it is then, if it decides that it is going to use a tool, the action input is going to be the LLM provides the input arguments for the tool, right? So once the input argument is provided, LangChain's, out of the box class, it just like stops, the streaming of the LLM. It tells the LLM shut up. It just basically takes the think action input. It is then going to call the tool, execute the tool, get the response, and with all the entire history, it is again going to send it back to the LLM. And now the LLM is going to observe the result of the tool, and if the entire problem is solved at that particular point, this is the final answer, or else the same loop is going to continue. So the problem that we faced was that we did not really have control over that default class that LangChain provided for running the React agent, right? Because sometimes we went into the infinite loop problem. We do not have the control to ourselves, right? So that is exactly what we're going to be solving using LangGraph. Okay, so before we actually start implementing LangGraph, let's actually take a quick peek into this method. Okay, so let me actually come back to the first introduction where we built out the React agent. So here you can see that we've used the initialize agent method. Okay, so let's actually take a quick peek into what is exactly happening. What are the components that sort of come together to build out the React agent? Okay, so that is what I've written here. So in LangChain, we use the initialize agent as an all-in-one solution, right? So that is exactly what we've used right here. It basically just takes in the tool, the LLM, the prompt as well, the React prompt. We're telling the method use the React prompt. Inside of it, the React prompt would have been written, and then we are setting the verbose to true as well, right? So this is what we're using as an all-in-one solution. But it combines two key components. So the first one is going to be the create React agent method. Okay, just on a very high level, think that this is a method that does one thing, and then along with that, we also have the agent executor class. Okay, so this is exactly what we are going to eliminate for LangGraph. Okay, so this is what actually controls the looping between LangChain and LLM. This looping is being done by agent executor, and that is exactly what we are going to be replacing using LangGraph. All right. So create React agent. So what is it? So you can basically think of this method to be that method that creates the agent. Obviously, everything's got to come together to create the agent, including the looping. But for now, just think that this is what is going to create the agent. So what does it do? It just takes each tool's name and description. Okay. So you can imagine that we would have provided a few tools to solve that problem, right? So let's come back to the code. We see that we have the search tool right here. We have the get system tool right here. And this entire tools is provided to this particular method, right? So let's see what it does. So it basically takes each tool's name and description. Okay, so we have the name right here and we have the description right here. Okay, all these things are not going to be taken at all. These things are not going to be considered at all. Just these two things are going to be taken. And then it formats them into a standardized way the LLM can understand. Okay, so basically it's going to convert it into a string, and then it inserts them into specific placeholders in the React prompt template. Okay, so let's quickly look at the React prompt template. So here you can see that we have a placeholder for tools, and then we have a placeholder for tool names, right? So that is exactly what this method is going to do. It is basically just going to take the name and description of various tools. It's going to structure it, it's going to parse it, it's going to make it into a proper string, and then it is going to combine it with the React prompt template, so that when we send it to the LLM is going to have full context about what are the tools that it can work with. All right, so not just that, okay, it doesn't just do the merging, it also makes the LLM call, and okay, it makes the LLM call. So the LLM is now going to proceed forward with generating, what is this? It is going to start generating the question, thought, action input. Okay, so these four things it is going to start generating, and the minute the action input is received and the minute we actually start going to this observation, okay, so the minute this is coming to an end, the streaming that happens between this particular method, and the LLM, that is interrupted. Okay, so we don't really want what happens after that. Okay, we don't want the LLM to continue, because the LLM is not going to have the result of the tool, right? So what I mean by this is, up until this point, the LLM needs to generate the action input. As soon as the action input is received, the LLM is going to stop it. Okay, this particular method is going to tell LLM to stop streaming. Okay, your work is done. I now have the action input. It's going to get that action input. Okay, so that is what it does. It makes the LLM call. It takes the LLM's response, and then it parses it. Okay, so this is an example, let's say. Okay, so first off, the LLM is like, thought, action input. The thought could be, I need to find out when SpaceX's last launch was and calculate the days since. Okay, so if you remember that this was the first prompt, the problem that we provided to the LLM, right? So it is first thinking to itself, and then the LLM is deciding I want to use the search tool, and then it is also providing the input to the Tavily search tool. Okay, so let's say this is up until this point, this method is going to allow the LLM to generate, and as soon as this is done and the observation is started, cut, and then the data is going to come back to this particular method. And finally, once it has these three things right here, it is going to parse the response of the LLM into one of these two classes. Okay, so this method is just going to return two things. It is either going to return the agent action class or the agent finish class. So let's actually look at what this agent action and agent finish looks like. So this is a LangChain class that represents an action the agent wants to take. It typically contains something like this. So this is how the complete, parsed output is going to look like. It's going to be an agent action class. It is going to have the tool input, and log. The tool is going to be what tool to use, the input to the tool, and then why the LLM thinks that it needs to use this tool. So this three data is essentially what these three things are going to contain. The thought is the reasoning, and that is exactly what is going to be put in the log. And the action is going to be which tool to take. That is exactly what is going to be converted into this tool input. And then finally we have the action input, and that is going to be this tool input. Okay, so it just like parses it and creates this particular class, agent action class. Okay, I really hope that makes sense. So in case that the LLM is actually does not need to call another tool, it thinks that I don't really need to call a tool, my answer is done, my work is done, I have all the information that I need, I have the final answer. In that case, this particular method, the create react agent method, is going to return the agent finish class. So this represents the agent completing its task with a final answer. It typically contains, this is going to be the output, and this is the log as well. Okay, so now I really hope that you understand what the first key component of React agent does. So this is going to be 50% of the work that is done by this initialized agent method. Okay, so let's look at the second key component of this initialize agent method, and that is going to be the agent executor. So let's see what it does. It takes the agent from create react agent, okay, and then manages the execution loop. So you can imagine that, the create react agent method is going to output parse the agent action and the agent finish, but something's got to control the looping between the LangChain class as well as the LLM, right? So after the LLM is done, the control needs to come back to the LangChain. LangChain's got to parse it. It's going to call the tool, and as soon as the tool is called, again all of the data needs to be sent back to the LLM along with the history. So all of that looping is being done by the agent executor. I hope that makes sense. So it basically takes the agent that is created from the create react agent method and manages the execution loop. It receives the user's question and feeds it to the agent. Okay, and then it identifies which tool to run based on the agent's output, agent action, or if it is no tool required, then agent finish. So it executes the tool and captures the result, feeds the result back to the agent for the next decision. It continues this loop until the agent produces an agent finish class, returns the final answer then to the user. Okay, so to put it very short, agent executor is what is actually going to be controlling the looping between the our system as well as the LLM. So this is where we actually lost control a little bit because of the infinite looping problem. So if I actually go back and go inside of the initialize agent, you can see that it is actually returning the agent executor. Okay, so this is why this is not really in our control at all. Okay, so if we mess up with the prompt, or we mess up, if we don't provide a tool or anything, then it's going to malfunction, and we don't really want that. So this is exactly where there is a drawback, and this is what we are going to replace, or rather eliminate, using LangGraph. So we are going to gain control of the looping. So let's actually look at some of the key advantages of using LangGraph. So LangGraph basically turns the hidden black box loop into a visible, editable workflow. So you can now add custom nodes, modify the flow, insert additional logic. So this is going to be the LangGraph graph for the React agent. And then we have the reason node and the acting node. So together is what is React, right? Reasoning plus acting. So let's actually look at what this graph means. So the reason node does what create React agent did. It thinks and decides. If the reason node outputs an agent action, then act node executes the tool. The results from the tool flow back to reason node for the next decision. When the agent has the final answer, it takes the right path to end. This visualization makes the black box of agent executor transparent and modifiable. So I really hope that this introduction makes sense. If it does not, don't worry. We are going to be, dissecting it, and we are going to be looking at it in much more depth. But yeah, in the next section, we are going to be looking at how we can build out the reason node right here. So I'll see you in the next section. Hello guys. So in this section, let's go ahead and build out the chain or the runnable that is required to build out the reason node, which is very similar to what we did in the Reflexion systems as well, right? So I'm just going to go ahead and first create a folder. Let's call it React agent. And then I'm going to call this let's say agent reason runnable. All right. So let's think about what we need right here. So all that we need is to, provide all of the properties that the create React agent method is going to need. So let me go ahead and paste a few imports right here. Pretty standard stuff. We have the OpenAI chat model. This is the method that we are going to be using, the create React agent, the Tavily tool, and we have the LLM as well. So what is the next thing that we need? So we can just go back to the first section. And then let's see what we did right here. So we're still going to need the same tools that we have to provide, right? So we have the get system time tool. Basically, I'm going to replicate the same example that we saw. We don't want to reinvent the wheel because we're just learning, right? So I'm just going to copy, everything right here, including the search tool as well as the get system time tool. So let me come back, put it over here. Perfect. And finally, we are going to use this particular create react agent method. And let's look at what are the things that it needs. So first thing is it requires the tools, and then it requires the LLM as well. And then it requires the prompt. Okay, so the prompt that we need to provide is going to be the React prompt. Okay, so for that, I can just go to, hub. Okay, so I can just say React prompt. Okay, this is going to be the React prompt template. I can just say hub dot. Okay, let me just go ahead and paste it. Yeah. So this is going to basically pull the React prompt from the HWChase17 LangChain, the website. Perfect. So let's actually go ahead and provide this here as well. Okay, great. So looks like this method has been provided everything that it needs. So this method is going to return a runnable, which is going to do all of those things that we saw in the slides before, right? So if I go in here, you can see that this is going to return a runnable. So we can call this the React agent runnable, let's say. Okay, perfect. All right, guys. So we have created the runnable, the reasoning runnable. In the next section, we are going to, build out the state that we need to build out the system. So in the previous section, we looked at the custom state, and we can actually put in pretty much any property that we want to achieve this particular system. So for the React, we are going to need a few, we are going to think about what are the states that we need. So we'll look at that in the next section. Alright guys, so in this section, let us look at what are the state properties that we need to achieve this React agent system. So you can see that I've already gone ahead and created a file called react state.py, and I've imported a few things like the operator. I'm pretty sure that you know what operator is by now. We have the annotated class, we have the type dict, and then we have the union. Okay, we'll talk about what these things mean. Alright, so this is going to be the agent state. We can call it anything that we want, but I'm just going to call it agent state or React agent state. We're importing the type dict, and these are the three properties that we need to achieve. These are the three state properties that we need to actually achieve this particular system. So the first one is going to be very simple. The first one is going to be the human message, the initial human problem. Okay, so for example, my problem initially was I wanted to, this was my prompt, right? So this is going to sit right here, and initially we're just going to put it right here, and it is going to stay for the rest of the process. All right. So next thing is going to be the agent outcome, and then we have the intermediate steps as well. So let's look at what this agent outcome is. So this agent outcome, if you remember, is exactly what this runnable is going to output. So if you remember this runnable, so if I go in here, you can see that this runnable is going to return either an agent action or the agent finish. So I can actually search for agent action. So you can see that it returns a runnable sequence representing an agent. It takes as input all the same input variables as the prompt passed in does. It returns the output either as agent action or agent finish, right? So this output is going to be put in right here. Okay. So initially it is going to be none, but once the LLM wants to use a particular tool, after the parsing, this agent action can sit here or the agent finish can sit here. Okay, so the union is basically like, it can either be this, or it can either be this, or it can either be this. That is what this means. But yeah, initially it is going to be none. And next we have the intermediate steps, and this is basically just to keep track of the entire history of all the existing problems that have been solved. We don't want the LLM to keep on solving the same problems again, right? So if there is a small part of the problem that's been solved already, we save it and then we keep it right here as a list of tuples. Okay, so anytime there is a new tool call and the output of the tool call is done, we're just going to add it to the existing list. So if this does not make sense to you, don't worry. I actually have sought the help of Claude. I've just like told it exactly, how basically I've told it, okay, I want you to give me the exact sequence of how the state changes as the looping happens in the right sequence. So this is exactly how it's going to go, guys. Okay, so initially when the application starts with app.invoke, okay, so let's say this is going to be the initial human prompt, right? So initially the agent outcome is going to be none, and then the intermediate steps initially is going to be an empty array as well. Okay, so in the first iteration, Okay, the flow starts at the entry point, right? So if you come back to the graph, so this is going to be the reason node, the entry point, right? So what this is going to do, this is going to it's going to call the method. This is going to sit inside of the create react agent. Don't worry about it. But yeah, this is going to process the input and it is going to parse and generate the agent action for the search tool, right? So this is going to be the updated state. So as soon as the React node is done executing, it is going to return the agent action. So that agent action is going to sit inside. We are going to update the state and put it in the agent action, the agent outcome property. So this agent action is going to have the tool, this tool to use, tool input, this is going to be the search term and then the log. Okay. So right here, this is going to return it. And now we are going to put the data in the agent outcome. So what is the next step? We need to send it to the act node. The act node is what is going to actually execute the tool. So now it has all the data. It knows exactly, what tool to use, what should be the input to the particular tool, right? It has all that information. So what's going to happen next? The conditional edge is going to happen. Okay, it's either going to go to the act node or the end node. So it sees the agent action. It is not agent finish. It sees the agent action. So it is sending it to the act node. We'll actually build all of this later in the graph, but it is going to send it to the act node, and then the execute tools. The tools are going to be executed. And then as soon as the tools are executed, the intermediate steps is going to get populated. Okay, so we have in the tuple, so this is going to be the first tuple in the list. In this tuple, in the first part, we are going to have the agent action that was generated before, and also we have the output. Okay, so we have the output of the tool execution. Okay, here it is going to, all the output of the, the search results is going to sit right here. So this is going to be the intermediate steps. Perfect. So as soon as this is done, the tool execution is done. What happens? So as soon as the tool execution is done, we are going to send all of that information back. The control flow is going to go back to the reason node, and then all that history is going to be again sent back to the LLM in that agent scratchpad. So now it has solved a particular problem. One problem it has solved. Now it needs to solve the next problem. And for that, it might use a different tool, right? So we have the second iteration, and then we have the agent reason node again. Okay, it's going to get updated. Now get system time needs to be called, not the other tabuli search. So this time, okay, the same thing happens. The act node is going to execute the get system time tool, and then it is going to append it. And then the final LLM call is going to happen in the agent reason node. Right? So this is going to be the updated state. And then finally, what happens? The agent finish is going to be, outputted by the reason node. And that, so what happens? The agent finish is going to come right here, and it's not going to go to the act node, but instead it is going to the end node. Okay, so this is exactly why we need these three different properties. So don't worry about how this is all coming together right now. But for now, just know that these are the three properties and why we actually need those three properties. Okay, so that is what I want you to take away from this. Okay, so in the next section, we are going to be building out the nodes. Okay, so this node and this node, we are going to be building it out. So I'll see you in the next section. Hello guys. So in the previous section, we built out the runnable that this reason node is going to depend on. In this section, let's actually go out and build these nodes. Okay, so you can see that I've already gone ahead and I've created this file called nodes.py, and we have the reason node as well as the act node right here. So let me take you through it step by step. So right here, you can see that we are going to use the React agent runnable that we wrote in the previous section. And all that we are going to do is we are going to invoke on it using the agent state. Okay, so all the values, these things that we see right here, these are reserved keywords, and this runnable is going to know exactly what to do with those particular names. So don't change anything. So you will have to follow the exact input agent underscore outcome intermediate steps. Okay, everything's got to be perfect. And now this runnable is going to look at the state. It's going to take all of the properties, merge it with the React prompt, and then it's going to do all of that magic, including calling that LLM and then parsing the output of the LLM and then having that particular agent outcome. If you remember what is going to be the agent outcome, this thing is going to return the agent action class or the agent finish class, right? So here we are going to update the agent outcome, right? So right here, we have the agent outcome that is going to be an agent action or the finish. So as soon as this node is executed, it is either going to have agent action or agent finish. Only during the first initial, instance, it is going to be none. But after that, it is always going to be action or finish. All right. So let's come back to the graph. So now let's assume that it is going to be agent action. Now it is going to come to the act node, right? So act node, we are going to again basically extract what is that agent action that needs to be done. And now we've written the tool executor here as well, right? So here we are providing the tools and we have the tool executor. All that we're doing is we're invoking that, we're providing that agent action. And then whatever output that we're getting, we are going to be appending it to the intermediate steps. Okay, so if you remember, the intermediate steps is going to be a list of tuples. Each tuple in the first part, it is going to have that agent action or the agent finish. And again, it is going to have the output of that particular tool execution, right? So in this case, the output is going to be here. We are stringifying it and then we are putting it here. And whatever we return here in this array, in this list, it is going to be merged with the existing intermediate steps list. Why is that? That is because if you come back to the state, we are using the operator .add. Okay, so now I hope that you see that everything is coming together, right? Perfect. So now we have the reason node as well as the act node. So the next step is going to be very simple and fun, to be honest, because all that we're going to be doing is putting it all together in a graph and drawing these edges and then running it. So we will build out the graph in the next section. So I'll see you there. Hello guys, I'm from the future. I had to rewrite the act node alone because in the latest version, LangGraph version 3, the tool executor class that we had used inside of the act node, that has been deprecated. It does not exist anymore. So we are going to do it without using any of these methods. Okay, without using the tool executor class. Okay, so it's going to be very simple. So this line we've already written. The only change that we are going to do is without using that tool executor, we have to invoke the right tool. Okay, so if I come back here, okay, so we already have the list of tools that we have available. I'm just going to take it right here. Okay, so we have this available. So from the agent action, all that I'm doing is I'm going to take the tool name and then I'm going to take the input. Okay, so we can easily extract that information from the agent action. So this is going to be step 1. Okay, so from step 1, we are getting information about which exact tool the LLM wants to call. Okay, so the LLM might want to call get system time or it might want to call the search tool. Okay, so we have both of that information right now. The next step here is to basically get access to whichever tool that we need at that particular moment. So I'm saying I'm basically just looping through the tools and I'm checking, okay, which tool name matches with the tool name that the LLM wants to call. And I'm finally getting the tool function, getting access to the tool function. Okay, so I'm basically getting a reference to this or this. Okay, so that is it. So once I get a reference to either this or this that I want in the act node, I can then invoke it. That is it. Very simple. We don't need tool executor in this case at all. Okay, so once we have that particular tool, I'm just going to invoke on it right here. Okay, so why do we have this if else? Very simple. If we are dealing with get system time and we have like another few these things, A, B, whatever, in that case, we will have to spread it out. If not, we don't have to spread it out. Okay, so that is what I have done here. Okay, and then finally, we are going to get the output and then we are going to add it here. Okay, so it's a very simple alternative. Also, I don't really want to keep on relying on these, LangChain classes that they're providing for two reasons. One thing is we are not learning, exactly how to do it without these classes because they introduce breaking changes, especially in production. We keep on having to change code, which I don't really like. So yeah, this is a much more simpler way of doing it, and that is exactly why I wanted to I just wanted to make this particular section. So thank you. I'll see you in the next section. Hello guys, welcome to the final section in this topic where we are going to be putting together all these different nodes together to form the final React graph. All right, so you can see that I've already gone ahead and created a file called React graph and I've already populated the code as well. So let me walk you through it step by step what I've done. So I'm just doing a very standard import of all the nodes that we've written we have imported the agent state as well, the global state that we have written, right? And then we've also imported the state graph so that we can create the graph. And then just some classes like agent finish and agent action just to, type it basically, okay, force type it basically, right? All right. So let's actually go back to our graph. So the first thing that I'm doing is I'm basically just giving it a constant name for these nodes. So that is exactly what I've done here. So we have the reason node and the act node. Okay. So if I scroll down here, all that I'm doing is I'm creating a graph using StateGraph, and I'm providing the blueprint that we've created as well, right? If you remember, the blueprint is going to be, the input is going to be a string, agent outcome is going to be one of these three things, immediate steps is going to be a list of tuples, with each tuple having the agent action as the first part and the string as the output of the agent, the output of the tool execution as the second part, right? So coming back, and that is exactly what we're passing in here, and I'm creating a simple graph. All right. So first thing is I'm adding the the reason node and the act node. So you can see that I'm adding the reason node, I'm adding the act node, and I'm also setting the entry point to be the reason node. Okay. So I'm saying that right after the reason node is done executing, we want to basically check if this particular outcome, let's go back to the state, if this outcome has the agent action or the agent finish. So if agent action is present, then it means that we have to go to the act node. If agent finish is present, we just have to end it. So for that, we need a should continue method, and that is exactly what I've written here. So you can see that. So I'm saying that right after the agent node is done executing, I'm adding a conditional edge, and it is the control flow is going to the should continue method. So the should continue method, again, like every node in the graph, it is going to get the entire state as the input right here. Okay. So for now, I'm just going to look at the agent outcome, because that is what is going to contain the agent action or the agent finish. So I am checking in the state, is it an agent action or the agent finish? So I'm checking if the agent outcome is an instance of the agent finish. So if it is an agent finish, then the control flow needs to go to the end. Okay. But if it is not, then we have to go to the act node, which is down here. Okay. So for our prompt, it is going to go to the act node, right? So that is exactly what's happening here. And I'm also adding an edge between the act node and the reason node, right? So right after the act node, it should always come back to the reason node, right? And that is exactly what I've added here. That is it. Okay. So nothing out of the ordinary. All of this is something that we are already familiar with. Okay. And finally, we are going to compile the app, and then we are going to invoke the app using the initial state. Okay. So right now, going back to the state, we are just providing the input, right? How many days ago was the latest SpaceX launch? So we've provided the input. It is always very good practice to provide the initial state for everything else. So I'm just going to, put the, okay, what's happening? Okay. So I'm just going to put the agent outcome to none, which is going to be the initial state. Initially, the LLM hasn't suggested anything. And then we have the intermediate steps, and that is going to be an empty list. All right. And finally, I'm just going to print out the final state right after the end node is reached. All right. And then I'm also going to print out something inside of the agent outcome. We'll be able to see why we are doing that, once we look at this particular result. So let me actually go ahead and run this while. Let's give it a few seconds. Okay. So perfect. You can actually see that we are getting the entire state right here. So we have the input, and this input is what I provided right here, right? So this is going to be the input, and then we have the agent outcome, which is going to have the agent finish. So if you remember, only because we have the agent finish did the control flow even come to the end node, right? So that is why it is ending the cycle, and then we are getting the result. So in the agent finish, in the return values, you can see that the latest SpaceX launch was 2 days ago. Okay, so this is going to be the final answer. Okay, so how we actually got to this point, we will actually look at the LangSmith logs, right? But for now, you can see that this is going to be, this is going to be the final answer. So you can see that this is how it actually arrived at this answer. So today is March 7th, 2025, which is true. It is March 7th, 2025. It was able to call my, get system time tool that I provided. So the latest SpaceX launch was 2 days ago, right? And then we also have all of the intermediate steps that it went through as well. So we don't really even have to go to LangSmith. So you can see that in the intermediate steps, first thing is there was an agent action. The LLM suggested that we use the Tavili search results tool, and then this was the input, and then this was the reasoning behind using that tool by the LLM. Okay, and then we have basically the same thing happened a couple of different times, and then finally I'm just going inside of the agent outcome, I'm going inside of the return values, and I'm printing the final result. So this is going to be the final output. The latest SpaceX launch was 2 days ago. Okay, so if you have any problems understanding this code, simply just go ahead. I'm pushing all of this code to my GitHub repo. So just go there, pull it, and then, you can test it out right away. So in the next section, let us look at, the LangSmith tracing so that we can better understand it. Alright guys, so in this section, let us look at the LangSmith tracing so that we better understand what are the different steps that our system went through. So I ran it a couple of times, but let's just go to the latest one right here. So let's actually look at, you can see that this took a total of 13 seconds, right? So this is going to be the initial state, and this is going to be the final state that we already looked at in the terminal. So let's actually go through, what are the steps that happened to arrive at this final output. Okay, so initially you can imagine that this is going to be the initial state that we provide, and the control flow is going to go to the reason node. So let's click on this, and you can see that this took a total of 4 seconds, right? So this gets the entire state, and then this, you can imagine, is going to output the agent action or the agent finish. So the agent action is what the reason node is outputting. So it is suggesting, use this particular tool, put this particular tool input, and as soon as this is done, the control flow should go to the should continue method, and that should direct it to the act node. So let's actually look at if the should continue is coming. Yeah. So we have the should continue right here, and that is directing it again to the act node, right? So it is going to the act node. And yeah, so you can imagine that the act node is only going to take the outcome, the agent outcome, right? So it is only going to take the agent outcome, and then it is going to actually call the tool, right? And then it's going to take that output, and then it's going to append a tuple to the intermediate steps. And that is exactly what it is doing right here. So you can see that the first element of the first tuple is going to have the agent action and the tool input and all of that. And it is also going to execute this tool. So let me actually go back to our graph right here, or rather let's go to the nodes. So you can see that it is going to invoke that particular tool. It's going to take that output, and then it is going to, in the second element of the tuple, it is going to put the output as well. So that is exactly what is happening right here. So the first one is going to be the agent action, and then the second one is going to be the output of the agent action tool execution. So we have that entire, Tavili search call that is being made. So what is the next step again? So right after this is done, the control flow goes back to the reason node. So you can see that we have the reason node again right here, and then the same step sort of like continues, the same step continues, the act node comes, and then finally the should continue is going to get the agent finish. You can see that agent finish, and finally the output, the control flow is going to the end. And that is it for building a React agent using LangGraph. I hope that you're able to see what is possible with LangGraph, and these patterns you can sort of extend it to a lot of different use cases as well. So if at all you face any struggles at all, go ahead, pull my code. If you have any problems, even despite that, please do go ahead and ask me in the comments. I'll be more than happy to help you out. I'll be more than happy to connect with you on, let's say, LinkedIn even. So yeah, that's pretty much it, guys. In the next section, we are going to be looking at another aspect of LangGraph, and we are going to be looking at persistence. We are going to be looking at RAGs. I'm not really sure which one I'm going to be covering, but I'm pretty excited for what is ahead, and I'll see you in the next section. Hello guys, so I'm excited about this section. In this section, we will take on chatbots. We will look at incrementally, we'll sort of increase the difficulty, and we'll introduce more concepts. Okay, so these are what we'll be covering in the next few sections. So the first thing, we are going to be building a very basic chatbot. A basic chatbot, meaning it does not have any memories, it does not, it cannot make any internet searches or anything of that sort. You give it something, it spits out a response, right? We also have chatbot with tools. We're adding tools like, various tools in order to get accurate data. And then we will introduce memory. Okay, so persistence and memory, we will cover those concepts. And then we have the human in the loop concepts. We will cover that. That will build on top of whatever we learn in the memory. And then we have, chatbots with more complex state. We'll explore a little bit more use cases so that you understand, all the edge cases that are possible. And finally, we have time travel. So without wasting any more time, let's go ahead and build out a very basic chatbot. Hello guys, so this is what we are going to be building. So you can see that this node just has a start, and then we have this node called chatbot, and then we have an end. Okay, so basically you can think of this chatbot node as just a model, just an LLM that sort of like, takes in a human message from the start. I mean, when we invoke it, we pass the initial state, right? So yeah, it just takes in the initial state and then it passes it to the chatbot node, processes it, and then sends it and then ends the graph. That's it. Very simple. So this basic chatbot does not have any memory. It does not have any tools either, right? So these are some of the new things that we'll be learning. We'll learn about another method. So far we've been using the app.invoke method, right? We'll also learn about, there's another method called stream. We'll learn about that. We'll learn about, looping in the chat. And finally, we can also use a free Llama model using the Grok interface. Okay, so if you do not know, Llama is an LLM that is created by Facebook, and it is hosted in a service called Grok. Okay, so basically from my experience, I've seen that the response is much more faster compared to OpenAI's, and also it is free. So we'll definitely explore that as well. So without wasting any more time, let's jump back to our VS Code. So right here you can see that I've created a folder called Chatbot, and I've just named it as basic chatbot. Okay, so these are some very standard imports that I've done. The only thing that I've done differently is I've used the Grok chat model, which lets us access some of these Llama models. So if you want to know where I pulled this from, I can just go to chat Grok. Okay, that is going to be a chat model inside of LangChain. So I can just click on this thing. I think let me go to this particular class. And you can see that this is what we have to install. Okay, so just say pip install langchain -grok, and then we just need to set the API key, right? So this is going to be the name of the API key. You can set it by going to grok.com. Let's go to dev console, and then I think right here in the API keys, you can just go ahead and create an API. Okay, so that should be it. And I'm just going to load all of the environment variables. Okay, so we have all of this ready. Let us now go ahead and build out this very simple graph. So, so let's go ahead and build out, let's think about what we need in order to run this, right? So whenever we're talking about a chat bot, I mean, it needs some memory, and that memory is going to be a list of messages, right? So it needs to, it needs to be a list of, AI message, human message, system message, or whatever, right? We are not going to be doing anything different. It's all something that we've already done before. So I'm just going to go ahead and say something like, basic, let's say basic chat state. Okay, so I can use the type dict again. And here it's going to be messages. Okay, so this object is going to have one property, messages, and I can use the same annotated, and I can say this is going to be a list of messages. And then how are we going to, append a new message to the existing list? We can use, the concat operator that we've seen before, but LangGraph also provides this method called add messages. Okay, so if I hover over it, you can see that it merges two lists of messages, updating the existing messages by ID. So you can see that this is also something that we can use. Perfect. All right, this is all that we need for the state. Now let's go ahead and what's the next thing? Let's go ahead and build out this particular node right here. Okay, so I can call it chatbot, doesn't matter. I can use this basic chat state. This is what this is going to be the state, and this is going to be the type of it, right? So what do we need to do here? So all that we have to do is, we are going to get a list of messages from the start. In this case, it's going to be very simple. The list is just going to have one human message. It just needs to take that list and then invoke it in the LLM, right? So all that we have to do is let's return the this is going to be the structure of the state, right? So here all that we have to do is let's go into the state. Okay, this is going to have the messages inside of it. Okay, so how do we do it? So LLM dot invoke, and then we can pass the state right here. Okay, so I hope that makes sense. And whatever is the response is going to be an AI message, right? So we're passing the entire list of whatever conversation, history that it could have. We're passing it all inside of this, and this is going to return an AI message, and that also needs to be an array. Okay, so this entire thing is going to return the AI message, and that needs to be an array so that two arrays can merge together. So we have to do something like this. Okay, so I really hope that makes sense. So the chatbot node is done, right? So now let's go ahead and create our state graph. Okay, so that we can actually add all of these nodes. So we've already created the chatbot node. We just need to add this thing and then connect it and set this as the entry point. All right, so what we can do is we can say graph equals state graph. Let's pass in this particular schema. All right, and let's go ahead and add all the nodes. So in this case, it's just going to be the chatbot node. All right, and then we can also set the entry point to this chatbot. And then finally, we can also add an edge, right? We can add the edge from chatbot to end. Okay, as simple as that. So we've added this as the chatbot node. We've connected this and this together, and we've set the chatbot node as the entry point. Okay, so now all that is left is to compile the graph. So let's go ahead and compile. And next up, we want to write a for loop, right? So this is something that constantly requires the users, we need to be able to basically have a conversation in the terminal, like a very similar, like a chatbot, right? Like how we would talk to, Claude's interface, web interface, or ChatGPT's interface. That's how we want to talk to it, right? So in that case, we can just go for the while loop, right? So inside of this while loop, we want to first add an end condition. Let's say if the user were to say exit or something like that, we need to come out of the loop, or else we just need it to continue looping, right? So in this case, I can just say user input. I'm first going to collect whatever the user is typing in there. I can use the inbuilt method, input method, and the message I want to basically show in the terminal is just user, something like this, right? All right. And now I can check if the user input, okay, so is one of, it could be many things. It could be, either exit or end or buy or something like that. Okay, end, okay, something like this. So if it is any of these things, I'm just going to break. Okay, that is it. If it is not the case, then we just need to invoke the graph, right? So I can just say app.invoke, and we have to pass in the initial state right here. And the initial state is going to be the messages. And right here, initially we need to pass in the human message, right? So we need to pass in the human message, and that is going to have the content, but we are going to get that content from the user message. Okay, I hope this makes sense. Now I'm just going to, I'm just going to say result of the entire, this thing. And finally, we are just going to print the result. Okay, so it's very simple. On every single iteration, we're going to restart the entire graph. It is very similar to just stopping the program and starting it again, right? So it's just going to start chatbot end. Okay, another while loop, start chatbot end. Okay, so let's come back and let's run it and let's see if everything is working fine. So, I can say something like, hi, I'm Harish. And great, you can see that the graph has completely executed once. So it started from here. I passed in the human message, hi, I'm Harish. And then coming down here, you can see that in this list, we have the AI message, right? The AI message saying, hello, Harish, nice to meet you. Is there anything I can help you with, right? So it only has one human message, one AI message. So we start off with one human message. It comes here, it adds the AI message to the list, and then it ends it, and then it shows the result. Very simple, right? But if I were to, do something like, if I were to, let's say, ask, okay, what's my name? Okay, what do you think would be the answer, right? Because we are restarting the graph, okay, this is going to be the initial state that we're providing, right? This is going to be the initial state that we're providing. The AI does not have context about what my name is right now, okay? So if I were to press enter, okay, this is where I put it. And here you can see that I don't have any information about your name. I'm a large language model. Okay, so there is no actual memory maintained, guys. I really hope that you understand what's going on here. Every single time the iteration of the while loop is running, we're starting the graph afresh. There is no memory at all. There is no persistence at all. Okay. And also if I were to, say something like, what's the weather in Bangalore, let's say, I mean, it's not going to be able to understand. It's not going to be able to give an answer. I'm not able to access real-time information about the weather in Bangalore, right? There is no tools available for the LLM to use either, right? So in the next, I hope you understood what are the limitations of this particular, basic chatbot. In the next section, we will introduce the ability for the system to access the internet. Okay, so that is one thing that we'll do. It's very simple. It's very basic. But once we have both of that, then we'll introduce persistence, we'll introduce memory, and we'll see how to do that. Okay, so I'll see you in the next section. Hello guys, welcome to this next section. In this section, we'll just equip our chatbot with the ability to call tools. All right, so you can see that I've already gone ahead and created a file, and then I've done some imports right here. It's not really very different from what we did in the previous section. I've just basically copy pasted everything. But in addition to that, I'm just going to use the Tavily search this thing again, and I'm going to create a list of this thing. Okay, so I can just say search tool, and then I can put this in here. Okay, just to be a little bit more descriptive. And as usual, we're going with this particular model again. All right, perfect. So the next thing that I'm going to do is I'm going to initialize a variable called LLM with tools, let's say, and then I'm going to use the bind tools method that this provides. And here I can actually go ahead and pass in all these different tools. Okay, so if you're not familiar with bind tools, basically when we make the API call to the LLM, okay, so normally we can just say something like, what's hi, how are you, or something like that. But if we are to, ask a problem that, the LLM would not be able to solve it by itself, okay, so we can actually make some tools available to the LLM. Okay, so in that case, what the LLM is going to do is it's going to look at all of the tools that are available. It's going to see, okay, can I answer it by myself, or do I need to suggest to use a particular tool? So let me give you a very simple example how it works. Okay, so it's going to be very similar to doing just LLM.invoke. It's going to be very similar. In addition to that, we are just making some tools available to the LLM to decide if it wants to use a tool or if it can respond by itself. So I can just say, LLM with tools, invoke. So I can say something like, hi, my name is Harish, and let me go ahead and print this out. So let me run this. You are going to see some errors and all because that is from LangSmith. Don't worry about it. But if you come up here, this part, you can see that, it says, okay, nice to meet you, Harish. Is there anything I can help you with, right? So this is a perfectly valid response, no different from, using just LLM.invoke. But because we've binded some of these tools, okay, so what this is going to do is, let me clear this out and let's tweak the prompt a little bit. Okay, so I can say something like, what's the weather in Bangalore? So in this case, if I were to run this, let's see what happens now. Okay, so in this case, you can see that the content is empty, right? The content is an empty string. And if you come, this entire thing is a dictionary, right? So if I come down here, in the tool calls, you can see that there is one object which is suggesting to call a particular tool that we have provided in the Tavily, that we have provided right here. Okay, so I know this is a little complicated to look at. Let me just actually, put it in a neat format. Okay guys, so basically what I've done is I've just copied this thing and I've put it in a JSON file so that we can actually look at it, in a proper way. So you can see that we have the content which is going to be empty. Okay, let me just, you can see that total of, 6 properties are there. The content is going to be empty. We don't really have to consider these things. These are just metadata and some additional information. But here inside of the tool calls, you can see that there is one object inside of which the LLM is suggesting to use this particular tool, and it is also providing the query, right? It is also providing the query. So that is something that we are getting from this bind tools. We're just making some tools that are available and the LLM can decide. Perfect. All right, guys. So now that we've understood this bind tools method, now let us go ahead and build out our graph. Okay, so let me show you, what we're going to be building. So it's going to be very similar, but right after the chatbot. Okay, so right here, this is where the LLM.bindTools lives, right? So what's going to happen is, let's say if I were to ask something like, what's the weather in Bangalore? So this is going to output a response, which we just looked at, right? So if the content is going to be empty, but the tool calls property is going to be having exactly what tool to call. So basically we're making a decision right there. So we're checking if there is a tool call available or not. If there is no tool call available, it means that we can just, end the graph. Okay, so the LLM, it means that the LLM has all of the information. It needs to answer the question. So in that case, we can just end it right there. But in case there is no content, there is only tool calls available. In that case, that method, that condition method that we are going to write is going to make a decision. Okay, it decides whether to go to the end or if it is going to go to the tools. If the tool calls are available, it's going to go here, and this tools method is going to execute the tool. Okay, so it's going to execute the tool. It's going to get the response from, let's say, Tavily search. Okay, so it's going to create a tool message with all the content, and it's going to append it to the list, and it's all going to be provided to this particular LLM. Okay, I really hope that makes sense. And then once the LLM has all of the full information, including, information about the weather in Bangalore or something like that, it is then going to, output the content. It's not going to make another tool call because it now has all of the information. So in that case, it's just going to give the content, the current weather is this, and then the flow is going to go to the end. So now that I've given you a bird's eye view of what we're going to be building, let's go ahead and code this out. All right, so as for the actual node, it's not going to be very different from what we did previously. So I'm just going to copy this particular chatbot, put it over here, and okay, we can change this. And then instead of using this LLM, we have to use this LLM with tools. That is the only difference. All right, perfect. So what is the next thing? So we've written this. Now, there is going to be a conditional, there's going to be a message that decides if the control flow should go to the tools node or the end node, right? So let's actually call this something like tools router. Okay, let's call it tools router. Okay, this is going to be a function. This is again going to get the list of everything, right? And okay, so what this tools router is going to do is, let me just copy paste some code and let me walk you through it. All right, so let me walk you through it. So first off, we're just getting the last message from the list of messages. Okay, so why am I getting the last message? Because if the control flow is coming here, it means that the last message is going to be because of this chatbot, that is always going to be an AI message. So I'm just getting the last AI message, and then I'm just checking, does the last AI message have a property called tool calls? And I'm checking if the tool calls property also has a list greater than 0. So if I come back to the response, you can see that this is present, and this list, the items, the length of it is greater than 0, right? So I'm just checking that. So if it is true, then it means that we have to go to the tool node, right? We have to go to the tool node. Okay, so that is what this method. I hope that makes sense. Now let us actually go ahead and build out this particular tool node. This is actually much more simple. LangGraph provides a very, very easy to use method that we can use that takes care of like 95% of the work. So, so we have tools. Okay, so let's call it tool node itself. And then we are going to use this class called tool node that just takes in the tools that are available. Okay, so this tool node comes from langgraph.prebuilt. So let me actually hover over it and let me show you what it says. It is a node that runs the tools called in the last AI message. Okay, so if this is going to be the last AI message, this entire thing, it is going to run all of the tools that are available in the last AI message. Okay, so it can be used either in StateGraph with messages state key, okay, or a custom key as well. So we always have to use this particular keyword messages. Okay, so this tool node actively looks for messages and looks at the last AI message, and it goes and executes all of the tools that the LLM has specified. If you want this tool node to look at something else, okay, let's say, I don't want this particular messages key. Instead, I want messages, let's say, okay, it's a different name, right? So if that is the case, then we have to tell the tool node to look at a different list and not the default messages list. Okay, so how can we specify that? We can actually specify it by saying messages key. Here we can actually specify this thing. That's it. That's as simple as that. Okay, it's going to look at this particular tuple. It's going to look at this particular, list, and then it's going to look at the last AI message that is present. But yeah, in this case, we can just remove it, and let's actually, okay. So yeah, the tool node is also done. So what have we done so far? So we built out the chatbot node, we've built out the tools node, we've also built out the tools router method that is going to decide if it needs to go to the tool node or the end. Okay, so now all that is left is to just create the graph and add all the nodes and connect it all together, right? So here's what I'm going to do. I am going to, go ahead and create the graph. So I'm going to say StateGraph. Let us pass in the basic chatbot. And now add node. Let's go ahead and add the chatbot first. Chatbot. The second node that I want to add is going to be this particular tool node, right? So I can just say tools, because in the diagram, that's what I've specified, right? Tools. And I can just go ahead and put this right here. And what's the next thing? So we've added this and this. Now we have to, connect it. So we know the entry point is going to be set entry point is going to be the chatbot. And as soon as the entry point, as soon as this chatbot node is executed, we have to make a decision whether to go to tools or end. So in this case, we have to set conditional edges. So we have to put the chatbot, and then we have to put this tools router here. Okay, I hope that makes sense. And once the tools router, okay, I think that should be it, right? So the tools router is going to decide, okay, so if we've named it tool node right here, let's just go ahead and name the same thing here as well. Okay, perfect. Okay, so right after the tools router is executed, it is going to go to the tool node or the end. Okay, so let me check if we've written all of the edges. So right after the chatbot, it comes to the tools, but we've not really added this particular edge yet. So let's go ahead and add a normal edge. So this is going to go from tool node to chatbot. Okay. So now let's go ahead and compile this graph. So I'm just going to go ahead and just copy this bit of code. It's not going to be any different. So we're compiling it and then we're running the same thing again. But the only difference is that this time we have tools available. All right. So let's go ahead and run it. So here I'm just going to say something very simple first, just to test it out. Hi, I'm Harish. It's going to be like, hi Harish, how are you, or something like that. Okay, so you can see that the AI message says that, hello Harish, it's nice to meet you, great. Still the memory is not really added yet, but now let's actually go ahead and force it to use our Tavily search tool. So I can say, what is the current weather in Bangalore? Okay, guys, even though it looks like, it is continuing, the graph is actually getting executed from the start with a different initial state. Okay, so it's not going to remember anything, even though it looks like, it is continuing. Perfect. So what is the current weather in Bangalore? So in this case, great. So right here, let's go up. Okay, so we have the user message right here. Okay, so what should happen? First is the human message. Okay, let's come back to the state. Okay, let's come back to the graph. So we have the initial human message, and then the chatbot, which is going to be the LLM call. It is looking at the what is the current weather in Bangalore, and then instead of actually providing the content itself, it is suggesting to use a tool, right? So we've got a human message, we've got an AI message with just the tool call property filled up. So right after that, the control flow is going to come back to the tools, this node. This node is going to execute based on the query, right? Based on the query, the search query that the LLM provided. So this is going to output what? This is going to output the tool message. So we've got a human message, AI message, tool message, and then the tool message, this entire list is going to be sent to the LLM again, right? And now it is going to give the final answer. So we should see all of these things. So what do we have right here? So we have the human message, what is the current weather in Bangalore? And coming down, we should find the AI message. Right here, you can see that the content is empty. Instead of the content, we can actually find the tool calls. And inside of the tool calls, the LLM is suggesting to use this Tavily search. So right after this, you should see what? A tool message. So if I search right here, okay. So we have the tool message right here. And right here, you can see that this entire thing is going to be the response of the Tavily search tool. So we have the URL and the content, URL content, a lot of these different things, right? And finally, the control flow is going to go back to the chatbot, to the LLM, right? So if okay, so we should be able to find another AI message somewhere here. Okay, great. So the AI message. So it is saying the current weather in Bangalore is partly cloudy with a temperature of 32.3 degrees. Okay. So now the LLM has full context about the weather. So it is giving a final answer. Okay. So this is in a nutshell, basically adding tool calls to a chatbot. Okay. But still you can imagine that if I if I were to say something like what's my name, right? Okay, it's not going to if I come down here, you can see that I don't have any information about your name, right? So it doesn't actually maintain the context about what happened previously. So that is something that we will tackle in the next section. So I'll see you there. Hello guys. So in the previous section, we spun up a very basic chatbot and we also built chatbot with tools. But we also noticed that, the previous conversations that we have, the chatbot does not remember because persistence have not been introduced yet. Memory has not been introduced yet. So that is exactly what we're going to solve using something called checkpointers in LangGraph. So when you build a basic chatbot using LangGraph, you run into an immediate limitation. By default, your chatbot has amnesia. This we've already seen. Every time a user starts a conversation, the bot has no recollection of previous interactions. This happens because without memory management, each invocation of your graph is completely independent. This is where the concept of checkpointers in LangGraph come into the picture. So let us look at what exactly are checkpointers. A checkpointer in LangGraph is essentially a way to save the state of your agent or workflow at specific points during execution. Think of it like saving your progress in a video game. When you reach a checkpoint, the current state of everything is saved. If something goes wrong later, you can always return to this saved point. You don't have to start over from the beginning as well, right? So in the context of LangGraph nodes and workflows, nodes are the individual steps or components in your workflow. This we already know. Checkpoints basically save the complete state after a node finishes its work. If an error occurs in a later node, you can resume from the last checkpoint rather than starting the entire workflow again. This is particularly useful for complex workflows where processing takes significant time or resources. You want to implement retry mechanisms, and in this case, all that we're going to do is introduce persistence across sessions or server restarts. So to introduce persistence and memory into your graph, understanding checkpointers is only half of the puzzle. You also need to understand, what is a thread ID. Okay, so together, both of it together, we can actually introduce persistence into our graph. So we will implement it later on in our code. But for now, let's understand what is a thread ID? Why is it even necessary? So a thread ID is simply a unique identifier for each specific conversation or workflow execution. You can think of it like a unique session ID for a user, a conversation ID that groups related messages together. So if you've ever used the web version of ChatGPT or Claude, every single chat that you create or every single conversation, this thing that you create has its own thread ID, right? So that is how we can actually separate out these conversations. So that is what a thread ID is. So if at all, it's a group chat or something like that, that group chat is going to have its own thread ID. So I hope that makes sense. Let's move on. A thread ID is necessary because you might have multiple conversations or workflows running simultaneously. Each needs its own separate saved state. The thread ID helps the system know which saved state belongs to which conversation. Without thread IDs, all your conversation would share the same state, which would cause confusion and errors. So far, we know that to introduce memory and persistence into our LangGraph application, we need two things. We need to provide a checkpointer, and we also need to provide it a thread ID so that it can link both of this together, right? So let's actually go ahead, jump back to our Visual Studio Code. Here, I've basically just created a file called chat with in-memory checkpointer. So all that I've done here is basically just implement the basic chatbot that we already saw right here. Okay, so we just have a state, we have the chatbot node and then end node. So we have start, chatbot, end, that is it, right? So that is all that I've done here. I've added the chatbot node, I've added the link between the chatbot and the end, I've set the entry point to chatbot, compiled it, and we have the final application right here. And all that I'm doing is I'm invoking this application using this initial state. Okay, I'm just providing hi, I'm Harish, and then I'm trying to use the same application again, and I'm passing in something else. Okay, what's my name? Okay, it's very simple. But usually what happens without memory, this graph gets invoked from the start to an end, and it doesn't really remember what happened previously. So that is the issue that happened. So let me quickly run this for you and show you that memory is indeed not working. So yeah, you can see that this is going to be the first invocation using, I've provided this thing right here, right? Hi, I'm Harish. Okay, I'm providing this thing. So you can see that, hi, I'm Harish. And in this AI message, nice to meet you, Harish, great. But if I were to use the same app and invoke again and use a different what is my name, if I were to ask that, it should ideally remember it, right? And it is saying that I don't have any information about your name, right? So the persistence is not really happening, right? So let's actually go ahead and introduce that. So we know that we just need to provide a checkpointer and a thread ID. So to introduce the checkpointer, all that I'm going to do is I'm going to import the memory saver checkpointer. Okay, so I'm just taking it from LangGraph checkpoint memory saver. So this is an in-memory checkpointer. This is not really put in an external file or an external database or anything. It's an in-memory checkpointer. Okay, we'll see further, what are the differences. But okay, all that I'm doing here is I can just say memory and then invoke this. Okay. So if I hover over this, you can see that it says it is an in-memory checkpoint saver. This checkpoint saver stores checkpoints in memory using a default dict. Okay, so this is really we can use this for debugging and testing quickly, but then in production applications you would have to use an SQLite or a Postgres checkpointer. So we will look at more about that later, but for now all that I'm going to do first is I'm going to come down here, and when we compile the graph, you can see that it actually asks for this checkpointer, and we can actually provide this in-memory checkpointer right here. Okay, so if you remember, this is the first thing that we have to do. And the second thing is we also have to tie it with a particular thread, right? A thread ID. So what I'm going to do is I'm just going to come down here and I'm going to say config. Okay, and this is going to be an object. And inside of this object, okay, so this is the exact structure that we have to follow. So we have configuration. Okay, and this configuration property inside of this dictionary is going to have another object inside of which we have the thread ID right here, and we can actually put one or two or whatever we want. Ideally, we want it to be something that is very unique. You can use the UUID package or something like that, but for now I'm just going to save it as 1. And what I can do is I can come down here, and wherever the graph is being invoked, I can just say config equals config. That is it. Okay, so this is going to be the first place where we're invoking the same graph, and we're also invoking it here. So if you want to tie this and this together, the first and the second one together, if you want the conversation to continue, all that we have to do is provide the same config here as well. Okay, great. So that is it, guys. Let me go ahead and run this file so that I can show you, the persistence. Okay, I messed up one word right here. Okay, this is not supposed to be configuration. It's supposed to be configurable. Okay. Sorry about that. Let's run this again. All right, great. So we have the first time we're invoking the graph right here, and then we have the second time we're invoking the graph right here, right? So the first time, we are passing in the human message and the AI message is getting generated, right? So if I come down here, the first time we are invoking this human message, we are passing in, and then an AI message. So we already have two messages, right? So since we are passing the same config here as well, so when I pass in this initial state, it actually needs to be the third message and not the first message, right? So that is exactly what we will be able to see in the final states of, both of these graph invocations. So right here, you can see that first is the human message, hi, I'm Harish. AI message is saying that, nice to meet you, Harish. Great. So the next time I invoke the same graph right here, you can see that we see the first message, right? The first message, even though we are passing in this what's my name as the initial state, we still see the previous messages that is linked with this particular config, okay, with this particular thread ID. So we have the hi, I'm Harish, nice to meet you. This is retained. And then what happens? Then I am again providing my human message. Okay, where is it? Okay, human message. What is my name? And the AI is able to say your name is Harish. Okay, so I really hope that you're able to see, how persistence works, but you still might have some questions about how exactly is the storage being saved in this memory saver, in this checkpointer, right? So I've actually prepared that as well. So you can see that this is how basically roughly how the structure looks like. So you can basically think of it as a dictionary with, different thread IDs. Okay, for in our case, it's going to be the thread ID of 1, right? So you can equate that with this particular thread 1 to 3, and inside of which we have multiple checkpoints. Okay, checkpoint 1, checkpoint 2, checkpoint 3, checkpoint 4. So inside of which we have the messages here, right? So initially I'm just providing hi, I'm Harish. So right after the first node's execution, okay, whatever is the output of that particular node, it is going to append to this particular messages list. And then after the AI responds with something, we are going to add that AI message to this thing, and that is going to be checkpoint 2. And then, there could be, another human message saying that, okay, what's the weather in New York or something like that. That is going to be added, and that is going to be checkpoint 3. So checkpoint 4, checkpoint 5. So every single time a node is done executing, whatever is the response of it, it could be a tool message, it could be a human message, it could be an AI message. It just gets appended with new checkpoints. Okay, so I hope that makes sense. Okay, you can see that we also have the tool message, and in addition to it, we are also maintaining basically that checkpointer is also going to maintain what was the current node, what was the next node, so that if there is something that goes wrong, we know exactly where to resume the execution. And if at all you want to look at the latest checkpoint, there are methods that LangGraph makes it available for us to use. Let me just comment this out. So this is the graph that you're working with, right? This app is what we're working with. We can just say get state, and we can pass in the config that we are interested in. Okay, so basically the thread ID that we are interested in. Let's go ahead and print this. Okay, so now you should be able to see the latest this thing. Okay, so this is going to give you a snapshot, the snapshot of the latest checkpoint. Okay, so here you can see that there is a human message, and there is an AI message, and there is another human message, and then there is another AI message. Okay, so that's it. And then a bunch of other things. Actually, let me just put it in a neat format. Okay, so yeah, so this result is what it looks like. Okay, so basically it's going to let me just okay, so this is how it looks like. Okay, so you can see that we have a bunch of different messages right here. Okay, so the first message is going to be a user message. I'm seeing this thing that's got an ID as well, and then the AI is saying this thing. Basically behind the scenes, human message and AI message gets converted to these roles and content. Okay, so we have the role content. Okay, we've got some other metadata as well, and then this is the third message, what's my name, and this is going to be the fourth message. Okay, your name is Harish, right? So, and then in addition to that, we also maintain some other things like the config, the thread ID. We also have the metadata, right? Okay, we've got some additional things that we don't really have to confuse ourselves with right now, but yeah. So we have all this data being printed from this particular latest checkpoint state. Okay, and I also want to do another thing right now. This is a little artificial, right? I've basically just invoked the same graph 2 different times so that I can sort of demonstrate this persistence in action. So let me actually put it in a while loop so that it's much more natural and we can actually have a conversation in the terminal. Alright guys, so all that I've done is I've just converted those 2 different invocations into a while loop so that we can actually extend it and basically have a conversation, basically have a long conversation. And finally, I'm just going to, to show the AI message, I'm just going to take the last message, which is going to be an AI message, and I'm printing out the content, and that is it. So let me run this. So you can see that, hey there, my name is Harish. I know I'm using the same example again and again, but yeah, my name is Harish. I just wanted to remember my name, right? So my name is Harish, and so nice to meet you, Harish. Great. Is there something I can help you with? And now I can say, what's my name, right? So it should be able to say your name is Harish because the entire history is now maintained. Perfect. So you can actually test it out yourself. So what I want you to do is, basically try to invoke this LangGraph application using different thread IDs, and you would be able to see that, if it is a different thread ID, the conversation history would not be available and it would start from scratch. And also guys, there is one big disadvantage when it comes to using an in-memory checkpointer. So what this is it's an in-memory checkpointer. Okay, so basically if we were to stop this program right here, okay, so if I were to say exit, all right, and if I were to run it again, and if I ask the same question again, what's my name, it is not going to have that information because the memory gets wiped out. So this is exactly why LangGraph provides, this SqliteSaver. This is something that we can use to sort of, save all of that memory externally, and not in memory. And it also provides a Postgres saver as well. Okay, so that even after we end the program, we can always continue it, and that is exactly how things should work in production, right? So that is what we are going to be looking at in the next section. So I'll see you there. Hello guys. So in this section, let us now go ahead and replace our in-memory checkpointer with the SQLite checkpointer so that we can introduce true persistence. Meaning we can, shut down the server, or, we can close the application and still we can resume the conversation, right? So I've gone ahead and created this new file right here called chat with SQLite checkpointer. I've basically just copy pasted everything that I had in my previous file. But right now, instead of this memory saver, we are going to use the SQLite. So I'm going to go ahead and, import another, okay, we don't need this anymore. We can go ahead and import the SQLite. So I want you to go ahead and install this package so that we can actually go ahead and import it. So let's do pip install this particular package. Let's give it a few seconds. All right, great. So now you can see that the warning has gone. Now let's go ahead and import the SqliteSaver. All right, great. So what's the first thing that we have to do? So we have to first import the SqLite 3 library that is basically a part of Python itself. So whenever you want to work with basically SQLite, you first create a connection string, right? So that is exactly what we're going to do. Let's say SQLite connection, and we can say SQLite dot connect, and then here we can basically provide the name of the database file that we want to create. Okay, so I'm going to call it something very simple. So I guess we can call it checkpoint dot SQLite. Okay, So this is a pretty standard thing that we do in pretty much any Python application if we want to work with SQLite. Okay, so now we have to introduce the check pointer. So to do that, basically all that I'm going to do is I'm going to replace the memory saver with the SqliteSaver, and then I'm just going to provide this connection string inside of this, and that is it. Okay, everything else should work perfectly fine. So let's go ahead and run the file. So the minute it hits this particular line, it's going to create a database file, and then it is going to, after every single node execution, this check pointer is going to take control. It is going to append new checkpoints, and it's going to save the state, right? So let's go ahead and run this file. Okay, and great. You can now see that there is a file that is being generated right here. There is a database file, right? So let's actually go ahead and, right now the check pointer is not really taken effect, right? It hasn't really worked yet. It just created the database file. So let's go ahead and say something like, hi, I'm Harish. So this way it's going to actually save the checkpoint. So let's see what happens. All right, so it looks like we are getting this error. The SQLite objects created in a thread can only be used in the same thread. All right. So guys, this issue is a pretty common issue. So basically how LangGraph works is that it's going to use multiple threads, different threads, whatever thread is available, in order to, work with the SQLite database. But SQLite database only prefers to work with one thread. Whichever thread that created the SQLite database, that is a thread that it allows to make modifications as well. So what we can do is we can actually explicitly tell SQLite to not freak out if some other thread were to go and make modifications. So to do that, I can say the check same thread and set it to false. Okay, so this should get rid of the error. So let's actually go ahead and run this again. Let's delete this off. Okay, so now it should hopefully work fine. Okay, so I'm Harish. Okay, I messed up my name, but yeah, how can I assist you today? What's my name? Okay, you can also see that there's multiple different files that are generated. They're all part of the same this thing. So what's my name? And you can see that, the persistence has been truly, introduced. So I can easily just exit out of it. Okay, so right now the application is closed, but still the database is persisting, right? So now I can again ask, I can basically, you can run this file again, and I can say, what's my name? And it should be able to pull it from this particular DB file. Okay, so we can also go ahead and take it up a notch. We can actually go ahead and explore this. So I'll also show you how we can actually take a look at. So right now you can see that it is not really accessible. So one way to do that is to go ahead and install the SQLite. There is an extension here. You can go ahead and install it. But I had some issues with that extension. So what I prefer working with is this DB browser for SQLite. You can go ahead and download it. This is what I clicked on to download it. And if I open it, this is how it looks like. Now I can just go ahead and open the database. I can just drag and drop this particular file, this file right there. Let me show you how it looks like. Okay, great. So I've actually opened that particular DB file in my DB browser for SQLite. And right now you can see that there are two tables that our LangGraph application, our SQLite checkpointer, has created. So inside of this checkpoint, you can actually click on this and go to browse data. And you can see that we can also see all of the different messages that have been added. So you can see that this is the checkpoint ID 2, whatever. And then if I click on this thing, okay, so this is going to be the metadata, right? So if I scroll down, scroll to the very right, you can see that the content is going to be I'm Harish. I'm saying I'm Harish, and right here there is a loop happening. We don't have to worry about that. And then the AI is saying, hello Harish, how can I assist you today? And then the same input happens, and then another loop happens. We don't have to worry about that. And finally, okay, I ask, okay, what's my name? And then it's saying, so basically you can see that all the messages are being stored in this table called the checkpoints table, right? So I can also do something where I can just go to the, I can basically execute an SQL command and then sort of delete all of the rows from this table. So the way that I can do that is I can just say delete from, I think checkpoints, right? Checkpoints. And if I run this file, okay, so you can see that 9 rows have been affected. So most of it has been deleted. And if I come back to my VS Code, So if I now ask the same question again, okay, what's my name? It is not going to be able to answer it because we have removed all of the rows. So let's check it. Great. You can see that, I'm not able to recall information. Great, guys. So I hope that you now understand how, the SqliteSaver works, how in-memory checkpointer works. So now that we understand how checkpointers in memory works, let us now use all of these concepts and introduce a human in the loop scenario. Okay, so I'll see you in the next section. Hello guys, so far we've learned a lot about checkpointers in memory. Let us now use some of those concepts and let's start exploring human in the loop. So let's look at some slides. So a human in the loop workflow integrates human input into automated processes, allowing for decisions, validation or corrections at key stages. This can be especially useful in LLM based applications where the underlying model may generate occasional inaccuracies. So some of the use cases include reviewing tool calls. So humans can review, edit or approve tool calls requested by the LLM before tool execution. We can also use it for validating the LLM outputs. So humans can review, edit or approve content generated by the LLM. Or, we can use it to provide additional context as well. Like for example, enable the LLM to explicitly require human input for clarification or additional details or to support multi-turn conversations. So next, let's look at some of the design patterns that usually are used with human in the loop. So there are 3 different actions that you can do with a human in the loop workflow. So the first one is approve or reject. So we can pause the graph before a critical step, such as an API call, to review and approve the action. If the action is rejected, we can prevent the graph from executing that step and potentially take an alternative action. This pattern often involves routing the graph based on the human's input. So here's a very simple diagram. So here we have, a node here, another node here, and then some other nodes here. So right here, we can actually decide, the human can decide if, if the flow needs to go to this particular node or this node. So depending on the human's approval or rejection, the graph can proceed with the action or take an alternative path. Let's look at another one. So review and edit state. Okay, so in this case, a human can review and edit the state of the graph. This can be useful for correcting mistakes or updating the state with additional information. And another use case could be reviewing tool calls, which we've already seen. A human can review and edit the output of the LLM before processing. This is particularly critical in applications where the tool calls requested by the LLM may be sensitive or require human oversight. So you can actually imagine that there could be some tools that could be expensive, and in that case we can have the graph ask the permission from the human, and if the human is okay with it, then we can go ahead with going to the particular tool node, or else we can go to another node in the graph. So if you remember, the first design pattern that we saw was approve or reject. Okay, so that would probably be the easiest for us to, as a beginner, for us to learn. So basically, the graph flow execution just comes in a certain direction, and depending on whether the human is okay, depending on whether the human says yes or no, we either direct the flow in the left side or we direct the flow in the right side. So I've just prepared a very simple, intuitive example. So you can see that we have basically the graph that we are looking at right now is like a very simple agent that creates LinkedIn content. And if the human is like happy with it, it goes off and talks to the LinkedIn API and then just creates a draft. Or if the human is not happy with the draft that is generated, the human can provide feedback on it, and then the agent is going to take that feedback and then iterate on it and make it better, and the loop is going to continue. So you can see that we have the start node, and here is where we are actually going to provide the, this is the topic that I want you to create a LinkedIn post on, right? So this node, when it hits this node, the LLM call is being made, a post is generated. And as soon as this post is generated, we are then going to interrupt this, the flow of the graph. It's going to stop the flow of the graph right here. And then we are going to, basically provide, show the user the post, the draft that is created, and ask the user, is it good or not? Okay. So if the user says yes, in that case, we are just going to go ahead and post, post it to LinkedIn, or rather, create a draft and communicate with the LinkedIn API, right? But if the user were to say no, then this node comes, and then we are going to collect feedback from the user. Okay, so we can have the user say, okay, make this shorter, make this longer, make it more funnier, or something like that. And then we are going to feed it back to the generate post, and it is going to iterate on it, right? So initially, we're just going to do it very quick and dirty. We are not going to dive deep into LangGraph's methods or anything of that sort, just so we can actually understand how simple it actually is, right? So you can see that I've actually gone ahead and created a folder and a file, and I'm calling it using input. Because in this particular example, we are going to be using the input, the Python input method, and that is going to be, something that all of us would have already been used to working with, right? So the first thing is obviously just a state with a very simple, messages property. We've provided the add messages reducer function here as well. And then we are first defining the generate post node, right? So this is something that we would have already seen before. It just takes in the list of messages and invokes on it, right? Right. So let's come back. So the generate post is done. So as soon as the generate post is done, what we want to do, we want to actually, get the feedback from the user. So if I were to come down here, you can see that. So right after the generate post is done, I'm going to go to this particular node called get review decision. Okay, let's go back to the get review decision. So all that I'm doing here is that I'm going to take the last message, which is going to be the AI message, which is going to contain the LinkedIn post, right? And then what I'm basically going to do is I'm going to print it in the terminal, right? Okay, this is going to be the current LinkedIn post, and then I'm showing the post content as well. And then I'm basically asking the user, do you want me to post to LinkedIn? Yes or no? Very simple, right? So depending on whatever the answer is, we are then directing the flow of the graph to either the post method, the post node, or the collect feedback node. So if you remember right here, we are either going to the post node or the collect feedback node, right? So if I were to go to the post node, I'm just basically saying that, I'm just showing that this is going to be the final LinkedIn post, and then I'm just going to print it. Okay, we are not actually going to make an API call or anything of that sort. So we're just saying the post has been approved and is now live on LinkedIn. Okay, so we're just keeping it very simple because we're just learning the concept of human in the loop, right? So if this yes is not going, if the user were to say no, in that case, we are going to come to this collect feedback. And right here, you can see that we have another input right here, which is going to ask the user, how can I improve this post, right? So the human could say something like, make this shorter or make this more funnier or something like that. And then we are going to append this to the existing list. And as soon as this is done, we are going to loop it back to the generate post again. So if you see that, I would have added an edge from collect feedback to the generate post, right? So that is going to run the same loop again. And then eventually, if the user is finally happy with it, they can just go ahead and post it to LinkedIn, right? And finally, you can see that we are providing the initial state, which is going to have one human message, which just says, write me a LinkedIn post on AI agents taking over content creation. So if I run this, okay, so you can see that the post has been generated and printed. So you can see that, okay, this particular, node, it comes inside of this particular node and it prints the current LinkedIn post. And then we see the complete post, right? It hits this particular line and it is going to ask post to LinkedIn, yes or no, right? So if I were to say no, it's going to ask, okay, how can I improve this post? And I can say something like, make it, 4 lines max. Okay, so you can see that now it's like, 4 or 5 lines, right? So now if I were to, okay, let's say I'm happy with this particular post, I now want the agent to go ahead and post it as well. So now I can say yes, and that is going to post the final thing, right? So final LinkedIn post, this has been approved and is now live on LinkedIn. Okay, and finally we are also logging printing the final state after the end of the graph, right? So we have a human message, an AI message, and then I would have provided the feedback somewhere. So I would have provided make it to 4 lines max, and then we have the final AI message somewhere here, right? So we have the AI message. So in this example, you can see that we are using this input Python method, but that is not the right way of doing things. Okay, so I've included this particular example because, the way that we are going to be doing it with LangGraph's interrupt method, we are going to be looking at it later, but it's going to be very similar to what we're doing here. Okay, so I just wanted to give you sort of like a bridge between, what we're used to and what we're going to learn. Okay, so let's look at some of the drawbacks of using input because this is not how we're supposed to do it. And then we'll sort of segue into learning about another method, a class that LangGraph provides called interrupt. Okay, so let's come back to the slides. So the drawbacks of input involve, it freezes your program completely until someone types something in. It only works in the terminals, right? It is useless for web applications. If your program crashes, all progress is lost. It can only handle one user at a time. It only lives in your terminal session. So this is why we use a special method that LangGraph provides called interrupt. So what is interrupt and why do we use it? It is a special LangGraph function that pauses your workflow nicely, saves your program state so it can continue later. It works in web apps, APIs, and other interfaces. It handles multiple users and sessions at once. It survives program crashes and restarts, lets humans take their time to respond. It is required for any serious human-in-the-loop system. So here are two ways wherein you can use interrupts. So in the first case, you can see that during the compile step, we can provide the interrupt before, and we can actually specify before which node do we want to interrupt this application. So here we are saying that if there is going to be a tools node in our graph, it means that right before the tools node is going to be executed, we can actually interrupt the graph. Okay, so that is what it means. And LangGraph also provides this interrupt function with the command class that we can use together. So you can see that this sort of using it is going to be very similar to what we did with the Python input method. So instead of the input method, we can just replace that with this interrupt method, and that is it. So whenever the execution hits this particular line, the program is going to get interrupted or basically just paused or exited from the graph. And now, after we get the response from the human, we can just resume it using this command class. Okay, so how can we resume it? Where is the memory stored? It is the memory is stored with the check pointer. Okay, so the check pointer is going to have information about exactly where the interrupt happened, and depending on what we pass in here, it is going to resume it. It is going to continue from it. Okay, so we'll look at a lot more examples about how we can actually use this interrupt method. So in the next section, let us use this interrupt method and then build out some human in the loop workflows. So I'll see you there. Hello guys, so in this section, let us understand what the command class is, what is the interrupt method using very simple examples, and once we familiarize ourselves with it, let us then go ahead and convert the LinkedIn agent that we built using the right methods, using the interrupt method and the command class. Alright, so first in this section, let us look at what is the command class, what is the utility of it. So what this command class allows us to do is to create edgeless workflows. And this is how it works. Okay, so let's say this is a node. This is a very simple node. So instead of, just updating the state as we've been doing so far, what we can do is we can return this command class, and this takes two keyword parameters. So in this goto keyword parameter, we can just specify go to this particular node right after this node is executed. Okay, so you can see that the next node to transition to. That is as simple as that. But what if, a node needs to update the state as well? So far, every node that we've been writing, it also updates a state, right? So we can also specify the same thing here as well. So right here, we have the update keyword parameter. Inside of this, we pass in the same object. This is this is no different to what we've been doing so far, which is just returning the state object, right? So if we return a response right here, it gets appended to the messages list. Very simple. So I hope that makes sense. So to better understand this, I've prepared an example. So right here, you can see that this is a very simple node, graph, I mean. So what we normally do is we just create these nodes, and then we add these nodes to the graph, and then explicitly we will mention add edge, right? But this time we are going to do the same thing using the command class without using any of these, explicit add edge methods that we've been using so far. So let me go to VS Code. So here you can see that I've already gone ahead and created a file. So all that I'm doing here is that, we have a node which is just going to print node A. Okay. So we are not going to be, making any complicated LLM calls. We're just trying to understand what the command class does, right? So we have a node A, we are printing node A. And then right after node A, what do we want to do? We want to go to node B, right? So that is exactly what we're doing. We're returning the command class. we're saying go to node B next. At the same time, I'm also, just to better drive the point home, I'm also going to update the state as well, just to show you that that is also possible. So right here in the state schema, you can see that we have something called text right here, right? So I'm just basically just going to take the text and then I'm appending this letter A to it. All right. So right after the node A is going to be executed, we are going to go to node B. Node B does the same thing. It's printing it and then it is saying go to node C next. And this time, before we go to node C, we are also going to append this letter to the state. Okay, so if the initial value were to be an empty string, so right after this it's going to be A, and when it comes to B, the state is going to have just A letter alone, and by the time this is done executing, we will have appended the B letter as well. And the same thing for C as well. And then we're just going to add the node, and the set entry point also needs to be done. And that is simply it. Okay, so I'm just going to leave it as an empty string right now. All right, great. So you can see that node A is done executing, node B is done executing, node C is done executing as well. And then the final response has A, B, C. I hope that makes sense. So I hope you understand the utility of the command class and the goto keyword parameter that it takes in. Personally, it's a lot more readable for me. It gives me a lot more flexibility on the logic that I put inside of my nodes. So given that this is a very simple graph, this would be a very nice way to learn the interrupt method as well. In the next section, we are going to be adding the interrupt method. We are going to interrupt the graph at a certain point, and then using the human review, we are going to direct the graph towards node C or node D. Given that this is a very simple graph, it would be a perfect candidate to learn about the interrupt method as well. So I'll see you in the next section. Hello guys, so in this section we are going to learn about the interrupt method. So this is the graph that I'm going to be building. So here we have start node A and node B. Inside of node B, you can imagine that we are going to have a command class that can either go here or here. Okay, so we have two different options right here. So in order to make the decision whether to go to node C or node D, I'm going to seek the help of a human. Okay, so I'm going to add a breakpoint in the node B. I'm going to pause the execution of the graph, and then I'm going to ask the question to the human. Do you want to go to node C or node D? Depending on the humans, whether they say C or D, it's going to then go to C or D and then end it. Okay, so I hope you're excited. Let's go to the VS Code. So I've created another file as well for resume. So the reason why I've named it resume is because we are just going to put a breakpoint. We're just going to pause the graph execution and then we are going to resume from it. We're not going to do anything else complicated. We are not going to, update the state, or we're not going to branch off or anything like that. So before we jump into the code, let's look at some of the operations that are possible with interrupts. So the first one is obviously resume. Right? So we can continue the execution with input from the user without modifying the state. Okay, so that is exactly what we're doing here, right? So we are going to pause the execution right here, and we are going to get an input from the user, and then depending on that we are resuming the execution. That is the first one. We can also do update and resume as well. So we can also do update the state and continue the execution. No different. So you can imagine that the command class that we have, it can also go to the next node. We can also direct the flow of the graph to a certain node, but at the same time we can also update the state as well, right? So that is also something that we can do. And the third thing is rewind or time travel, basically. So go back to a previous checkpoint in the execution. So what I mean by that is, so in this graph, let's take a very simple example. So let's say there is a node A, node B. The user decides they want to go to node C and then end, right? So the graph is actually ending completely, right? But we can also do time travel. So after the graph is done executing, if we want to actually go back and then choose a different option for whatever reason, maybe we might have made a mistake, right? It could be anything. So we can actually go back to node B and then simulate that same interrupt again, and then this time go to node D and then end. So how can we do that? We can do that because of checkpointers, right? So after every single node execution, there is a checkpoint getting created, right? So we can actually just take that checkpoint and then continue from that. So that is also another possibility. Along with that, we can also have branch. We can create a new branch from the current execution state to explore alternative paths. It's kind of very similar to what we just saw. And then we can also abort. We can cancel the current execution entirely as well. So each of these operations give you different ways to control the flow of your graph when it is interrupted. Okay, so I hope that makes sense. Now let's actually go ahead and see interrupts in action using this very simple example that I just showed you. Okay, so we're going to be using this particular example, and let's actually go through it. So it's no different. So the previous code that we saw, I've just basically copy pasted everything as is. All that I've done is added this memory. Okay, so why do we need memory right here? So if we are going to, interrupt a particular point in the graph, basically what is actually happening is it's going to exit out of the graph. Okay, but we need some sort of information about where it got exited, right? Where the breakpoint happened. So the memory is going to keep track of where the interrupt happened, so that the next time we can resume from that particular interrupted point. Okay, so that is why we want this memory saver right here. All right. So the rest of it is pretty very much the same. We have node A, and then you can see that inside of node B, I have this interrupt method. So you can see that I've imported it from LangGraph types. So all that I'm doing here is I'm just asking, do you want to go to C or D? Type C or D, right? So we have the human response. And then depending on whether the user says C or D, we are going to go to node C or we are going to go to node D. Okay. At the same time, I'm also going to update the state just so, we're learning and we're seeing possibilities. So we can also do it if we wanted to. So because we are in node B, we are appending B in each of these places, and the initial value is going to be just an empty string. All right. Okay, great. So the same thing continues. We've got node C, we've got node D, and then we are adding all of these nodes together, and then we are providing the memory as well, a config object. Okay, and then finally, okay, we are also providing the initial state. Okay, so the initial state is going to be the value with an empty string. Okay, that is it. So if I were to invoke, okay, so I am not running this just yet. So if I were to invoke this graph, what do you think is going to happen? So it's going to, print out node A, and then it's going to print out, okay, so the execution is going to come to here. It's going to print out node A, and then it's going to go to node B. It's going to print out node B. Okay, so this much we know. So after this node B is printed out, it is going to encounter this input interrupt method, right? Right here, it's going to look at this particular line and it's going to exit the state. Okay, so this interrupt, okay, this is the area where the interrupt happened. That information is put in the checkpointer, right? That information is going to be added and it's going to exit from the graph. Okay, that is it. So if I go ahead and execute this file, so you can see that we have node A and node B printed coming from here. Okay, so as the graph went through these two different nodes, we are printing both of this. And we also see this information right here. Okay, so since we set the stream mode to updates, we are going to see the output of every single node, the state return, right? So node A successfully returned the value of A. This is correct. And then the node B did not get a chance to completely execute because the interrupt happened, right? So that is exactly why we see this interrupt right here. So in here, you can see that the value says, do you want to go to C or D, type C or D? Okay, so ideally in production applications, we would surface this information to the user in the UI in the front end so that you can get that response and then resume the graph from there. But right now we're just going to do it very quick and dirty. But in the next section, in the next few sections, we are going to be building, we are going to be seeing how to build production grade graph applications. But this is great for learning. All right, great. So right here we are getting the latest checkpoint. You can imagine that the checkpoint is going to have information about, what is the exact state at that particular point. But in addition to that, it is also going to have information about, which node, the next node it should go to, right? All those flow related things as well, it is going to contain, right? So I'm going to use this next property, and that is going to give you information about the next node it needs to go to. So if I come back to the diagram, so the interrupt method, we put it right here, right? So because we put it right here, it's going to stop the execution right here. So the next time we resume it, it's going to start off from node B. So that is exactly why we see the node B right here. All right. So What are we going to do right now? We now need to, get the user to give a particular value. It could be C or D, right? So depending on that, it's going to go here or here. So how can we do that? We can now use the command class. Okay, so we can say app invoke command, and we have to use this exact keyword parameter. Okay, so here we can pass in pretty much any information that we want. We can pass in an object, we can pass in a lot of different properties, but right now I'm just going to keep it very simple. I'm just going to pass in the a single letter alone. Okay, so whatever I pass inside of here, the graph is going to resume wherever it left off, wherever it it got interrupted, and this value is going to go and sit inside of here. Okay, so whatever is going to be the response of this, we are sending in this command resume. So if I come down here and if I run this file, what do you think should happen? So we are getting D right here, right? So it should come print D and then go to end, right? So if I run this, you should now be able to see that we are printing node D, and we also see the node B and node D got executed right here. So node B and node D. And as you know, B would append a B letter and D would append D right here. So that's why we have B right here and then we have D. And now I want to explore one more use case. What if we made a mistake coming to the D node? So right now, because I passed in the resume value to be D, it came to D and then it ended, right? The graph ended completely. It ran its entire execution, right? It went through the entire thing. So what if I wanted to sort of come back to this node B, and then if I wanted to provide C now? In this case, it's not going to be possible, right? Because the graph is already ended. We are using the same thread ID as well. So there is nothing to actually resume. There are no interrupts, right? There is nothing to resume actually. So if I just go here and if I change it to C and if I try to run it, we are not going to get anything. Okay, why are we not going to get anything? Because we don't have anything to execute anymore. The graph has already ended. So one way to get around this is to change the config thread ID. So that in that case, you can start over from the start. But in case you want to use the same thread ID, what you might have to do is we might have to do something called time travel. It's very simple. It's a pretty straightforward concept. So I'll explain that in the next section. So I'll see you there. Hello guys. So in this section, let us look at the other way of using interrupts. So if you remember, we've already done this way of doing things, right? So where we use the interrupt method and then we get a response and then based on it, we make a decision inside of the node, right? There is also another way of using interrupts, which you can still see in a lot of code bases, which is to use it this way in the compile step using the interrupt before, keyword parameter. So we are also going to explore this. And in addition to this, let's look at another use case of human in the loop. Okay, so if I were to go to the human in the loop documentation, LangGraph, so you can see that we've got a couple of different design patterns, right? So we've already seen the approve or reject, right? Depending on what the human is saying, we can either go to this node or this node, which we've already seen. Let's also, explore another use case, which is to review tool calls. Okay, so where could this be useful? So you can imagine that there could be a scenario where this particular tool execution could be expensive, or it could be something that is sensitive. It could be an API, or it could be like a Tably search tool, or it could be some expensive tool, something like that. That could potentially require a human approval, right? That could be a valid use case, right? And this is something where we can use human in the loop as well. So we have an LLM, and the LLM is suggesting that we use a tool, and based on that, the human can actually approve before it goes to the tool executor step. Okay, so that is exactly what we are going to be looking at in this section. So once we do this, we can also take a look at the multi-turn conversation. So let us now explore the review tool calls use case. So you can see that I've already gone ahead and created a file called approval. So what I have right here is going to be absolutely no different to what we saw in the chatbot with tools section. But if you don't remember it, don't worry. This is what we did in that section. So we have the start, model, tools, and end, right? So if the human were to say something like, what is the capital of India or something like that, the LLM is already going to know it. It's already going to know the answer. So in that case, there is not the tool condition is not going to go to the tools. It's just going to go to the end. But in case, it requires some real-time information, like what is the current weather in Chennai or something like that. In that case, this LLM that is bound with the tools. So this LLM is going to not give the answer, but instead it is going to give information about which tool to call, if you remember, right? So it's going to go to tools, the Tavily search tool or some other tool is going to execute. It's going to send the response, the tool message back to the LLM, and the LLM can make an informed decision, right? So, and then finally it's going to come to the end. That is exactly what we're going to be building here. The only difference is that we are going to interrupt it before this tools node ever, the execution, before it ever hits the tools node, we are going to interrupt it. We are going to get a human approval before making that Tavily search call. All right. So let me walk through the code step by step. So we have the Tavily. We are putting it inside of the tools list, and we finally have the LLM with tools. And as usual, we just need one messages, property in the schema. We have the model, which is just going to invoke on all the list of messages. Very simple, right? So what should happen right after the model executes? Okay, so right after the model is done executing, right? We have it right here, right? So right after the model is done executing, we need to go to a router, a tools router. The tools router is just going to take the latest AI message. It's going to look at the tool calls, and it's going to see if there is any tool calls the LLM wants us to do, right? So if there is some tool call, like, Tavily search tool call, if the LLM wants us to call the Tavily search, we are then going to direct the flow to the tools node. And the tools node, we can use this pre-built, tool node, class, and we just need to provide in all these tools right there. All right. So that is going to execute that particular tool, and it's going to automatically create a tool message, append it to the messages list. All right. So after that is done, we are again going back to the model. The model now has information that, it would not have had otherwise. Tavily is returning that new information, and based on that, it is going to make an informed decision and then come to an end. So far, this is something that we're already super familiar with, nothing new here. The only new thing that we are going to learn here is look at this compile step. Okay, so as usual, we are going to provide the memory, because if you remember, anytime we use an interrupt, we need to provide a memory, right? Checkpointer, basically, not a memory, checkpointer. And next, this is new. This is where we are providing this interrupt before keyword parameter, and we are providing which node before which we need to exit out of the graph, right? So before we even get a chance to come here, we are going to exit out of it. Okay, so that we can actually review the tool call that the LLM is suggesting. Okay, based on that, we can approve it. In addition to this, we also have an interrupt after. So you can see that we also have an interrupt after right here, right? So this interrupt after also is going to be very similar to interrupt before, but interrupt after is something that exits the graph after this tool node is executed. So that could be another use case wherein we can actually make it mandatory that the user should be able to review the output of a tool call, right? Just to make sure that everything is looking good, right? But in this case, we're just going to do the interrupt before. And if I scroll down here, we have the config object, right? We are specifying the thread ID, and then all that we are going to do is invoke the graph. Okay, so in this time, we are not going to use the invoke method. We can use the stream method this time. The only difference between app.invoke and app.stream is that app.invoke returns a value after the graph has exited. It could be because of an interrupt, or it could be because the end node has reached. But stream is something that it basically just returns. It's a generator function that emits events after every single node, right? So that is exactly what I'm doing here. This events is something that we can actually iterate through, loop over, and then every single time a node is done execution, we are going to get an event right here. And that event is going to contain all the different messages at that particular point. We're just going to take the latest one and pretty print it. Okay, it's very simple. Okay, we can also set the stream mode to values because we are only interested in the values and not the entire object. All right, great. So if I were to now, let's run this. Okay, let me just clear all of the outputs because I ran it before, but let's go ahead and run this file, this code block, run this. Okay, so everything is looking perfect. Let's run this as well. All right, great. So this is, as you know, that this is the question I'm asking. So as expected, the LLM is saying that, okay, you have to go ahead and use this Tavily search results, right? That is what we've provided. So it's also providing the query here as well. Okay, Chennai current weather is what it wants to search for. All right, great. Now coming down, let's actually go back to the diagram. So the model has successfully, provided the AI message, and now we are interrupting out of it. Okay, we are exiting the graph, right? So if I were to now, look at the next node that this latest snapshot is going to go to, what should we see? We are supposed to see the tools, right? So if I run this, you can see that we have the tools, which is next in line. So how can we resume it? It's going to be very simple. All that we're going to do is, we can say app.invoke none, app.stream none, no difference. And then we can actually go ahead and run this again. So this time it is going to, go ahead and execute the Tavily search tool, right? So you can see that this is going to be the result of this is going to be the tool message, the result of the actual tool execution. And once that is done, we are going to feed it back to the LLM, right? So we have the AI message and it's doing an informed answer. So right here, we successfully have interrupted the tool call, right? Okay, we can apply it to a lot of different use cases where, it could be something sensitive that we have to sort of, make sure that a human is approving, or, it could be the result of a tool call that the human has to confirm, they have to quality check or something like that using the interrupt after. So I hope you now understood how simple it is to basically use the interrupt in the compile step as well. So we can also provide in as many nodes as we want, and it's going to be no different. Okay, perfect. So in the next section, we are going to, let's scroll down. We are going to look at this multi-turn conversation as well. So I'll see you in the next section. Hello guys. So in this section, let us look at an example where we make use of interrupts in a multi-turn conversation, and we are going to be using the same LinkedIn post creation agent example. So as you can see that I've already created a file and I've populated the code as well. So let me walk through the code step by step. So looking at the state first, we have the LinkedIn topic. Okay, so this is something that we can populate at the very start of the graph execution. We have the generated post, which will get populated every time the model creates a post, and then we can append it to this particular list. And the same thing for the human feedback as well. Okay, so the first node that we are going to be entering into is going to be the model, obviously. So you can see that here we are using the LLM to generate a LinkedIn post with human feedback incorporated, right? So coming down, I'm just going to extract the LinkedIn topic. I'm going to extract this human feedback, and then I'm going to first create a prompt. Right? So this is going to be the main prompt, right? So I'm providing the LinkedIn topic right here. I'm providing the human feedback. I'm just going to take the latest human feedback, because you can imagine that we are appending everything. We don't really need to append everything in the human feedback. We just need to maintain the latest one. But yeah, why not? We can always have a list so that we can later look at, what are the different human feedbacks that came in, right? So I'm just going to take the latest one. If there is no feedback that we were able to see, then no feedback yet. Okay, so this is the main prompt. I'm simply just saying, generate a structured and well-written LinkedIn post based on this particular given topic. Consider previous human feedback to refine the response. So this is going to be the prompt. I'm providing the prompt, and the system message is going to be a very simple: you are an expert LinkedIn content writer. So as soon as I get the generated post, I'm just going to add it, and I'm also going to add the feedback as well. Perfect. So what are we doing after this? Okay, so if I come down here, you can see that right after the model, we are going to go to the human node. Okay, so what do we have to do? Right after the content is generated, we have to, go to the human node to basically, show the message to the human and ask the human, okay, is this good? Do you have any feedbacks, or do you want to continue? Do you want to finish the execution? Right? So let's go to the human node. So the human intervention node, it loops back to the model unless input is done. Great. So we are awaiting human feedback right here. So we're just going to take the generated post, and then we are going to surface this to the user. Okay. So we're basically just saying this is going to be the generated post. Okay. So this is in an object format so that we can actually show it in a neat way in the UI, right? And then we're showing the message, provide feedback or type done to finish. In that case, okay, the human feedback has been received. this is not going to be a done, but instead it is going to be an actual feedback. So if it is done, in that case, we are just going to, go to the end node. Okay, so go to end node. If you remember, we can also use the command class to do edgeless graphs, right? We can actually direct the flow of the graph right within the node, right? So, but we're not going to be doing this. In this case, we have an actual human feedback that we are going to append to the human feedback, right? So this time we are going to go back to the model. So we are going to do the same thing again, and we are going to now incorporate this particular feedback. Okay, so this loop happens a couple of different times. Okay, how much ever times the human wants to refine it. Okay, so once the user actually says done, in that case, it's going to come to the end node where we are finally going to show the generated post. We're going to show the final human feedback as well. Why not? And then we are going to end it basically, right? So that is what I've done here. Scrolling down, we're just adding all of the nodes. We're adding some initial edges, and then we're finishing it with the end node. All right, great. So coming down, next we have to, take care of the interrupt mechanisms, right? So we have the check pointer, we're compiling the graph, we're creating the thread config, and then now we need to collect the initial state. So if you remember, this initial topic needs to be present at the very start. And in this case, we are getting it from the input method, and the other two is going to be just an empty list. And finally, we are going to invoke the graph. We are using the stream method. And from the chunks that we're going to get in every single event, we are going to look at the node ID, and we're checking if the node ID is interrupt or not. Okay, so if we've encountered an interrupt, we are entering into a while loop right here. Okay, so this while loop is going to stay true until the user says done. Okay, so if the user keeps on providing feedback, we want it to keep on running, and then we are going to provide this user feedback in this resume. All right, so let's actually go ahead and run this file. So let's say, I want to see something like, AI agents taking over content creation. So right here, you can see that. So this entire thing is going to be the LinkedIn post that the model has provided. But one thing that I see is that this is too verbose, too long. Here we can actually provide a feedback right here. Okay, so what feedback can we provide? Keep the entire post to less than 5 lines. Okay, so let's say something like this. So now you can see that it's not more than like 3 or 4 lines, right? So now I can probably say too short, make it longer and funnier maybe. And now it's going to make it a little bit more funnier, right? So I'm not going to read it, but you can actually read it if you want. So, and that is it. So it's going to keep on looping until we say done. And if we say done, and now we can see the entire history. So what is all of this? So in the final end node, we are printing the generated post, the last final generated post. We're printing the last human feedback, and that is all that we see right here. So I hope that you now are starting to see why human in the loop can be powerful. If you have any questions, don't hesitate, ask me in the comments, or you can always go to the source code, pull it, and you can play around with it, try to break it, and yeah. So that's it for this section. I'll see you in the next one. Hello guys, welcome to this brand new section where we are going to be combining retrieval augmented generation, or RAGs, with LangGraph. So we are going to be building RAG enhanced AI agents. Okay, so this is not going to be an introductory video to RAGs, because I expect you to know it already, because I've already covered RAGs extensively in my LangChain crash course. Okay, so if you have not watched it, please go ahead and watch it. So let's anyway get a quick refresher about what RAGs is. Basically, a RAG system is going to comprise of 2 different parts, right? So the first part is going to be the knowledge base construction, and the second one is the query processing. So let's quickly talk about why we even need RAGs. So we use RAGs because we want to give additional information to the LLM. So let's say we have a lot of different documents. I run my own private company, and let's say there's a lot of documents. In that case, the LLM is not going to be aware of the contents of my private documents. So in that case, I can actually make these documents available to the LLM to query. Okay, so that is the whole point of RAGs. So let's go through the knowledge base construction quickly. So let's say these are my private documents, and you can see that 1 million tokens is a lot of information, right? So the first thing that we have to do is we are chunking it up. Okay, so we're taking a huge document and then we are chunking it into smaller documents. So you can see that I'm chunking it, and each chunk is going to have 1000 tokens. So it's much manageable. It's much more smaller, right? So this is what I'm representing right here. We have multiple different chunks. So now that we have chunked up all of our texts, the next thing that we have to do is we have to put them through an embedding model. Okay, so an embedding model is going to take normal text, like normal English. It's going to take that and it is going to embed it, and it's going to convert it into a vector representation, or to put it very simply, it's going to convert it into a mathematical representation. Okay, so this chunk is going to be converted into a mathematical representation. This is going to be the corresponding version, and this chunk is going to be converted into its own mathematical representation. The same thing for every single different chunk. So now we have the English version of the chunk, and we have its corresponding mathematical representation as well, right? So now that we have both of this information, we are going to put it all, okay, we are going to put all of this information, both the original version as well as the mathematical representation, we are going to put everything in a database called the vector database. So now that we have all of the chunks and its corresponding vector embedding versions in the vector DB, now we can actually go on to doing the second part. Okay, so how does the second part work? Let's say there's a bunch of different documents. We've already put it in the vector database, and as a user, I want to query something. So I'm asking, like, some question about my own company, and even that is going to be converted into a mathematical representation. So, and now that we have both this information, the query as well as the data in the vector embedding format, this retriever component is going to, based on this particular question, it is going to fetch all of the relevant chunks which could potentially have the answer to this particular query. Okay, so it's going to fetch all of this. It's going to fetch the corresponding chunks as well, and then finally this retriever is going to have the chunk 1, chunk 2, and as well as the query. Okay, so this is going to be in English. Okay, this is not going to be in the vector embedding format. And then finally we are going to send it to the LLM. So this is chunk 1, chunk 2, chunk 3, and question. Okay, so this is how we are going to send to the LLM. So the LLM is going to look at the question. It's going to look at all the relevant pieces, relevant document chunks, and then based on this, it's going to give an informed answer. So this is a very quick intro to RAGs. So let's quickly see it in action as well. Okay, so I've gone ahead and created a file called basic. Okay, so right here you can see that I've imported document, I've imported the OpenAI embedding model. I've also imported Chroma, which is the vector database that we are going to be using right now. Okay, so later on when we're building production applications, I'll be making a lot more videos, courses on that, where we are going to be using Superbase and doing a lot of cool stuff. But since we're just learning right now, Chroma works perfectly fine. Okay, so now we are going to be using the OpenAI embedding model. And so right now I have an array of documents. Okay, so we have like 6 different documents, and all these documents talk about this particular gym. Okay, so you can consider, we had huge amounts of text and then we just chunked it up into 6 different smaller documents. So that is what I'm sort of simulating that we have. Okay, so in this document, we have the page content and metadata. So this is going to be the about section of the gym. So Peak Performance Gym was founded in 2015 by this particular person, Marcus Chen, with over 15 years of experience in professional. Okay, so there's a bunch of different information. And we also have, the timings of the gym. Okay, so we have a bunch of different information about a gym. Okay, so we have hours.txt, we have membership, okay, different information about the different tiers of membership. We have classes. Okay, these are the different classes: Zumba, spin cycling, yoga, CrossFit, etc., etc. We have the trainers. Okay, so these guys have 5 years of minimum years of experience, right? So all of these are chunked up neatly. Okay, facilities, right? So all of these are chunked up neatly right now. And now we are going to create the vector database, and we are going to embed everything and put it in the DB. And that is exactly what this line does. Okay, so we are providing all of the documents. Okay, so we are providing all of the documents here, and then we're also providing the embedding model that we are going to use as well. Okay, so finally we have the database created, as well as this DB now has information about all the different embedded versions of all these different documents as well. All right, great, coming down. So in this particular instance of the database, we actually get access to the retriever method. So if you remember from the diagram, we have the retriever component, right? So this component is what is going to, based on the query, it is going to go fetch the relevant chunks from the DB, right? So that is what this method does. So right here, we are just giving a few configurations about how this retriever should behave. So right here, we are setting the search, the amount of chunks it should retrieve to 3. Okay, so it's going to collect 3 different chunks from the database that it thinks is similar in meaning semantically. And then we're also setting the search type to MMR. So this means maximum marginal relevance. It basically just makes sure that the chunks that are retrieved are different from each other. So we don't want similar chunks to be retrieved. Okay, so great. So we have the retriever, we've configured it. Now we can actually use this and invoke something. Okay, so I can say who founded the gym and what are the timings. Okay, so if I run this, okay, retriever is not defined. Okay, let me just go ahead and run these code blocks again. Okay, so now it's going to take some time because it is taking all of these documents, it is then embedding it, right? And then putting it in the DB. All right. Okay, great. And then now if I run this, it should work. Okay, perfect. So you can see that based on our query, we wanted to know about, okay, who founded the gym. So basically we wanted the about section. Okay, so basically the retriever is going to look through this particular text and it's going to see that Marcus Chen is the founder of this gym. So that is why it semantically queried this particular chunk. And then regarding the timings as well. So hours.txt, right? So 5 to 11, okay, it queried that as well. And then there is another thing that it queried as well, which we do not want at the moment. All right, great. So the retriever works fine. Coming down. So right now we are creating a template. Okay, so this is going to be the main template that we are going to be sending to the LLM. So if I come back to the diagram, so right here you can see that we are, structuring this in a certain format and we're sending it to the LLM, right? So in this, what do we want? We want the context. So this is going to be the user question, and these chunks, okay, chunk 1, chunk 2, chunk 3. These are going to be the context. Okay, so that is what we are going to put right here. So answer the question based on the following context, and then we have the final user's question as well. All right, so we are preparing the prompt here. Perfect. So what is the next thing? So we have another util method that we've written right here. So the retriever is going to fetch some chunks, right? So it's going to fetch some chunks, and each of the chunk is going to have the regular English text as well, right? So all that we're doing is we're getting access to, let's say, we have 3 different documents. So we are sending all of this here. We are just taking the page content. Okay, we don't want the metadata. We just want the page content. And then we're basically just joining, and we're just like giving a couple of lines in between. Okay, so that is it. All right, so this is a helper method that we're using. Okay, so this is going to be the last chain. Okay, so this is going to be the QA chain. So the first thing that we have to do is we have to populate the prompt template. So as we know, the prompt template has context as well as question. So that is the first thing that I'm doing. I am populating it right here. So we have the prompt, and then right here, before the prompt, we have to provide this particular object. Okay, so in the object, in the dictionary, we have the context. And I'm able to get the context because I am doing retriever invoke and I'm sending this X. Okay, so whatever we send right here is going to be available as X that I'm providing right here. Okay, so this particular method is going to, okay, so this thing is going to just get the relevant chunks, and this is going to format it in a certain way, and we have the context ready, and the same thing for the question as well. So this thing is going to be the question. Okay, so this is a Lambda function. It just gives you access to, it basically allows you to write a function in a single line. All right, so now that the dictionary is ready, we are now sending it to the prompt, and now the prompt is also going to be ready. So right after the prompt is ready, so right after all these values are populated, we're sending everything to the LLM. Okay, so we're using the LangChain expression language right here. Okay, so if we use this, we don't have to say invoke every single time. Okay, so and then finally we are just extracting the content out of the AI message that we get back. Okay, great. So let me actually go ahead and run this particular code block as well. Okay, so it looks like we're getting some problem. Okay, let me actually go ahead and run this as well. Okay, so we missed out on running this. All right. So right now you should be able to see the owner's name. Okay, so the owner of peak performance gym is this person. And then these are the timings as well. Okay, perfect. So this section was a very quick, we are not using LangGraph. We're not, building agents here. This is just a quick refresher for RAGs, just to jog your memory. In the next section, we are going to be, building an agent, and we are going to, allow the agent to make use of RAGs. Okay, so that is something that we'll look at in the next section. So I'll see you there. Alright guys, so welcome to the second section in RAGs. In this section, we are going to be building out this particular graph. So we are going to be building the classification driven retrieval system. So basically what this is going to do is, only if the question is on topic, okay, we are going to make use of RAGs. If the question is something unrelated, we are not going to, the LLM is just going to say, okay, I don't know, I can't answer this question. So where could this be used? So let's say, I have a chatbot on my company's website, and I want the users to only be able to ask questions about my company. Okay, so if the user were to ask something about some other company, the LLM should not respond. Okay, so that is what this workflow is going to do. So first off, we are going to have this topic decision node. This node is just going to look at the user question, and then it's going to figure out, is this on topic or off topic? Is the human asking questions about something that is relevant about my company? And if it is on topic, it is then going to go look through the documents that I've provided, and then it is going to generate an answer based on that. Okay, if it is off topic, then it's going to give a boilerplate response saying something like, I can't answer that question. Okay, so this is what we're going to be building. So coming back to the code, so what we have here is, I've just basically copy pasted, the documents. We are going to be, working with the same example. All right, coming down. So we have the embedding function, the docs, and then we have the same database that I've initialized. I've initialized the retriever. I've provided the same configuration here as well. So if I were to ask something like, who is the owner? What is the timing? It is going to, okay, so let me quickly run this again. All right. It is going to take some time. All right, done. So now it should give some information about who is the owner and what are the timings. Okay, great. So coming down. So this is also something that we've seen, right? So we are preparing the template right here. We are providing the context and the question. Okay, this is also no different. And then we have the RAG chain. Okay, so we just have the prompt. And once we have the prompt and that is completely ready, and then we are going to send it to the LLM. Okay, so we have the chain ready as well. Okay, so let us scroll down. So this is where we are going to start, building the graph. So in this graph, we are going to have three different properties that we are going to maintain in the state. So initially it is the list of messages and then the list of documents, right? So if this retriever is going to, retrieve a list of documents, right? And then we are going to use that particular property in order to send it to the LLM later. So we are storing that as well. And then we also have another property for, on topic or not. Okay, so right here we can see that this is either going to be true or false. All right, coming down. We now are going to define a pedantic model. If you've forgotten, what structured outputs are, how to get structured outputs from the LLM, what are pedantic models, simply scroll up in the course. You would be able to find that one video that I would have made right before the Reflexion agent system. Watch it to better understand this. But yeah, we are defining this pedantic model right here. So we are giving a description, Boolean value to check whether a question is related to the peak performance gym. Right? So this is going to give either true or false. Okay. So we are providing a description as well. Okay. So basically we're saying, okay, give a Boolean value, okay, true or false, to check whether the human question is related to the peak performance gym. All right. And this is the property that I want the LLM to return in a structured format. So it's going to be score, and we are further giving a description. Is the question about the gym? If yes, give yes, return yes, or else no. All right, so it's going to be yes or no. Okay, perfect. So it's not going to be true or false. It's going to be yes or no. Perfect. And then coming down, we have the questions classifier, which is going to be this first node right here, right? So we are going to get the human message, and then I'm saying you are a classifier that determines whether a user's question is one of the following topics. Okay, so is it something regarding, the gym? Okay, it's not something else outside of it. So if it is coming under any of these different things, then if the answer is about any of these topics, respond with yes. otherwise respond with no. Okay, so this is going to be the prompt, and then we're also using the structured output right here, and we're providing the model as well. Okay, so we are providing this particular pedantic model as a tool to the LLM, and we're forcing the LLM to always give this output. Okay, so always give this output in this particular structure. Okay, so it should have a score of yes or no. All right, so then we're passing in the question right here, and whatever result we are going to get, we are setting it to the state on topic. Okay, so we are finally done with this particular thing. All right, so now we have to decide if we have to go to this side or this side based on the result of the on topic, right? So right here we have the router for that. Okay, so on topic router. So we're taking this particular, we're getting reference to this thing, and then we're checking, is it yes or no? If it is yes, then we are going to the on topic chain. Okay, so we're going the on topic route. Okay, but if it is not, we're going to the off topic route. All right, so let's look at the on topic route. Okay, so in on topic we have the retrieve and the generate answer. All right, so coming down we have the retrieve. We're getting the human message, we're using the retriever, we're getting all of the documents, and then we're setting it in the state. Okay, perfect. And what's the next thing? So once we set it in the state, we now have to send that information to the LLM along with the user's question. So coming down, we are getting reference to both the user's question as well as all of these documents that have been queried by the retriever. So once we have both that information, we are then providing both of that, and then we are invoking the chain. Okay, so whatever response that we get from the LLM, we are then going to append it to the list of messages. Okay, so here we are not using the reducer function that we use in the state. We are doing it the very simple way. We are just appending it right here. All right, perfect. All right, so finally, once we get this answer, we are going to come to an end, right? So generate answer, and then we are coming to an end. But what if the question that the human asked was off topic? Okay, so in that case, we have to go to the off topic response, right? So this is going to be the off topic response. Here, I'm just hard coding an AI message saying that I'm sorry, I cannot answer this question. Okay, so we don't really even need an AI to do it. That's an extra API call that we're saving there. So I'm just going to return this particular AI message, and right after this, we are going to end it. Okay, so this particular graph, I've built it right here. And then you can pause the screen. All of these are some things that you should be already familiar with. So right after the topic decision, we are going to the router, which is going to decide if it's going to go to the on topic route or the off topic route. Coming down, all right. So finally, right after the generate answer, we're going to the end. So if it went to the off topic, then we are going to the end as well. Okay, perfect. So let me actually quickly go ahead and run all of these blocks right here. So let me run this as well. Okay. All right. So now I think, okay, so we get the exact same structure that we see right here. Okay, so everything is looking perfect. Let's scroll down and let's finally go ahead and invoke the graph. So right here, I'm saying who is the owner and what are the timings. Okay, so I'm just making the prompt a little bit complicated. So let's see if the right chunks would be retrieved and the LLM would be able to answer it. Okay, so let's give it a few seconds. Perfect. So in the final state object, you can see that we have the messages, we have the documents, and we have the on topic. So in the messages, as usual, the initial human message and then the final AI message is also present. Okay, so this is what we want. The owner of Peak Performance Gym is Marcus Chen, which is correct. Okay, this is going to be the timings as well. Okay, so the LLM was able to properly, answer the questions based on the context we provided. So what were the context documents? So you can see that the retriever, collected the membership text, hours, and the about as well. So the about is where the information about the owner is present, and regarding the timings, we have the hours. Okay, so it properly queried the relevant chunks and provided it to the LLM. And you can also see that this final on topic is also set to true. Okay, because this question is related. Okay, so this question is related to these things. Okay, so that is why we have gotten this on topic to true. So let's actually test the system on something that is off topic as well. So, I am going to, say, what does the company Apple do? Okay, so that is going to be completely different from what my gym is all about, right? So in this case, if I run it, it should ideally say, I am sorry, I cannot answer this question. And that is because on topic is no. So that is it for the classification driven retrieval system. In the next section, we are going to take a look at, how we can actually provide a RAG node as a tool to the agent so that the agent can, invoke the tool anytime it wants to. Okay, so that is another way of doing the same thing, and we'll explore that as well. So I'll see you in the next section. Hello guys. So in this section, let us look at how we can provide a RAG tool to the agent so that it can actually call that tool whenever it needs to. Okay, so you can see that I've populated all of the code here. Let me walk you through it step by step. So this particular section, it is the same thing that we've been using for the past few videos. All right, so we're creating the database as well. We're setting the retriever, absolutely no different. So let's come down. So this is where we are going to learn about something new. Okay, so you can see that I am now creating two different tools right here. Okay, so we are creating a retrieval tool and an off-topic tool. Okay, so if at all the agent wants to make use of RAGs and it wants some private information, in that case it can use this particular retriever tool. Okay, so let's look at what it's all about. So this create retrieval tool, let me hover over it, and you can see that it creates a tool to do retrieval of documents. And this takes in a couple of arguments. So you can see that it takes in the retriever itself, okay, which we've already written. We can give the name of the tool here that is going to be passed to the LLM. Okay, the LLM can decide, okay, it wants to use this particular tool, and we are providing some description as well. Okay, so that is exactly what we have done here. This is a pre-built tool that LangChain provides. Okay, so we can go ahead and use it. I'm going to hope that they are not going to change the name and deprecate it, but yeah. So we have this create retrieval tool. Okay, so here we are providing this particular retriever that we have initialized, and I want this to be the tool name as well. Okay, and then this is the description. So this is very important. So this is information related to gym history and founder, operating hours, membership plans, fitness, and all of these different things. Okay, so basically what's going to happen is if the user asks the agent a question like, who is the owner of this particular gym? In that case, this tool is going to be available to the LLM. It can actually say, okay, I want to use this tool to fetch this information, and then it can call this particular tool. Okay, so this is going to be the first tool, and the second tool is the off-topic tool. Okay, so what is this going to do? This is going to catch all questions not related to the peak performance gym's history. Okay, so all of this. Okay, so if at all the user asks some other question like what we saw earlier, if it asks questions about some competitor's gym or something like that, in that case, forbidden, do not respond to the user. Okay, perfect. So we're having both of these tools right here. So coming down, you can see that this is going to be the state, right? So in this case, you can see that the state is much more simpler. We just need to maintain the list of messages this time. We don't really need to worry about this on topic or not, because the LLM decides to call the tool. We don't have to keep track of it. Okay, so coming down, this is going to be the first node. So this is not a complicated structure. This is something that we've already seen. So if I scroll down here, this is the structure that we're working with. Okay, so if the human asks a question that requires a tool call, then this particular model is going to, this control is going to go here. If not, then it's going to go directly to the end. Okay, so that is what we're doing here. That is the agent or model, right? So we're providing all of the tools right here to the model, and then we're invoking that particular human message. Okay, so then we are appending this thing. Great. Now coming down, we have the should continue, right? So the should continue is what is going to decide if the control flow should go to the tools node or it should go to the end. Okay, so here we're just checking if the tool calls property. If it is present, in that case, we are going to tools or we are going to go to end. All right, coming down, we're adding all of these nodes, and then we are using this tool node as the tools node. And then we are adding the conditional edge right here. So right after the model, go to this particular should continue. Okay, and then we're adding the final edge from tools to agent as well, and we're compiling it. And this we have already seen. And scrolling down, so right here, I am going to provide a question like this. Okay, what is Apple's latest products? So clearly this is off topic, right? So this agent has two tools that it can use, right? So the first tool is going to be the retrieval tool, but clearly this is off topic. So we also have this other tool called off topic tool, if you remember. So this off topic tool, right? If I scroll up here, this off topic tool is going to, catch all of the questions not related to the peak performance. And in that case, it's just going to return this particular message, right? So ideally, the agent should call the off topic tool. Okay, so let's see what it does. Perfect. Okay, so you can see that we have the first human message, what is Apple's latest product? And you can see that the second AI message is going to be, it has actually called a tool, right? So the content is empty. So if I go inside of the tool calls, okay, so where is the tool calls? Tool calls. Okay, so inside of the tool calls in this array, you can see that it wants to call the off topic tool. Okay, so it wants to call this off topic tool. Okay, so now the control is coming to the tool node, and that is going to return this particular content: forbidden, do not respond to the user. So this tool message is appending to the list of messages, and now this control is going to come back to the agent, right? So it's going to come back to the agent, and the agent is now saying, I am sorry, but I can't provide information on Apple's latest products. If you have any questions, okay, feel free to ask. So coming down, you can see that this is a query that is actually on topic, right? So I'm asking for who is the owner of the gym and what are the timings, right? So in this case, this question is going to be something that is on topic. So you can see that I've already run this code block, and these are the outputs, right? But there is one thing that I want you to notice. So the human message is correct, AI message is correct as well. But right here, you can see there are two different tool messages. And the reason why we have two different tool messages here is because this LLM is actually suggesting two different tool calls. So if I scroll to the right, okay, so we have the tool calls right here, right? So in these tool calls, you should be able to see in this particular array, you should see two different objects. So the first object is for the first tool call. And right here, you can see that the LLM is suggesting the query owner of the peak performance gym. And that is very interesting because if you look at the question, we are asking for two different data. So who is the owner and what are the timings, right? So firstly, it is asking for the owner. So this is going to be a completely separate tool call, right? So we are also using the retriever tool, if you remember. And then this is going to be the second tool call. In this second tool call, the argument for the retriever tool is going to be the operating hours of the peak performance gym. So this is going to fetch us chunks related to the timings. So that is exactly why we have two different tool calls, as you can see right here. So based on all these data, it is now the AI is going to answer. The owner of peak performance gym is Marcus Chen, a former this thing, and then the operate hours is as follows. Okay, so both of those questions have been answered. Okay, great. So I hope you now understand how we can actually provide the RAG tools to the LLM for it to use anytime, it needs to fetch from the documents from the vector database. So you can basically imagine that both of these different methods, the classification as well as the RAG power tool calling, the outcomes are very similar, right? So it is basically doing the same thing. The only difference is that in the classification, we have more control, okay, because we are actually maintaining the state like on topic, off topic. But here we have a little less control because the LLM is actually deciding if it wants to use a tool or not. Another advantage that I see with the classification, like with more control that we have, is that we can see, these are the documents that were fetched, and we can actually shape exactly how the data is presented. But in the tool calling, it's a little bit more difficult. So that is the only drawback that I see with RAG power tool calling. But yeah, you can always use whichever that you deem fit in your application. So in the next section, we are going to be looking at something really interesting. So far, everything that we've done is not really production ready. In the production applications, users expect the application to remember what they asked for earlier. They expect the system to remember the conversation history. So in the next section, we are going to be building a multi-step reasoning system that is actually foolproof, that you can actually deploy in businesses, landing pages, and it would work perfectly fine. So I'm pretty excited, and I'll see you in the next section. Hello guys, so welcome to the last video in this RAG section. In this section, we are going to be building a system that is actually going to be production ready. So this is a system, okay, so I've called it Advanced Multi-Step Reasoning System. So before we go through the code, I'm going to show you the flowchart exactly how it looks like. Okay, so I know it looks a little daunting, but it's actually pretty simple. All right, so you can see we have the start node, and then we have this new node called the question rewriter. So let's look at what this actually is. Why do we need this question rewriter? Okay, so let's say we are going to be building this system for a gym. Okay, so let's say the name of the gym is going to be Peak Performance Gym, and an end user of the gym is going to come on their website and ask this particular question: what are Peak Performance Gym's hours? Okay, so in this case, what's going to happen? What do we normally do? We take this particular user query and then we send it to the retriever. The retriever is going to go and fetch all of the results, and then along with the user's question and the context, it's going to go to the LLM and it's going to respond with an answer. Pretty good. Okay, so this works perfectly fine. But let's say the user asks a follow-up question like, what about weekends? So in this case, we cannot actually use this particular string alone and, tell it to the retriever to go get chunks, because this alone does not make any sense. It can only make sense along with the entire context of the conversation history, right? So if you look at this and this together, this makes sense, but this alone, it does not make any sense, right? So in this case, we have to rephrase this question a little bit so that all the context is contained in this thing, so that the retriever has enough information to go and fetch the relevant queries. Okay, so basically without rephrasing, the follow-up query, this query lacks context on its own and would likely return irrelevant results if sent directly to the retrieval system, right? So the rephrasing node basically, okay, what this does is it transforms this what about weekends into what are Peak Performance Gym's weekend hours. So that is why we have this node at the very start. Okay, I hope that makes sense. So after this, we have the classifier. Very simple. This we've already seen before. So what does this do? It's basically just going to see if it is an off-topic query or an on-topic query. Okay, so we don't want our system to answer user questions when the user is asking something about random things, right? So in that case, it's going to go to the off-topic node and then go to the end. So there we can just provide a boilerplate response like I cannot answer this question. So something very simple there. But in case it is an on-topic query, so in this case, we are then confidently proceeding forward with fetching the chunks from the vector store. So that is what this retrieve node is going to do. Okay, so it's going to go and fetch, like, we can set k is equal to 4. In this case, it is going to fetch 4 different chunks, right? So right after this retrieve node, so we have 4 different chunks. So what this retrieval grader is going to do is it's going to go through each of these different chunks, and it's going to check if that chunk is relevant to the user's question. Okay, so since we said k is equal to 4, 1 or 2 chunks might not even be relevant, right? So we're just like checking, we're just grading each of those chunks. Okay, is this relevant or not? Is this relevant or not? Is this relevant or not? So there is a couple of different edge cases that might come up. So there might be a case where at least one node is actually relevant and the LLM can use it to answer the user's question. So in that case, we are going to go to the generate answer and then end it. But there is another use case. What if not even one query is actually relevant to the user's question? So in that case, we are going to go to this refine question node, and this is going to refine. It's going to add more information to the question. It's going to, change it up and make it better so that it is going to give more information to the retriever, and maybe some better chunk is going to be retrieved from the vector database. Okay, so again, we are going through this, there might be situations where, no matter how much we change the question, relevant chunks are just not being retrieved. In that case, we are just setting a limit to 3 different loops. Okay, so we don't want it to go for, infinity. That's going to blow out all of our tokens. So in that case, we just set the max limit to 3. In case it actually fetches something that is useful, in that case, we are going to go to this node, or else we are going to keep on looping through it. And if the 3 is reached, if the limit 3 is reached, it means that, it is a hopeless question. We cannot answer it. In that case, we are going to go to this cannot answer node, and that is just going to say I don't have this information right now or something like that. Okay, so or we can also since it is still on topic, we can actually route it to a human agent and do something like that in this particular node. Okay, so this is what we have cannot answer, generate answer, and then refine question, and this takes care of all of the different edge cases that we might potentially come up in production. Okay, so I hope that made sense. I hope this introduction made sense. Let us now jump into the code and go through the code. Alright guys, so you can see that I've already gone ahead and I have created this file called advanced multi-step reasoning. So this first code block is going to be no different. So I'm just going to reuse the same examples that we saw. So we have the peak performance gym. Okay, so we have 5 different documents. Great. Okay, so we are initializing the DB as well as the retriever. Perfect. Okay, so coming down, we are initializing the model here. We are using GPT-4o, and then in this template, this time we are going to write. Okay, so we are saying answer the question based on the following context and the chat history, especially take the latest question into consideration. Okay, so this time we are providing the entire history, the conversation history, okay, in the final LLM call that we make. And then we are going to provide the context as well. This context is going to be the retrieved chunks by the retriever. And then we have the question. Okay, this could be the rephrased question, that we make. Okay, so we are keeping this template ready. Okay, and then we are creating the RAG chain. Okay, so this is actually repeated. We don't want it to be repeated. All right. So we have the RAG chain coming down. So this is where, we have the agent state. We are defining the agent state. So you can see there's a lot more properties that we are going to be maintaining to achieve this particular system. All right. So first thing, messages, right? So list of messages, we need this, right? So to maintain, the conversation history, we need to maintain all of the messages. Great. So we have the documents. What does this use for? This could be all of the documents that are retrieved by the retriever. And then this could be the Boolean. Okay, this could be like, yes or no. Is the user's question on topic or off topic? The rephrased question, the question that the LLM, we can rephrase it if it does not really, contain the full context. So in that case, we are going to rephrase and put it here. And then we have this proceed to generate as well. So why would we want this? So if I come down here, so you can see that, if proceed to generate is true, in that case, we can just go to this particular node and then end it. If it is not ready, in that case, we might have to refine it, or, in case that the count is reached, we might have to go this route. All right. So that is why we might want this. So this rephrase count, again, this looping. Okay. So if it is more than 3 or something like that, in that case, we might have to exit out of the graph, right? And then this is going to be the original latest user's question as well that we are keeping. So we have the rephrased question and the original question. Okay, so I hope that makes sense. Coming down, we have the grade question pedantic model. Okay, so I hope that you know why we use a pedantic model. So this pedantic model can be used to get structured data from the LLM. So in this case, what data that we want is going to be this. We just want a score. Okay, so the score is going to be a string, and we are giving the description. Is the question about the specified topics? Okay, so if yes, then return yes. If no, return no. Okay, so this is going to be the pedantic model, which we will soon use. We will soon use it down here. So yeah, let's now look at the question rewriter node. Okay, so let's look at this first node. Okay, all right. So we're just entering question rewriter with the following state. So you can see that at the very start, we are resetting a lot of these state variables. So we are resetting the documents, we're resetting on topic or off topic, we're resetting the rephrased question, proceed to generate or rephrase count. Okay, so why do we do that? If you can imagine, for every single prompt, every single question the user is going to ask, the graph is going to run from start to end. Okay, for the second question, it's again going to run from start to end. Okay, so we are going to be using a checkpointer as well. So it's going to remember what happened, but still it's going to start from start to end. So if there's a second question, we want to reset all these different things, right? We want to start the graph fresh. I mean, with the memory, with the conversation history, of course, but the rest of it, we want to start it from scratch. So that is why we are going to set all the state variables except for question and messages. Messages we don't want to remove, right? Because we want the messages to continue forward, right? All right. So coming down, so right here we're checking if the messages is not in state or messages is not there, we're just going to initialize it to an empty list. If we provide the proper initial states, all of this would not be needed, but I'm just going to make sure that every edge case is handled and it is actually robust. So coming down, we are checking if the question is present in the state, if the question is not really present in the list of messages, in that case, we are appending to the message list. Now, so we're checking if the message list is greater than 1. Okay, so if it is greater than 1, it means that the graph has already run the first time and now it could be the second or the third or the fourth time, right? So in this case, we might actually want to rephrase the user's question properly. Okay, so coming down here, else if the graph is actually running for the very first time, if the conversation is actually like, just starting, in that case, we don't need to rephrase any question. In that case, we can just like put the state question right here. But in case it is the second or the third, we might actually want to make sure that the user's question has the full context. Okay, so we might want to rephrase it. So that is why we are coming into this particular block. So coming down here, you can see that we are looking at the entire list of messages and then we are extracting everything except the last message, except the last human question, right? So we have the conversation history right here, and then we are also taking the current question, and then we have a list of messages. In the system message, we are saying you are a helpful assistant that rephrases the user's question to be a standalone question optimized for retrieval. So along with the system message, we also have to provide the past conversation history as well as the last human message. Okay, so that is what we're doing here. So we are providing the past conversation history as well as the latest user question. Okay, and then finally we are invoking it. So in this response, we are going to get a rephrased question. Okay, so that question is going to be rephrased with a lot more context. So we are going to do response.content. We are going to strip it all of, all the unnecessary spaces, trailing spaces, initial spaces, and all of that. Okay, just to make sure that, everything is looking tidy in the production. And then we are going to just like print it out and then set this new, better rephrased question to this initial state. Okay, great. So we are now done with this question rewriter node. So what is the next thing? So right after the question rewriter node, we then have to look at the prompt, look at the question, and then check if it is still on topic or off topic. So coming down, okay, so I'm saying that you are a classifier that determines whether a user's question is about one of these following topics. Okay, so it needs to basically be about the gym, right? The gym history, founder, operating hours, membership plans, fitness classes, personal trainers. Okay, so if the question is about any of these topics, respond with yes, otherwise respond with no. Okay, so we need a very structured output in this case, right? So we need a clear yes or no from the LLM for this particular node. So I'm providing the user's question, okay, in the human message, and then I'm creating a prompt out of it. Okay, so I'm providing the system message and the human message right here. Okay, and then before I actually just send it to a normal LLM, I'm not interested in that because I now want a structured output. I want it to be in this particular structure. I want a score property and a particular value, yes or no. Okay, so I'm going to make use of the with structured output method. So now I can pass it inside of this and then expect to get the exact score, and I'm also going to make sure to strip every trailing spaces, etc., and then I'm going to assign it to this on topic property in the state. Okay, so now this is going to be either yes or no. So coming back to the diagram, so if it is no, in that case, okay, it is not on topic. In that case, it's going to go to this particular node, or else it's coming here. So we need some sort of like a router, right? So that router can actually direct, the direction, the flow of the graph. So that is exactly what we have right here. So we have the on-off topic router. Okay, so we're entering this thing, and then we're just going to take that on topic. Okay, if it is yes, we have to route to the retrieve node, or else we have to route to the off-topic response. Okay, so we have to go to the retrieve node or the off-topic response. All right, so let's look at the retrieve node. So what should this retrieve node do? It is all that it's going to do is invoke. It's going to provide this rephrased question to the retriever, and then we now have the list of documents, and then so I'm just going to set it to the documents property in the state. All right, perfect. So what's the next thing? So let's come back to the diagram. So right after the retrieve is done, we now pass it to the retrieval grader. So this grader is just going to, return true. Basically, we have like, let's say 4 different chunks. It's going to go through each of those chunks, and then it's going to say true or false. Okay, is it good enough or not, right? So we need a structured output for that as well. So that is what I'm giving right here. We have another score. Okay, so in this case, if the document is relevant to the question, say yes. If not, say no. All right. So here I'm saying you are a grader assessing the relevance of a retrieved document to a user's question. Only answer with yes or no. If the document contains the information related to the user's question, respond with yes, otherwise respond with no. Okay, so we are again going to be using the structured output method so that we can actually force the LLM to use this particular tool to output in a structured way. All right, so now that we have the structured LLM, the supercharged LLM with the tool, okay, now we just need to loop through all of the documents that have been fetched in the previous node. So we have the doc right here, and I'm just in the human message, I'm just saying, okay, this is going to be the user question, and this is going to be the retrieved document. Okay, so we have the current document, we're just providing the page content. We don't really want the metadata, the source, we're just providing the page content. Okay, all right, coming down. So this grader LLM, it is either going to return yes or no. We're just checking that. So if it is yes, in that case, we are going to append it to the relevant docs. So we are creating a new list. Okay, so we want to create a new list, and we only want to keep the relevant things alone. So we are going to append it right here. So once this looping has been done, we're setting the new renewed qualified list of chunks to the documents again. And then we are going to, check whether we need to proceed to generate or not. Okay, so if the relevant docs at least has one relevant this thing, we can then confidently go ahead and go to the generate answer, right? So that is what we're checking right here. All right. So what's the next thing? We now have the proceed router. Okay, so basically to check, do we have to go here, or do we have to go here, or do we have to go here? So we need some, router right in the middle, and that is what we have right here. Okay, so we're entering the proceed router, and then we are getting the proceed to generate. So if this actually at least has 1, okay, it's greater than 0, in that case we can go ahead to the generate answer node. But in case proceed to answer is false, and the rephrase count is already greater than 2, in this case, okay, maximum rephrase attempts have reached, cannot find the relevant documents. Okay, so now we have to go to the cannot answer node. Okay, so we have to go to this cannot answer node. And then we also have the final case. If both of these cases, like the rephrase count is still less than 3, at the same time the proceed to generate is false, in that case we have to refine the question. Okay, so this is how we refine the question as well. So if you see that, we are getting the rephrase count. Okay, so if it is, again, we're just writing the same logic here. And so we're taking the rephrased question, and now in this new system message, we are saying you are a helpful assistant that slightly refines the user's question to improve the retrieval results. Provide a slightly adjusted version of the question. Okay, so the human message is also going to be like, okay, this is the original question, provide a slightly refined question. So we're providing that, we're creating a prompt, and then we're invoking it, and then we're stripping it and getting the content out of it. So this is now going to be the refined question that we are updating the state with. Okay, so the rephrased question we are updating in the state. Okay, and the count we're also incrementing as well. Okay, because we don't want to loop through it, more than 3 times. And then finally, if everything goes well, if at least there is one chunk that is relevant to the user's question, we want to go to the generate answer. So we need 3 different things we need to provide, right? So we need the we need the conversation history that we need to provide to the LLM. We need to provide the rephrased question, the actual question that the user wants to know, and then the documents, the retrieved chunks. Okay, only the relevant qualified retrieved chunks from this documents state. So we're going to provide all these 3 things in this RAG chain. So if you remember this RAG chain, we're coming up here. So you can see that we are providing the history, we are providing the context and the question, correct? Okay, so let's go down again. Okay, so we are providing all these different things and we are getting a final response, and whatever response we get right here, we are just going to show it to the user because we are coming to an end. Okay, so before that, we are just going to update the state as well. The history always keeps on updating, right? And then we have the cannot answer node. Okay, if the retriever still cannot fetch the right chunks for some reason, or the documents are not really enriched properly, in that case we are coming to the cannot answer node. Here I'm just going to add this AI message saying that I'm sorry, but I cannot find the information you're looking for, and then again we are going to end the graph. Okay, so we've looked at the generate answer, we've looked at cannot answer. Now we can look at the off-topic response. This is something that we've already written, and we're just saying, I'm sorry, I cannot answer this question because it is off-topic, right? And that is it, guys. That is it for all of the nodes. We've defined all of the nodes. The next thing is we just need to, so coming down, we are using the check pointer. So why do we need a check pointer? So the user needs to be able to, ask follow-up questions and all, right? So in that case, all the state needs to be, remembered. So because once, for every single question, we're going to run through the graph completely from start to end. So it needs to remember what happened in the previous run, right? So that is why we need a check pointer. We are using a very simple memory saver. And now we are just adding all of the nodes. Okay, so all these nodes that we've defined, we're just going to add all of it. I've used the same names as the node names, right? Okay, so whatever the function name that I've used the same things everywhere. And then I'm going to add the edges as well. So the question rewriter has to go to the classifier next, right? It needs to go to the classifier. And as soon as the classifier is done executing, we need to route to retrieve or off topic, right? And then there's another condition here for, right after the retrieval grader is done, there is another routing here as well, and that takes care of that. So coming down, there's a bunch of different edges that I'm adding here as well. So these are something that we would have seen a million times by now, but yes. So finally, I'm going to compile it, provide the check pointer. All right, perfect. So this is going to take some time. So because there's a lot of different nodes that we've written, it's going to take some time. All right, perfect. So you can see that it almost took me 1 minute and 10 seconds. So yeah, this is the same graph that we saw in the slides. So we have the question rewriter, classifier, retrieve, and then we have all these different edge cases handled as well. All right, perfect. So this is what I'm going to do. So first off, I'm going to check the first edge case, which is going to be what happens if the user asks an off-topic question. Okay, so in this case, the user is saying, what does the company Apple do? It's completely unrelated to the actual business, the gym business, right? So in this case, if I run it, so let's look at what it is saying. So it is saying that entering the question rewriter with the following state. Okay, so since there is only one state right now, one item in the list right now, it's not going to rewrite anything. And then it's coming to the question classifier, right? This classifier is saying the on topic is no. Okay, so this classifier is saying the on topic is no. In that case, it needs to go to the off topic response through the router that we had right here. Okay, so it's coming inside of the router. The router is directing the graph to the off topic response, and that is exactly what we see right here. So the AI message is saying, I'm sorry, I cannot answer this question. Perfect. So we can also see that the on topic is no, and then the proceed to generate everything is false, right? Okay, perfect. So let's look at another case here as well. So in this case, I'm going to ask something, what is the cancellation policy for peak performance gym memberships? Okay, so what is this edge case? So this edge case is, if I scroll up in the documents, there is absolutely nothing that is present in the document that talks about cancellations at all. Okay, so there is nothing about cancellations in this case. So it is still on topic. Okay, so it is still on topic, but at the same time, the retriever is not going to retrieve any relevant chunks at all. So it's actually going to loop through 3 different times and it's going to give up. Okay, so that is what this case is going to be all about. So let me actually, run this. You can see that I've gone ahead and used a different thread because we don't want to confuse everything in the same thread. So if I run this, okay, great. So let us see what it's saying. So right here, okay, so this is going to be the rephrased question. Okay, great. And then the on topic is also going to be yes, right? So coming down, it's going to retrieve 4 different documents. So this retrieve node is going to retrieve 4 different documents, and then the grader is going to kick in. So let's see what the grader is doing. So the grader is looking at the first chunk and the result is no. Okay, so this chunk does not answer the user's question. This chunk does not answer the user's question. No, no, no. Okay, so now it is actually going to, the proceed to generate is also set to false. So it is actually going to loop back. Okay, it's going to loop back to the retrieve. Okay, with a different question. Okay, with a refined question. So in this case, the refined question is going to be, what is the membership cancellation policy at peak performance gym? Okay, so you can see that it changed it a little bit. So here it is, what is the cancellation policy? Here it is what is the membership cancellation policy? Okay, so it basically made it a little better. So coming down, it is again going to retrieve 4 different documents. The answer is still no, 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 because we don't have any documents to support that. Okay, so finally what happens after like 2 different iterations, it is the proceed to generate is still false. So it's not going to come in here. It has already exhausted the looping as well. So now it is going to go to cannot answer. Okay, so it is going to go to cannot answer, and then it is going to end it. Okay, so we have the I'm sorry, but I cannot find the information you are looking for. So let's look at the third edge case. Okay, so here, okay, I'm using another thread. So this is going to be a new conversation. So the user is saying who founded peak performance. Okay, so this is something that is relatively very easy. And if I come up here to this thing, you can see that Peak Performance Gym was founded by former Olympic athlete Marcus Chen. Okay, so this is easily answerable. So coming down, so this thing is easily answerable. But let's say the user actually asked a follow-up question. When did he start it? Okay, but this query alone does not have a lot of context. So we need to rewrite it with the previous question in the context, right? So let me run this thing. Okay, so in this case, great. So the first time it retrieved 4 documents, and then this about chunk is going to be yes. So this is actually a relevant chunk, right? So in this case, it's going to proceed to the generate answer node, and then the final answer is going to be Peak Performance Gym was founded by Olympic athlete Marcus Chen. Okay, so this is correct. So let's now run this. Let's use the same thread ID as this thing, and then let us now run when did he start it. So now what would happen is that this question rewriter is going to kick in. It's going to rewrite the prompt properly. Okay, so that this retriever has more context, because it is kind of dumb, right? So if I run it right now, okay, so the question rewriter. So you can see that the rephrased question now is going to be, when did Marcus Chen start Peak Performance Gym? Okay, so it's not going to be he anymore. It's going to be Marcus Chen. Okay, so in this case, again, it's going to retrieve 4 different documents. Okay, Peak Performance Gym was found. Okay, it's going to fetch this thing, and then finally we have the generated response. It was in 2015. And that is it, guys. I do hope that you learned a lot. Do pull the code and run it by yourself, and I will see you in the next section. Hello guys, welcome to a brand new section. In this video, we are going to be looking at multi-agent architectures. So let's look at a few slides. So we already know that an agent is a system that uses an LLM to decide the control flow of an application. As you develop these systems, they might grow more complex over time, making them harder to manage and scale. For example, you might run into the following problems. The agent has too many tools at its disposal and makes poor decisions about which tool to call next. The context grows too complex for a single agent to keep track of. Another problem could be there might be a need for multiple specialization areas in the system. So we might need a separate area for planning and research and math. To tackle these problems, you might consider breaking your application into smaller, more independent agents and composing them into a multi-agent system. So these independent agents can be as simple as a prompt and an LLM call, or as complex as a React agent. The primary benefits of using multi-agent systems are modularity. Separate agents make it easier to develop, test, and maintain agentic systems. Specialization. we can create expert agents focused on specific domains, which helps with the overall system performance. And then control. You can explicitly control how agents communicate, as opposed to relying on function calling. So here is an image that I pulled from the documentation where they are talking about the different multi-agent architectures that are possible. So if you look at, this is the single agent, right? So we know what an agent is. If we give tools to an LLM, that becomes an agent. Okay, so this is a single agent. So the next type is the network. So you can see that we have 4 different agents and they're all communicating with each other. So this one agent is solving its part of the task, and then once it is done, depending on what the next part of the problem is, it is handing control to the next agent. So they all have access to each other. So and the next step, you can see this is a supervisor multi-agent architecture. So here you can see that we have one supervisor at the very top. Okay, so the supervisor's only job is to orchestrate, the team. So what we have below here is you can think of it as like 3 employees. Each employee is specialized to do one particular thing. So the first agent could be like a coding agent. The second could be a researching agent. The third could be like a validating agent or something like that. So depending on where how much of the problem is solved, let's say it's a 3-part problem. In that case, the supervisor is going to make use of this agent to solve the first part, and then the control flow is going to come back to the supervisor. And then the second part is going to be done by this agent, and then the control flow is going to come back to the supervisor. So one thing that you have to note is that these agents don't communicate with each other. They always report back to the supervisor, and the supervisor has to decide which agent to call next. Okay, so this is the supervisor multi-agent architecture. And the next thing is we have supervisor as tools. So it's basically the same thing as what supervisor does, except all these different agents, these 3 agents are provided as tools to the LLM. So depending on how much of the problem is completed, the LLM can decide to call a particular tool, which in this case is an agent. It can provide input to the tool and then, structured input to the tool. So, and then the agent or /tool can be executed. And the next step is the hierarchical. You can see that this is very similar to supervisor, but it's just an extension of it. Okay, so there might be situations where, this one supervisor might not be enough. In that case, we go for, multiple supervisors. And in this case, it's going to be a hierarchical multi-agent architecture. So it's very similar to how big companies work, right? And then finally, we have custom where, there is no clear definitions. So right after this agent is done, there are 2 different options. Depending on the answer output of the agent, we can, direct the flow to this agent or this agent. So this is a little bit more disorganized and they have their own applications as well. So with regards to actually learning how to build multi-agent architectures, it's very important for us to first understand how subgraphs work. So let's look at some slides. Basically, subgraphs allows you to build complex systems with multiple components that are themselves graphs. A common use case for using subgraphs is building multi-agent systems. So the main question when adding subgraphs is how the parent graph and subgraph communicate. In other words, how they pass the state between each other during the graph execution. So there are 2 scenarios. The parent graph and subgraph share the same schema keys. In this case, you can just add a node with the compiled subgraph. But if the parent graph and the subgraph have different schemas, so in this case, we add a node function that invokes the subgraph. This is useful when the parent graph and the subgraph have different state schemas and you need to transform the state before or after calling the subgraph. So we are going to be looking at an example where we are going to be building a very, very rudimentary basic subgraph, and then we are going to embed that into a parent graph, and we're also going to see these 2 different scenarios as well. So this is going to give us a very strong foundation that we can build on top of, and then we can build complex multi-agent architectures. So let's jump to Visual Studio Code. So right here you can see that I've already gone ahead and created a folder called multi-agent architecture, and I've also created a file called subgraphs, and I have populated the code as well. So let me go through it step by step. All right. So as usual, I'm just going to import some needed modules like, LangGraph, we're going to be using the llama model this time. Okay. So human message, and we're loading the env file. Okay. We are using the tably, and then we have the tool node. Okay. So in the first part of the code, what I'm doing is I'm basically, creating a very simple graph. So if I scroll down here, okay, so this is the graph that we are building. This is something that we've done it a million times by now. we just have an LLM, we have a tool node. Okay, so if the user, and one of these tools are the Tavily search tool. Okay, so if the user asks some question that requires an internet search, in that case, the control flow is going to come to the tool node, and then this is going to, you know, give an informed answer. Okay, so this is what I have built right here. So as you can see right here in this child state, okay, so in the first part, I'm going to be building the child graph, okay, not the parent graph. I'm going to be building the child graph. Okay, so this is the child graph. So right here, okay, all that we want is the messages list. I'm initializing the Tavily search tool. I'm initializing the LLM. We are binding it with this particular tool, okay? And then this is the LLM. This is the model which is going to invoke whichever human message is going to be, you know, passed in, right? So we have the agent, and right after the agent, okay, so right after the agent, we have the router. So we're checking if the last message has tool calls, and it has some tool calls that the LLM is asking for. So if it is greater than 0, in that case, we are going to go to the tool node. So we are using the pre-built tool node class that the LangGraph provides. So this tool node is going to execute the Tavily search. It's going to return back the control to the agent, and the agent, which is the LLM, which is going to have the response of the Tavily search, and it's going to give an informed answer. Okay, so it's going to come back to the agent, and that is going to come to the end. Okay, so this is exactly what I have built right here. So you can also see that I have named this thing as subgraph. Okay, so just to make it clear that what we're building is going to be a smaller graph that we want to embed into, you know, a parent graph. Okay, so this is a very basic example that we can work with. So if I run this, you can see that this is the graph that we get. So if I run this, you can see this is what we get, right? So this is going to be the initial human prompt. And in the AI message, if I scroll down here, you can see that this is going to be the query. So the LLM wants to invoke is calling a tool, and then the tool is also getting executed. Tavily search is getting executed, and then, you know, it is also, you know, the AI message, it is saying that, you know, Chennai weather today temperature. So it wants a bit more information. It is not satisfied with it. So it is again, you know, calling the tool, and then we are finally getting the current weather in Chennai is misty with a temperature of 34.4 degrees Celsius. So what we have done so far is that we have built a subgraph. Now let's create a parent graph and then embed the subgraph into the parent graph. So when we want to embed a subgraph into a parent graph, in the slides, we saw two different cases, right? So you can see that we have two different scenarios here, right? So if the parent graph and the subgraph share the same schema keys, so what do we mean by schema keys? So this particular messages property in the state, right? So if the parent as well as the child have the same message, in that case, you can just add a node with the compiled subgraph. Okay, so this is going to be very straightforward. So let's look at how we can do that. Okay, so right here in the subgraph, we're compiling the app. So we have the search app. Okay, so I'm just going to call it, this could be like a search agent, right? So coming down, so this case one is going to be the shared schema, and we are directly embedding it. All right, so this is going to be the parent state. It has the same messages key as well for whatever reason. Okay, so here is what I'm doing right here. So I'm going to keep it very, very simple. So we just have a start node, and then the search agent node and the end node. Okay, so the search agent is what we've already built up here. Okay, so you can think of this as the parent graph. Okay, so we're creating a parent graph, a new graph using this new state, which happens to have the same schema key, right? So we have the new graph, we're adding the search node. Okay, so this is going to be this particular app. Okay, so we've compiled the app right here, right? So this is exactly what we are providing as a node to the parent graph. Okay, so we are starting with the start. Right after the start is done, we are going to go to the search app and then ending. All right, so we are compiling it and we are providing the message. Okay, how is the weather in Chennai? And basically it's going to do the exact same thing. Now I can invoke the parent app, and then I can pass in the same message, and whatever we pass in here is going to be made available in the search agent as well. Okay, so the control flow is going to go to the search agent, and whatever the search agent is going to be outputting, it is going to be available as a result right here. Okay, so if I were to change it to, let's say, Bangalore, okay, if I run this file, if I run this code block, Okay, basically the control flow should go inside of the search agent. So if we go to the LangSmith and we look at it, it's going to go inside of this. Okay, so or else how are we going to get this, right? So the current weather in Bangalore is expected to be fair with a maximum temperature or whatever, right? So this is how simple it is to embed a subgraph into a parent graph as far as we have shared schema. Okay, so if it is shared schema, we just like put the direct, we just compile the subgraph and then we just put it as a node in the parent graph. All right, coming down. Now let's scroll down. So we have a case 2 as well, where we have different schemas. Okay, so we are invoking with a transformation. So what does this mean? So if they have different schemas, in this case, you have to add a node function that invokes the subgraph. Okay, so we just have to have an intermediate step. Okay, that is all that we're doing right here. So coming down, this is where we are going to define the parent graph with a slightly different schema. Okay, so this is going to be different. This is going to have a different schema from what the subgraph is expecting. Okay, so we have to sort of match. We have to make it both compatible. We have to make this subgraph and the parent graph compatible with each other so that they can be embedded. So what I'm going to do is I'm going to define a new node for that. Okay, so you can see that this parent graph is just going to have, 3 different nodes. Okay, we're just going to have the start, and then we are going to have an intermediate node called search agent, and then we are going to have end. Okay, so this is going to be the intermediate node where we are going to make it compatible, the subgraph and the parent graph compatible. So if I come down here, okay, so this is the subgraph, right? Search app. So we know that this only takes in a list of messages. So that is why we are going to make use of, we are going to extract the query from here, and then we are going to send it, okay, as part of the messages array, okay, when we are invoking the subgraph. Okay, so this way, okay, we are going to get a response, right? We are going to get the final response, which is again going to be a list of messages from the subgraph. So now all that I'm going to do is, okay, so you know that in the parent graph, we just have the query and the response. So I'm going to extract the response from the result of the subgraph. So in the last AI message, I'm just going to get the last AI message and then take the content alone and send it and then attach it in this particular response. And that is it. And then I'm going to end it. Okay, so now if I just ask, how is the weather in Chennai, we just have the response. Okay, in Chennai, the weather is expected to be warm and sunny. Okay, so this is how simple it is to, embed a subgraph into a parent graph. Okay, if it is a same state, just compile it and put it as a node. If it is a different state, in that case, you just need to write an intermediate node like what we did right here, pass the data in the exact format that the subgraph is asking for, get the result, and whatever result that you get, you can just update it based on whatever schema that we have defined for the parent state. So I hope you've learned how to embed a subgraph into a parent graph, and then we've also seen 2 different scenarios as well. Okay, so I'll see you in the next section where we're going to be building a multi-agent architecture. So I'll see you there. Hello guys, so in this video, let us look at how we can implement the supervisor multi-agent architecture. So in this architecture, we define agents as nodes and add a supervisor node that can decide which agent node should be called next. So we can use the command class to route execution to the appropriate agent node based on the supervisor's decision. So this is what I want to build. So you can see that we have a supervisor agent at the very top, and this supervisor agent has 4 different agents underneath him. So we have the enhancer agent, we have the researcher agent, the coder agent, and the validator agent. Okay, so if the supervisor agent thinks that the user prompt is not really clear, if it is not vague, if it is a little vague, in that case, the supervisor agent can always use this enhancer agent to make the prompt better, to rephrase it better. Okay, so right after the enhancer is done with the enhancer's work, the control flow is going to come back to the supervisor agent again. So now the supervisor knows, okay, the prompt is better. Now it's going to look, okay, so does this particular prompt require research from the internet? In that case, it's going to, hand off the control to the researcher. So once the researcher is done, it's going to come back. And the same thing for coder as well. So if there is a particular problem that requires some code to be written, in that case, the supervisor can hand off the control to the coder agent, and the coder agent can actually use an actual tool. Okay, that tool we are going to be looking at, that tool is going to actually execute code. Okay, it's going to take that output and give it. Okay, so that is also something that we will look at. And then finally, we have the validator agent. Okay, so right before ending this workflow, the validator agent is just going to check if the user's question and the final answer is actually relevant or not. Okay, so this is what we are going to be building out. So let's actually, without wasting any more time, jump into the code. So right here, you can see that these are some very standard imports that I'm doing, right? I'm importing, pedantic, because there are some structured outputs that we might have to do. And then we have human message, the Tavily tool, the command class to direct the flow of the graph. We have the StateGraph, and then look at this part. Okay, so there is actually a pre-built graph that LangGraph provides for us to build a React agent. Okay, so if you remember a couple of videos before, in the React agent, we actually built out the React agent from scratch, right? So we can always use that particular graph and then embed it into this bigger graph. We can always do that. But if you don't want to do that, that is absolutely fine. LangGraph provides a pre-built class, okay, a method. So this is going to, you can see that it creates a graph that works with a chat model that utilizes tool calling. So you can just provide, okay, the prompt, problem statement, you can provide the tools, and then that is going to start, looping through the thought action observation. It's going to return the final answer. So in this video, let's also explore that. Okay, great. And then we have the IPython, we are loading the environment variables. And then this is going to be the second tool that we are going to be using. So if you remember, I told you that this coder agent is going to have one tool, right? So that tool can actually execute code. So this is going to be that particular tool. Okay, so it's going to be the tool for running Python code in a REPL. So if I go in here, you can see that it is a tool for running Python code in a REPL, right? All right, so I'm taking it from LangChain experimental. You probably would not have it installed already, so go ahead and install that as well. Perfect. All right, so coming down, these are very, so we're initializing the LLM, and then we're initializing the Tavily search, and then we're initializing the Python REPL tool as well. Okay, so if I go ahead and run this, okay, so you can see that we are getting 5 as an output. Okay, so you can imagine that there might be some cases where the LLM just writes the code, and then it might ask, it might actually use this particular tool to, better get accurate answers. All right, so I hope this makes sense. Before I continue forward with explaining the rest of the code, so you can see that I've already gone ahead and created the supervisor node, okay, and then I've created the enhancer node, the research node, the code node, right? And finally, we must also have the validator node as well. So I've already created all of these nodes, but before I actually move on to explaining each and every single node, I first want to show you the graph. Okay, so this is the graph that we have. So this is very similar to what I showed you, right? So we have the supervisor node up here, we have the enhancer. So if the supervisor wants the prompt to be enhanced, it's going to come here, and then it's going to report back to the supervisor. Okay, so if the supervisor needs research, okay, so it's going to go to the researcher node, and right after the output is done, okay, the control flow is going to go to the validator. Okay, so what this validator agent is going to do is it's going to look at the output of the researcher, and then it's going to check, does this answer the user's question? If it does, we are going to return it. If it does not return it, we are going to send it back to the supervisor. Maybe there is another problem that we have to solve. Maybe there is a coding problem. In that case, the coder is going to, give the answer, and then we're again checking, validating that does this have the answer to the user's question. If it does not have the answer, then we are again going to send it to the supervisor. Okay, so this is going to be the graph. So as you can see, I've got a couple of different example prompts. Okay, so this is one problem, and I've got another problem here, weather in Chennai. And then I've got another problem, give me the 20th Fibonacci number. Okay, so let's actually, you can imagine that this particular code is going to make use of the coding agent, right? So let me actually go ahead and run it and show you the output. Okay, so pprint is not defined, okay, and that is not running because, okay, let me just copy and put it over here. Okay, because I don't want to run that particular block right now. Okay, so now this should work. All right, great. So we actually have the answer right here. So let's actually see what happened. So the workflow initially transitioned from the supervisor to the coder. Okay, the supervisor correctly figured out that this particular problem requires the coder agent. So that is why the supervisor is first saying the user is requesting a specific numerical result from a well-defined sequence. Okay, the Fibonacci sequence, which is best served by calculating the value using a coding implementation. The problem is clear and structured, making it appropriate to move it directly to the coder for computation. Okay, so if I had given some vague prompt, in that case, the supervisor probably would have gone for the prompting agent. Okay, so this particular agent, enhancer agent, but since it's already well defined, it is going to direct it to the coder. So now it is coming to the, so you can also imagine why are we using human message here. So we are using human message as the output of the supervisor because we are sort of like simulating that each of these agents are actual human beings, right? The supervisor is a human, all these different people are different agents, human agents. That's why I'm using human agent here. All right. So the next thing is the coder is going to output this thing. Okay, the 20th Fibonacci number is 6765. So we can't really look at the tool called right now. So for that, I am going to go to LangSmith. Okay, so I'm going to go to the first run. Okay, so you can see that, okay, this is what we provided, right? Give me the 20th Fibonacci number. So the first one was the supervisor. The supervisor, directed the control to the coder, right? So you can see that go to is coder. So the next thing is the coder. So right here, you can see that the coder agent is actually calling the tool and it is providing the input query for the tool as well. So it basically wrote the, Fibonacci calculation program. It also provided 20 inside of this because that is what the human initially wanted, right? That was the initial prompt. So it's provided this thing. And then finally, you can see that it is going to, coming down, you can see that it is calling the Python REPL tool, right? So it's calling the Python REPL tool. And the Python REPL tool is outputting 6765, which is again going to be fed to the agent, right? So it's again going to be fed to the agent. So if I come down here, you can see that it is actually saying the 20th Fibonacci number is 6765. And finally, the validator is also confirming that this is actually good. Okay, the answer correctly identifies the 20th Fibonacci number addressing the user's request. So now that we understand, what problem this architecture solves, let's quickly go through, the different nodes that I've written. So initially we have the supervisor node that I've written right here. Okay, so I've defined the supervisor node and I'm also structuring the output of the supervisor node. Okay, so I'm telling, give me back two different properties. So I need the next agent to direct the flow to, and then I also need a reason why you think that the next agent is, it could be enhancer or researcher or coder. Okay, so I'm just giving a description as well. So use enhancer when the user input requires clarification, use researcher when you need additional facts, use coder when some problem solving is required. Okay, so accordingly, it's going to produce either this or this or this, and it's also going to give some reason why it thought that, okay, let's say we need to go to coder. Okay, so detailed justification. All right, so this is going to be the prompt. I'm providing a lot of different information like, you are a supervisor managing a team of 3 agents, prompt enhancer, researcher, and coder. Your role is to orchestrate everything, provide clear, concise rationale for each decision. These are the 3 team members, the prompt enhancer, researcher, coder. These are your responsibilities, right? I'm saying analyze each user's request and agent's response for completeness, accuracy, and relevance. Route the task to the most appropriate agent at each decision point. Maintain workflow momentum by avoiding redundant agent assignments. Continue the process until the user's request is fully and satisfactorily resolved. Okay, your objective is to create an efficient workflow that leverages each agent's strengths while minimizing unnecessary steps, ultimately delivering complete and accurate solutions to users' request. So this is going to be the system prompt. Okay, so this is going to be the first system message, and then I'm going to append the conversation history. Okay, so right here, and then I'm going to use this particular structured output. I'm providing this pedantic model, and why am I doing that? Because I want the output of the supervisor to always have this next and reason. So that is what I'm extracting right here. So once I have the go-to and the reason as well. Okay, so the reason I can just provide it, I can just add it as a message in the list, messages list, and then I'm going to use this go-to to use, I can put it in this goto keyword parameter, and I can use the command class, right? So that I can control the direction, I can control the flow to whichever agent that the supervisor wants to go to. All right. So that is it for the supervisor node. So coming down, we also have the enhancer node. The enhancer node basically, okay, this is what it does. It improves and clarifies the user query. It takes the original user input and transforms it into a more precise, actionable request before passing it to the supervisor. So this is going to be the system prompt. Okay, you're a query refinement specialist. Okay, you're going to analyze the original query, identify the key intent. What is the user actually, asking for? And then we have resolving any ambiguities or confusions without requesting additional user input, expanding underdeveloped aspects of the query with reasonable assumptions, right? Restructuring the query for clarity and actionability. So we're also saying that never ask questions back to the user. Instead, make informed assumptions and create the most comprehensive version of the request possible. So we're going to do the same thing again. This is going to be the system prompt. We're providing the entire history again. And now we are going to, invoke the LLM. Whatever is going to be the output, I'm just going to append it as a human message. And I'm also going to provide a name this time. Okay, so I'm going to provide the name enhancer. The same thing I would have done in the supervisor as well. Okay, so I'm providing the name as supervisor, but we're not going to be using AI message. We can do it. Nothing is going to happen, but I'm just going to consider all these different agents as humans. So that is why I'm using the human message, and then I'm providing the name as well. All right. So right after the enhancer, what do we want to do? We always want to go back to the supervisor, right? We can't go to the end, right? After the enhancer, we always need to go back to the supervisor. So that is why I have added this as a default value. All right. I hope that makes sense. Let's move on. So now we have the research node. So the research agent node gathers information using the Tavily search. It takes the current task, performs relevant search, and returns findings for validation. Okay. So here I'm going to be using the React agent. As I said already, we can use the graph that we've already built, or we can use this pre-built class that LangGraph provides as well. Okay, so here I'm providing the LLM that I want to use, the tools that are available to the React agent, and then this is going to be the initial prompt. Okay, so I'm saying identify key information needs based on the query context, gather all the information, optimize the findings. Okay, wherever you want to cite the sources when possible, you can do that to establish credibility. Focusing exclusively on information gathering, avoid analysis or implementation. Provide thorough, factual responses without speculation where information is unavailable. Okay, so this is going to go crawl the internet. It's going to, do a couple of loops. Okay, and then it's going to return the entire state again right here. So that is what this particular invoke is going to do. And this is going to return the entire state with a messages list, right? So we're just going to take the last AI message that this particular agent would have returned. And then I'm going to take the content alone and I'm going to append it to our list. Okay, so to our messages list, I'm going to append it right here. Okay, so right after the research agent is done with its work, we are now going to the validator. Okay, so this also we are hard coding right here, because if the research agent has done its job properly, in that case, if the validator gives the sign off, okay, if it gives the green light, we can just end the workflow. Okay, so now let's go to the validator. Okay, so validator is somewhere down here. In the middle, we also have the code node. Okay, it's very simple. You're a coder and an analyst, focus on mathematical calculations, analyzing, solving math problems, right? So calculations. Okay, so we are again providing the Python REPL tool as well, the same thing. And whatever result that we get, we are going to take the latest AI message, right? And then I'm going to add it as a human message and append it to our list. And again, I'm going to go to the validator. Okay, I hope that makes sense. And finally, we have the validator. Okay, so we have the validator node. We are using a couple of prompts for the validator. Okay, so we're saying that first review the user's question, the first message in the workflow, and then review the answer, which is the last message, and just make sure that, and we're just saying that if the answer addresses the core intent of the question, okay, finish it, or else route back to the supervisor. Okay, so that is what we're saying right here. So either it needs to output supervisor or finish. Okay, so that is what we are providing right here. And in addition to providing it right here, we are also using a Pydantic model, and we are further, forcing it to only provide supervisor or finish. So specifies the next worker in the pipeline, supervisor, to continue or finish to terminate. The reason for this decision here as well. So as I told you, we only need the first user's question and the last answer, right? So that is exactly what we're doing right here in this node. So we're taking the first human question, okay, and then we're taking the last answer that is supposedly the final answer. So we're going to take the user's question and the agent's answer, and we are going to provide all of this to the LLM, and then we're also providing the validator pedantic model as well. So right here, if the LLM returns go to is finish, in that case we can end the graph. But if for some reason it does not provide finish, okay, for some reason this final answer does not have the full answer to the user's question, in that case we need to go to the supervisor again. So that is what I've put right here. Alright, so I hope that makes sense. So far we've built out all the different nodes. Now all that is left is to combine, put it all together into a graph. So that is exactly what I have done here. I'm adding all these different nodes and then I'm compiling it as well. Okay, so that is why we have this final graph right here, which looks pretty good. So coming down, let's actually go ahead and implement this other example that we have. So the user is asking for weather in Chennai. So in this case, the researcher agent is going to kick in, right? You can imagine, because researcher is the one access to the Tavily search tool, right? So let's actually go ahead and run this. Okay, great. So you can see the supervisor is handing off control to the researcher. Why? The user has requested information about the weather in Chennai, which requires collecting current data. The task is best handled by the researcher, who can gather updated information. So this is the reason that the supervisor is providing, and using the command we are directing the flow to the the researcher. Now, what is the researcher saying? The current weather in Chennai is as follows. It is calling the Tavily search tool. It is providing the information right here. And then finally the validator. Okay, so the answer provides a detailed current weather thing. Okay, so that is it. So we have the final answer right here. And that is it, guys. This is how we can build out the supervisor agent architecture system. So do go ahead, pull the code, run it by yourself, try putting in different prompts. So there might be some prompts that might not work, and that might require some tweaking in the prompt. Okay, so that might require some changing prompts here and there according to the problem that you're trying to solve. And that is something that I will leave you to explore. And that is it for this particular section. I will see you in the next one. Hello guys, so in this video let's actually try to understand streaming in depth. So in the past few videos we did use streaming here and there, but we never really deep dived into it to an extent where we can actually build production grade applications. So I'll tell you what I mean. So this is an application that we are going to be building for the final Capstone project. So I've called it Perplexity 2.0 because we are sort of mimicking what Perplexity does in their UI, wherein if I were to ask something like or let me just say, hi, I'm Harish. In this case it's going to stream the tokens. So you can see that as and when the words are generated by the LLM, all these tokens are being streamed to the front end. And also if I were to ask a question like what is the current weather in Bangalore, let's say. So in this case, you can actually see all of the tool calls that are being done. So you can see that it's searching the web. This is the query that the LLM has suggested to the Tavily search. And then this is the response of the Tavily. It is actually pulling all of the information from these 4 different websites. And then finally, it's writing the answer. Right? So we can actually see that all these different things are being streamed to the front end, and we can actually see what the LLM is doing. So it's very important because just imagine if there is no streaming happening, the user is not going to know what is happening. So for a good 20 seconds, 30 seconds, the user is just going to stare at the screen. So this is exactly what we're going to learn in this particular video. So you can see that if we're building a responsive application for the users, real-time updates are key to keeping them engaged. Common use cases are, workflow progress, right? So we need to get state updates after each graph node is executed, LLM tokens as they're being generated. So that is exactly what we saw right here. And then custom updates, right? So when we talk about streaming in LangGraph, so we have the stream and asTream methods. So the stream and asTream are sync and async methods for streaming back outputs from a graph run. So there are several modes you can specify when calling these methods. So we can say graph.stream. This is actually very similar to how we say graph.invoke, right? So we say graph.stream, we pass in the initial state, and then right here, look at this. So right now we pass in values, but the common modes are we can either pass in values. This streams the full value of the state after each step of the graph. And then we also have stream mode updates. So basically this streams the updates to the state after each step of the graph. So let's actually look at a pictorial representation of the difference between stream mode updates and stream mode values. So if we set stream mode updates, we are only going to see what is the value that has been updated. Okay, so we know that the messages, okay, so this is node 1, 2, 3. So in node 1, it just updates A. Okay, initially the list would have been empty. So node 1 just updates A. Okay, node 2 basically would have appended B to the list. Okay, so that is why we are just seeing B, and the node C just appended C to the list. So that is why we are seeing just A, B, and C. And when we look at mode values, okay, so after the execution of the first node, we are going to get the entire state at that particular point, which is going to be a list with the item A. And then after the execution of node 2, we are going to see the entire state at that particular point, and the same thing for node 3 as well. So let us actually put this in practice. You can see that I have already gone ahead and created a file called stream events. So right here, you can see that this is going to be the picture that this is something that we've built already, right? So we have the start node, and then we have the LLM sitting right in the middle. And then we are just providing one tool, which is going to be in this case, the tably search tool, and then the tool node. So let's actually go and look at the graph structure. So we have the agent state right here, which is just going to contain the list of messages. We are initializing the tably search, and then we have the tools list right here. And then we are also, initializing the LLM, and then we are binding the tools with the LLM as well. And now we have the LLM with tools, right? So right here, we are defining the model node. We are just going to invoke and send in the entire list inside of this. And then the tools router is basically just going to take the last AI message, and then it's going to see if there is any tool calls needed at that particular point. And then if there are any tool calls that the LLM wants to do, in that case, it's going to direct the flow to the tool node node. And for this tool node, we are using the tool node pre-built method class right here, where we are also going to provide the list of tools as well. All right, so we're just connecting all these different things. And finally, we have a graph like this. This we have already seen. All right, so everything is looking good. So coming down. So in this case, we are actually going to put the stream method to use. So right here, you can see that what I'm doing is I'm saying app.stream, and then I'm providing the input. So the input message list is going to be what the first human message is going to be, what is the current weather in Bangalore. Okay, so I'm also setting the stream mode to values. So if you remember, when we set stream mode to values, so what that is going to do is right after the execution of every single node, it is going to emit an event. Okay, it's going to emit an event, and in that event, we are going to see the entire state at that particular point. So I am looping through the events right here. Okay, so this event is going to be an iterable. It is a generator. So anytime there is an event that is being emitted, that is being yielded from the generator, we are going to get this event right here, and we are going to print it down here. So let me actually go ahead and run it, and let me show you what it means. All right. So you can see that initially we have this one human message alone. Okay, so that is the only thing that exists. So why are we getting this particular object? We are getting that object because the start node just got executed. So at this particular point, the list only has one human message. And then after the execution of this LLM model, what should be there? There should be two items in the list, right? We have the first human message, and then we should have an AI message with an empty content field. And then we should have a tool call item, because this is a query that requires the LLM to use the tably search tool, right? So in this case, you can see that this is going to be the first item. And then if I come down here, you can see we have an AI message. As predicted, the content is not there because we actually have the tool calls, right? So we can actually see the argument here as well that the LLM is suggesting. So it is suggesting, okay, use this particular query, current weather in Bangalore, right? So that is all that is present right here. Okay, so it only has two different, okay, it's pretty long, but it only has two items in this particular list right now. So what next? What should be the next thing? Next, the control is going to come to this tool node. This tool node is going to take that query and then it's going to call the Tavily search tool, and that is going to output a tool message. So that is exactly what we see right here. We have the tool message. This is going to be the output. And finally, it's going to come back to the model, and then finally there is going to be an AI message. So that is why, in the last event that was emitted, here you can see that we would have the final AI message as well. It's going pretty long, but you get the idea. All right, I'm not even going to try at this point. Okay. All right, so great. So we have the AI message right here, right? The current weather in Bangalore is sunny with a temperature of 30.1 degrees Celsius, right? So we have 4 different events that were emitted, and each of these events had the full state after the execution of each of those nodes. So I hope that made sense. We can actually go and we can actually say something like messages right here, and this would probably give you, just the messages alone. Now let's actually go ahead and look at the updates. Okay, so if you remember, updates is just going to give you what is that new item that's been added to the list, right? So it is also going to provide you which node actually did the change as well. So let me actually run this and show it to you. So in this case, okay, so you can see that the first change was made by this particular model node, and then it updated something. Okay, so it just added this AI message at the very start. Okay, so that is all that we see right here. So this model node just added this AI message, and this tool node just added this tool message, and then this model node added this AI message, which has the final answer here. So let's actually take it to the next step. So if you remember what we did in the UI, we are not interested in getting the entire state after the execution of every single node. That's not what we're interested in. We are interested in getting every single token that is being generated by the LLM, right? So that is what we did right here. That is how we can actually achieve this sort of a UI, right? So to help us with that, there are other methods. Okay, so let's look at that. So let's actually look at some slides as well. So in production applications, we usually want to stream more than the state, right? So in particular, with LLM calls, it is common to stream the tokens as they are generated. So we can do this using the aStreamEvents method, which streams back to events as they happen inside the nodes. Okay, so we are not interested in what happens at the end of the node. We are interested in what happens within the node, right? So each event is a dictionary with a few keys. Okay, so in this case, every single event is going to be a dict, and it's going to have an event property, name, data, and metadata properties. So the event is going to be the type of event that is being emitted. The name is going to be the name of the event. Data is going to be the data associated with the event. And we are also going to have some metadata about which particular node emitted that event as well. I hope that makes sense. Let's actually now go ahead and put this method to use. So right here, coming down, you can see that I have used this particular method right here. So I'm going to be using something very simple right here, message, hi, how are you? We are not going to be using any tool calls at this particular point because we are learning. So I'm saying app.aStreamEvents, passing in this input. This also takes in 2 versions. Okay, so we've got version 1 and version 2. I'm going to be using the latest version. And all that I'm going to do is I'm going to loop through all of the events that are getting emitted and then printing it. Okay, so make sure to use this particular async because this is going to be an asynchronous operation. All right, so in this case, let's actually go ahead and run it. And you should be able to see that, the events are actually getting generated. You can see that there's a lot of events that are getting generated. We can actually use all these different things and then accordingly we can show it in the UI. So right here you can see that these are the event types, right? So these are the event types. So on-chain start, on-chain end, on-chat model stream, right? Okay, so on-chain end. So these are the event types, and what we are interested in is the streams, the event that are emitted from the LLM. So these are the things that are emitted from the LLM. Okay, so on chat model start and then on chat model stream. So inside, if you look at the data that is associated with this on chat model stream, you should be able to see in this particular chunk, we should be able to see this AI message chunk. Okay, so this is going to be the response. So you can see that it is saying, hello, I am here and ready to help you with any information or questions. So this is going to be the response of the LLM, right? You should be able to find all these different tokens that are emitted inside of the data in this particular type. So if you wanted to, we can also always use these particular types, right? We can always use these particular event types and then isolate it and yield it, isolate it and send it, stream it to the front end. So what I mean by that is, right here you can see that I'm only interested in this particular event called on chat model stream. And then I'm just going into event data chunk and then I'm printing it. Okay. So in this case, if I run it, it's going to be the same query as well. So if I run it, you should be able to see just that being printed. Hello, I'm just a computer program, so I don't have feelings, but I'm here, right? So if you want it to be in a same line, this print method also provides this end. So right here, we can just say, we can just give an empty string. Okay, so in this case, what's going to happen is it's not going to go to the next line. Instead, it's going to concatenate everything. So right here, you would have actually noticed that, it did not generate word by word. And the reason why that happens is because, it actually, this print method by default, it's going to, store some chunks together and only then print it. Okay, so to override that, we can actually use this flush true. And this is just going to flush everything from the buffer as and when, some value is actually stored in it. So in this case, if I actually go ahead and run it, you can actually see word by word, it is being generated. So I hope this makes sense. We can actually use these events. We can actually use the metadata. So if I actually go to the right side, okay, so inside of the on chat model stream, so this is the data, this we know. We can actually also go to the metadata. Okay, so we have the metadata right here, where we also have information about which particular node emitted, which particular node is responsible for this particular event. So in this case, the LangGraph node that is responsible for this event is the model node. Okay, so we can also use this particular name, this particular LangGraph node, and we can also add that in one of our conditions and then yield, we can isolate that and yield to the stream it to the UI. Okay, so it is completely in our control. We can actually make use of all these different, properties like event, data, metadata, etc., etc. So by the end of this course, we are going to be actually putting all these different concepts to use, and we are going to be building this particular application. So I'm pretty excited, and I'll see you in the next video. Hello guys, welcome to this brand new video. In this video, we are going to be building a full stack application using LangGraph in the backend. We are going to be using Fast API. We are going to be using React in the front end, and we are going to achieve something that is very similar to what Perplexity does in the UI. So I'm not sure if you've used Perplexity before, but it basically, it's basically like a very smarter version of Google. You can think of it like that, right? So if I were to ask some question that requires the AI agent powering Perplexity to actually make an internet search, the user, I can actually look at what is happening on the UI. So, I can see something like, it's searching the web right now. It is actually reading through all these URLs. It is actually giving a response as well. So I would be able to see all these different things. So that is exactly what we are going to be building as well. In addition to that, all these, it's going to remember our previous conversations, all these different words as and when the tokens are being generated, it is going to be streamed to the front end, so the user is not going to wait for anything. So let me actually quickly demo it for you. So let's test out the first thing. Okay, so there's a few errors right here. We don't have to worry about it, but let's just say hi, my name is Harish, right? So in this case, it's basically just going to, you can see that every single word is actually being streamed and it is shown in real time. So it says, hi Harish, how are you? How can I assist you today? In this case, I can ask like, what was my name again? So it should be able to tell, okay, your name is Harish, because it remembers the previous conversations. So this is a very small part. Now let's actually ask the agent something that is a little more tricky. The agent now has to actually make a Google search, an internet search, only then it can actually respond to it. So let's ask something like, when is the next SpaceX launch? Okay, so right here, it is actually going to, search the web. So you can see it's searching the web. This is the query. And then it is actually reading from all these different URLs, all these different pages. And then finally, it is saying that the next SpaceX launch is scheduled for Sunday, April 6th. So this is going to be a very exciting full stack application. So in the backend, in LangGraph, we are going to be learning how exactly to build this graph. It's going to be very simple. We are going to be learning check pointers for memory, for persistence. We are going to learn how to actually set up streaming. And if for some reason you're not a front-end developer, you don't want to, you're not interested in learning about React, etc., that is absolutely fine. You can just go ahead, steal my code, copy paste it, and it would just start working out of the box. So I'm pretty excited about this application. So first thing, let us now go ahead and start building out our agent graph. So let's now go ahead and build out our LangGraph agent graph. So once we build out our graph, we can then wrap our graph using an API endpoint, and then we can connect it with our front end, right? So you can see that I've already gone ahead, created a folder called Perplexity 2.0. I've created two folders, client and server. So right now the client and the server is empty. So let's now first go ahead and build out our server side code. So I'm going to open it using my Visual Studio Code. So let me just zoom in a little bit. So the first thing that I'm going to do is I'm going to install virtual environment. And we need the virtual environment because we want all our packages that we are going to be installing later on to be isolated in this one particular location. We don't want it to be available globally. So to initialize my virtual environment, I'm going to say Python 3. I'm saying Python 3 here because I'm working with a Mac right now. If you're working with a Windows, in that case, you can just say Python. And then I'm going to say -m. This stands for module. I'm using the venv module, and the folder that I want created right here, I want it to be named as venv as well. So right here, in a while, you can see that we have the venv folder created. All right. So the next thing is we have to activate this virtual environment. So right here, you can see that the path is not really pointed to venv, it is still pointed to base. So in order to activate this, since I'm working with a Mac again, I'm going to say source. Okay, I'm going to go inside of the venv, and then I'm going to go inside of this bin, and then I'm going to invoke this activate file. Okay, so this is going to activate my virtual environment, as you can see right here. In Windows, it's a slightly different command. You can look it up. Okay, it's pretty simple. All right, so now that we have the virtual environment initialized and activated as well, now I'm going to go ahead and I am going to create an app.jupyter notebook. Okay, and now there's a couple of packages that we might have to install in order to build out our graph. So I'm going to go ahead and install. First thing is I'm going to install LangGraph. We absolutely need LangGraph. And then I'm going to be using LangChain OpenAI chat model. Okay, we can always use other chat models. We can use Gemini, we can use Grok to access Llama models. But in this case, I'm going to be using the LangChain OpenAI chat model. And then we need the LangChain core package, and then we also need python.env because we want to make the environment variables available inside of our Jupyter notebook, right? And then we also need fast API, and then we also might need LangChain community, because in the LangChain community we can actually get access to a lot of tools like the Tavily search tool, etc. So if at all we need something else in the future, we can always come back here and then we can install it. So let's go ahead and install it. All right, great. So now that it has been installed, let's go ahead and import a few things. And guys, before we start coding this, I expect you to know LangGraph already. Okay, so I expect you to know LangGraph, LangChain, the fundamentals of it. I expect you to know how to build a React agent. I expect you to know the basics of streaming. I expect you to know, how persistence works, etc. If you do not know any of these fundamentals, I have created a course that I'll attach the link in the description below. That course is going to take you from absolute beginners to, pro level. We are going to be covering, what are the different types of agents, how to build a React agent, how to do streaming, how to do persistence, how to, what are check pointers, how to do human in the loop, how to build complex architectures like, the supervisor agent. So I would have covered everything. So I would expect you to know it already. If you do not know it, please go ahead, watch that, and then come back to this video. All right. So now let's actually go ahead and start importing our, modules. So the first thing is we are going to need from typing. Okay. So from this, we are going to need the type dict and the annotated and the optional. So basically, why do we need these things? We need these things because we want to define the state of our agent graph, right? And then obviously we are going to need LangGraph, and inside of the graph module, we are going to need the add messages method. This is going to be the reducer method, which is going to let us easily update the graph state. And then obviously we are going to need the state graph and then the end node. Okay, so what's the next thing? And the next thing is we are going to need a chat model. Basically, chat models are tools that LangChain gives us, which lets us interact, basically like interfaces, which lets us interact with LLMs, right? So in this case, I'm going to be using OpenAI's chat model. But if you don't want to pay for it, you can always go for Google's chat model, or you can go for Llama's chat model. All right. So just go to Google, search for chat model Google. In that case, it's going to give you a different chat model. You can import it and use it. But in this case, I'm going to be using the LangChain OpenAI, and I'm going to be using the OpenAI chat model. All right. And then obviously we're going to need the .env as well, because we want to load all our environment variables in this file. And then we are going to need the Tavily search tool. The Tavily search tool is what is going to let our agent access the internet. So in this case, we can actually go to LangChain community, and then we can say tools. And inside of this, I can access the Tavily search. So I can say Tavily search results. So the last thing that I want is the ability to persist our graph. So what I mean by that is we need memory introduced. So I'm going to be using a check pointer. That is the go-to way of introducing persistence in our graph. Okay, because we want our application to remember what the user said previously, right? So in this case, I'm going to be using LangGraph.checkpoint.memory. Okay, so from this, I'm going to be using the memory saver. And then after this, we also would need the UUID, because we will have to create unique IDs for each user session. So in this case, we might need the UUID. Let's use UUID 4. All right. So we are done with most of our imports for now. So now I'm going to go ahead and I'm going to create an env file. And right here, we need to add a couple of, environment variables for, the Tavily search. Okay. So for the Tavily search results, we might need the API. For the chat OpenAI as well, we might need the API key. So for the OpenAI API key, I'm going to go to platform.openai.com. I can go inside of the profile, and I can go inside of API keys right here. And now I can go ahead and create a secret API key. So I can just say perplexity, and I can go ahead, I can have the permission set to all, and I can go ahead and copy this. And the same thing for Tavily search as well. So I can just go to this particular link, log in, and then I can just go ahead. You can see that I've already created a few Tavily API keys. I can just copy this thing, come to the env file. So what would be the environment variable name? So if I go inside of the chat OpenAI, you can see that it requires this particular environment variable set. Okay, so just put the API key that you would have copied there inside of single quotes or double quotes right here. And then the same thing, you will have to do it for the Tavily search as well. So if you come inside of here, you can see that this is the environment variable. Okay, environment variable key. All right, guys, so I've already populated all the environment variables in my file. So in this case, I'm going to go ahead and load all the environment variables. And the first thing that I'm going to do is I'm just going to make a simple LLM call and make sure that everything is working fine. So in this case, I can just say this is going to be the model. So I can say the model that I want to use is going to be GPT-4o. And now let's go ahead and invoke this model. And we can say something like, give me a joke about cats, let's say. Okay, so let's get the response right here. Then let's also, okay, so let's try to run this. So you can see that running cells with this virtual environment requires the IPyKernel package. So let's go ahead and install that as well. All right, so now you can see that it is running, and it should give us a joke about cats. All right, perfect. You can see that we are getting an AI message back. We are saying that why was the cat sitting on the computer? So everything is working fine. If at all you're getting an error saying that, insufficient balance or something like that, just go ahead and top it up. You can go to the billing and you can top it up. It's going to last you anywhere from 3 to 6 months. I paid it several months ago, and you can see that it's still, I've still got a lot of balance. All right, perfect. So now let's get rid of this. And now let's also actually go ahead and test out our Tavily search. Okay, so I'm going to initialize our Tavily search. So in this case, I can say search tool. Okay, so search tool, Tavily search results. And in this case, I can just set the max results to 4 in this case. Okay, so now I can just go say search tool. Okay, what's happening? Search. Okay, so I can just say search tool dot invoke. Okay, I can say what is the weather in let's say what's the weather in Bangalore. So in this case, this is also going to give us a proper response. Okay, so I'm just going to test out all the environment variables, make sure that everything is working fine. All right, perfect. So now you can see that we are getting an array of 4 different objects. Each of these objects are going to have title, okay, and the URL and the content. Okay, you can see that there's quite a lot of content. Basically, the Stavely search is very similar to a Google search. Okay, it searches for this particular query. This is the URL that it pulled all this particular content from. So this is the query and this is the URL that it pulled all the content from, right? Okay, so we've got a lot of different information, which then later the agent can actually use. Okay, so the agent can actually make use of this particular tool whenever it needs to, needs that particular data, live data, and then it can actually make some informed decision. All right, perfect. So now that this is also working fine, I'm just going to clear this out again. And then we can just say tools. And right now we're just going to have this one search tool in the list of tools. All right. So what's the next thing? So next thing is we can actually go ahead and initialize our memory saver as well. Okay. So this is going to be the check pointer that is going to introduce persistence in our chat application. Now let's actually go ahead and create an LLM instance that is going to have access to these tools. So I can just say LLM with tools. Okay. So I can just say model dot bind tools, and then I can pass in all these list of tools right here. Okay, so what this is going to, let me actually put it in a separate code block. Okay, so what this is going to do is, now if I were to actually LLM with tools, now if I ask a question right here that is actually going to require some live data, okay, that is going to require live data, in that case the LLM is not going to give an immediate answer, but instead it is actually going to call the search tool. Okay, so if I were to ask something like, what is the current weather in Bangalore? Okay, so in this case, it is going to, let's see what it actually returns. Okay, tools is not defined, and that is because we have not run this. All right. So in this case, you can see that the AI message does not have any content, but instead, if I go to the tool calls, okay, so where is the tool calls? Let me actually search for it. Tool calls. All right. So in this tool calls, you can see that in this array, there is going to be one tool call. So the LLM actually wants to call the Tavily search results JSON because we've provided it. We've bound all the tools right here. Okay, so it actually wants to call this particular tool, and this is going to be the query that the LLM is suggesting as well. Okay, so now we have the LLM with tools instance as well. Okay, which is perfect. Okay, so what's the next thing? So now let's go ahead and build our graph. Okay, so let me copy paste some code right here. All right, guys, I've copy pasted a bit of code right here. So before I actually walk you through this particular graph, so I'll show you what is the structure of the graph that we have built. Okay, so if you've actually followed along with my LangGraph course, okay, this is something that we would have done a million times already. So you can see that we have the start node at the very start, and then we have the model. Okay, so the model, anytime the user question is something that requires the model to make a tool call, in this case, the control flow is going to go to the tool node. Okay, so in the tool node, this particular tool node is going to make use of the Tavily search, and then it's going to, take the query that the LLM has provided. It's going to make the internet search, and then it's going to return the response back to the LLM. Okay, and if the internet search is sufficient, in that case, the LLM is going to, end this particular graph. Okay, so this is what we have built right here. So if I scroll up here, you can see that we have, this is going to be the initial state. So to achieve this particular thing, we just need the messages list, and we are going to be using this particular add messages reducer function. So if you do not know how this reducer function works, if you do not know the different types in which we can update the state, all of these things I would have covered in the course. So do check it out. All right. So initially we have the first node, which is going to be the model node. Okay, so if I come back to the diagram, you can see that that is going to be the entry node right here, right? So we have this particular entry node. So this node is going to get the entire state right here, and we are going to be using the LLM with tools, we are going to invoke and we are going to pass in the entire list of messages, and then we are going to update the state with it. All right. So also another thing that I want you to note here is that we are going to be using the async await keywords. And why do we need to do that? Because when we are dealing with production applications and when there's going to be a lot of concurrent users, in that case, you don't want to block the thread. Okay, so we want multiple threads to be working concurrently. So in that case, we will have to use async await, and we will also have to use the a-invoke method and not the plain invoke method. Okay, the functionality is going to be very similar. All that we're doing is we're going to be using a-invoke and adding async and await in all our nodes. Wherever there is an async operation, wherever there is an LLM call that is being made or an API call is being made, we have to do async await there. So right after this particular model is executed, we are actually going to look at this AI message right here. Okay, so that is what this tool router is going to do. Okay, so it is basically just going to take the latest AI message. Okay, and then it's going to look at the tool calls. Does it have any tool calls or not? If it has some tool calls, in that case, it is going to route the flow of the graph to the tool node. Okay, so or else it's just going to go to end. So let's come inside of the tool node. Okay, so this is going to be the custom tool node that handles tool calls from the LLM. Again, we are going to take the, the last AI message. Okay, so this is going to take the last AI message, and then we are going to go inside of the tool calls. And from that tool call, we are going to get the name of the tool call. In that case, it's going to be the Tavily search results JSON, because that is the only tool that we've made, that we've provided to the LLM. We can also get the args. So in this args, this is where the query, the internet search query is going to be located. So we are going to get a reference for that as well. And then we also need the tool call ID. And then we are going to execute the search tool with the provided arguments. So we are going to provide all the queries and all the, everything that is inside of the args. And then this is going to give us the search results. So we are just going to stringify it. And then we are going to add the tool node in the tool message and the tool name as well. Okay, so now we have the final tool message that we are going to append to the list of tool messages, and then we are going to update the node as well. So this is going to be the function, the tool node function definition. There is also another pre-built, tool node class that LangGraph provides, because this is such a common thing, right? Okay, whenever we are working with agents, calling this particular code block is going to be such a common thing. So LangGraph actually wrote a class and then just gave it to you for us to use. So if I actually go back to, this is part of the LangGraph series that I'd worked on. So here you can see that in a lot of different sections, we would not have actually written this entire thing. We would have just used this tool node right here. Okay, so this LangGraph pre-built import tool node. And I would have just like instantiated this tool node, passed in the tools, and this would have been the tool node. Okay, so exactly what we've done right here. Okay, so we can either do this or that, but I'm doing it this way because this gives you a lot more, transparency on what is happening inside. But if I actually go inside of this particular tool node, you can see that this is basically what we're doing right here. Okay, so we're taking the latest AI message, we're going inside of the tool calls, and then we are invoking it, and that is it. Okay, so that is exactly what we are doing right here as well. Perfect. So coming down, we are going to be using StateGraph. We are building the graph. So the first node is going to be the model node. Okay, so that's going to be the entry point. And then we also have the tool node, and then we're adding a conditional edge. So right after the model is executed, we have to look at whether we have to go here or here. So that is why we have this tools router right here. Okay, so the tools router is going to decide if this tool calls is present, at least one item is present or not. If something is present, in that case, we have to go to the tool node, or else we have to go to the end. Okay, so I hope this makes sense. And finally, during the compilation step, we are going to provide the memory, the check pointer right here. So that is it. So now let's actually go ahead. Let me run this as well. And let's now go ahead and put this to test. So I can say graph.invoke. Okay, so in this case, in the messages array, I can use this human message. Okay, so I can ask something like, how are you doing? Okay, so let's just test it out. Response. Okay, so we are getting an issue right here. Okay, so this is because we are using the check pointer right here, right? So in this case, since we are using a check pointer always requires a session ID. Okay, so the graph needs to know which session is it storing the particular state for, right? So in this case, we have to actually go ahead and create the config object. Okay, so let's say config. Inside of this, we have to say configurable. Okay, in this we have to say thread ID, and right here we can say 1 or 2 or 3, and then we can provide this config right here like this. Okay, so now everything should work fine. Okay, so it's still not working, and that is because, okay, so to fix this, we just need to say a invoke, and then we have to await this as well. And now let's also go ahead and change it to, let's say, 5 or something. And now let's say let's introduce ourselves, and then let's ask what my name is, so that we can also test out the check pointer. So hi, I'm Harish. Okay, so in this case, okay, so you can see that we have the first human message, and then the AI message is saying, hello Harish, how can I assist you today? So let's actually test out the persistence, if it is working or not. So I can say, what is my name? So now you can see that all the past conversations are being carried forward, right? So we have the first thing that I sent, and now it is actually, remembering that my name is Harish. Okay, so now let's also try to ask a question that requires the agent to make an internet search. So in this case, I can say, when is the next SpaceX launch? Okay, so in this case, it would actually have to go, utilize the Tably search tool, and it would have to fetch internet results, right? So you can see that right after this particular question, you can see the AI message, the content is empty. In this case, it is actually, suggesting to call a tool, right? So when the tool calls, you can see that it is saying that, use this particular tool and pass this particular query inside of this particular tool as well. Okay. And then finally, what happens is we have tool message, right? So this is going to be the return, the response from the Tably search. This is going to have all the information. You can see it has pulled information from nextspaceflight.com. It pulled it from, a lot of different URLs, right? See, it pulled from spacelaunchschedule.com as well, right? And then finally, the last AI message is going to have the next SpaceX launch is scheduled for this particular date. Okay, so everything is working fine. And finally, I also want to show you how streaming works, because this is not what we want, right? We actually want every single token as and when it is being generated to be streamed to the front end, right? So what I mean by that is, so whenever I ask a question here, let's say what is the current weather in Chennai itself? If you remember, every single word was like streamed to the front end, right? It wasn't like, abruptly there. So this is going to give you abruptly. This is not what we're interested in. We want data to be streamed. So let's also get a quick rough, idea about how streaming works as well. And then we can all put it together later on. Okay. So I'm going to create another block. So in this case, I'm going to be saying graph. In this time, I'm not going to be using this a invoke or invoke. That is going to abruptly give you the final response. That is not what we want. In this case, LangGraph provides another method called a stream events. Okay, so this is what we are going to be using. So let me actually show you how this works. So in this case also, we can use an input. Okay, so where is the input? Okay, so we can actually copy the same input. So let's put it here. So in this case, I'm just going to introduce myself here. Hi, I'm Harish. All right. Okay, so what's the next thing? So similar to what we do right here, we are providing the config, right? We have to do the same thing here as well. Okay, so I can give it a different thread ID this time. I can say 6 this time. All right, and now what's going to happen is this is going to return us a generator function. Okay, this is going to give us something like, we can say events. Okay, so anytime there is an event getting emitted, we can actually loop through this iterable and then print it. Okay, so I can say for event in events, and then I can print this particular event. Okay, so I hope that makes sense. So this is going to be an iterable. Anytime there is an event getting emitted, this function is going to run. All right, this particular block is going to run. So now if I run it, I hope that everything is looking good. Okay, we have not provided the config right here. Okay, so we have not provided the config. And one more thing that I've forgotten is we also have to provide this version. Okay, by default, it's going to be v2, but still let's also go ahead and provide the version as well. Okay, so there is version 1, okay, and there is version 2. There's a lot more information being emitted in version 2, and that is what we are interested in. So let's actually go ahead and run this and make sure that everything is looking good. I'm not sure if we actually have to await it here as well. Okay, I'm not sure if we have to do it here or here. Let me actually run it. Okay, so we're getting the error. So in this case, it is saying that we have to actually use the async await. Okay, so right here, we are not using that, right? So I can do something like this. So I have just put the async for event right here. So we're using async to iterate over the async generator. All right. So now you notice that if I were to now run this, you should be able to see a lot of different events that are being generated. So you know that this is the question that I'm asking, or rather I'm just saying I'm Harish. In this case, you can see that a lot of these events are being generated right here, right? So you can see there's a lot of events. So you can see that we have on-chain start, okay? So we have on-chain, on-chat model start, on-chat model stream, okay? So all of these are event, okay? So this is a particular event item. This is another particular event item, right? So in one particular event object, we would have the event type, we would have data, right? We would have another property called metadata as well. These are some things that I would have deep dived in the LangGraph course, but I'll just give you a quick, overview as well. So, I'm not able to search for it, metadata. Okay, so you can see that we have metadata here. That is going to give you information about which node this particular event was emitted from. Okay, so we have all these different information through which we can actually isolate these events, and then we can yield it to the front end, right? So I can actually do something like this. So I can say, if event is equal to on chat model stream, because we're only interested in this particular event type, okay, I can just isolate that particular thing alone, and I can go inside of the data. So inside of the data, I can go inside of the chunk, and then I can just extract the content alone. So if I clear this file and if I change it to, let's say 7, and if I run this, it's pretty fast. So give me 100-word, essay on climate change, let's say, okay, change. So you should be able to see the words that are getting populated. Okay, so you can see that every single word was getting, streamed. Okay, so this is what we're interested in, guys. All right, so next up, we are going to transfer all these files. Okay, so when we are dealing with production applications, we are not going to be working with Python notebooks, right? So we are going to be creating a plain Python file. We are going to be, importing fast API. We are going to create an endpoint around this agent so that the front end can start accessing it. Okay, so that is what we're going to be looking at next. Hello guys. So in the last part, we built out our agent graph, but we built it out using the Python notebook. So basically what I have done right now is that I've created a new file called app.py. I basically transferred all of these code, okay, to a separate, Python file. Okay, so no difference at all. I have imported the same exact imports. Okay, so you can see that I'm initializing the memory, initializing the state. Okay, so we have the model node, we have the tools router, and then we have the tool node as well. And then I'm connecting all these different things together. So up until here, we've completely already seen. Okay, so coming down, this is the new code that I have added. Okay, so it's going to be very simple. All that I'm doing is I'm importing fast API. Okay, from fast API, I've installed that as well. Okay, so coming down, you can see that I've initialized the fast API app. I'm adding some middlewares. Okay, so this is basically just to, for our browser, for our client to be able to communicate with the server endpoint without any issues, without any cost issues. I've added these things. All right, so here, look at this thing. So we have the chat stream. This is going to be our endpoint. So whatever new message that the user in the front end is going to enter, that information is going to come right here. Okay, so that is what we are accepting in this particular argument. And the second argument is going to be the checkpoint ID. Okay, so this checkpoint ID, this is going to be provided as a query parameter. Okay, so if at all the client does not provide a checkpoint ID, that is completely fine. In that case, we are going to default to none. Okay, so we are going to default to none. But if they do provide something, in that case, we are going to accept it. And okay, so let's pay attention to what we are doing right here. Okay, so if it was a simple, if you're not thinking about streaming or anything like that, we can just go ahead and, we can just say graph invoke or a invoke. In this case, we can just provide the message inside of this, and then we can use this particular checkpoint ID as well. It's going to be very simple, but since we are interested in streaming right now, okay, so in Fast API, we are going to be making use of this concept called server sent events. Okay, so it's going to be server sent events. Okay, server sent events. This is for your own education. You can definitely Google it, research more about it, learn more about it. But essentially, server sent events is slightly different from WebSockets. Okay, so what are the difference between server sent events and WebSockets? WebSockets essentially, establish a consistent connection between the server and the client, and both the client can communicate the server as well as the server can communicate with the client, right? It is bidirectional. But in our application, in our project, that is going to be an overkill. What we need in our chat application is going to be server sent events. So what this means is that the server can actually communicate with the client. Okay, so it's going to be one directional, not bidirectional. This is what we need. So the way that we can do this in Fast API is that we can use this streaming response class that Fast API provides. Okay, so streaming response. So the first thing that we have to provide in here is going to be the generator function. So the generator function is just going to, emit events. Anytime it receives something, it's just going to emit it. And then the second thing, this is very, very important. Okay, so in the media type, we have to set it to text event stream. Okay, so this is going to be the protocol that we are going to be using, the server sent event protocol. All right, so let's actually take a look at this generator function. Let me now expand this thing. All right, so first off, we are going to check if the checkpoint ID is there or not. So if it is a new conversation, we have one if block right here. If it is an existing conversation, we have another else block right here. So let's look at the first block. Okay, so the first thing is we are going to generate the checkpoint ID, and then we are going to construct the config object. And then we are going to be using the same aStreamEvents method that we just looked at, in the IPy notebook, right? So we are going to be using the aStreamEvents. We are going to provide the message that is received. We are going to use the same thread ID. Okay, and then this is how we are going to be yielding. Okay, so this is what, this is a generator function is going to emit the events, or we can also say it's going to yield events. So if we put yield right here, okay, this is what we are going to be sending back to the client. So we are going to be looking at exactly how the data looks like using a Swagger docs. Okay, Fast API provides a very easy way for us to actually look at exactly what is being emitted from the API. So we'll take a look at that. So here you can see that we are the type is going to be checkpoint, and we are going to be providing the checkpoint ID. So you might think that why are we using all these // It's basically just to escape this particular double quotes. Okay, so we can't use double quotes within double quotes without escaping it like this. Okay, so that is why we are yielding it like this. And if you're wondering why we are saying data right here and why we are saying /n right here, so we have to say that because that is basically just how the server sent event protocol works. This is how the browser is going to know that this is going to be a server sent event. Okay, so we just need to follow this. All right, so now we've seen this particular if block. Let's now move on and let's understand the else block. So let's say this is going to be a continuing conversation. In that case, we are going to be using the checkpoint ID that we get from right here. Okay, so we are getting it from right here. So the server knows exactly which session to continue the conversation. Okay, and then the same thing is again continuing. Okay, the same thing. And coming down right here, you can see that we are getting reference to the event type, and then based on that we are doing a couple of things. Okay, so for every single different event type, we are structuring it in a certain way and then sending it to the client so that the client can differentiate between each event type. Right, so the first event type that we are interested in is the on chat model stream. This is going to be a very basic, this is going to be the most common thing that we are streaming. So what I mean by that is, let's come back to our Jupyter notebook. So if you remember, okay, so let me say, okay, I've just said that give me a 100-word essay on climate change. In this case, you can see that this is going to be, the events that are going to be emitted when the LLM is actually generating something. something, right? So this is when the LLM is starting to generate, and this is when it has started generating already. So that is why we see, you know, the empty array, empty string. Climate change refers to significant long-term changes in global or region. So this is what I am going to be grabbing next. Okay, so how can I grab it? So you can see that I'm passing the event data chunk inside of this particular method. It's just going to be a fallback method. Let me show you what it means, but I'm going into event data and chunk. So this is going to be the entire event. I'm going to go into data. I'm going to go into chunk. Okay, so I'm grabbing this AI message chunk. I'm passing that inside of this method. All this method is going to do is it's just going to check if this chunk is an instance of AI message chunk. Okay, so there might be some situations where, you know, there could be something going wrong. In that case, I'm just going to, show an error. Okay, so that is all that this is doing. So we're grabbing this content. So this particular content, I'm grabbing that particular content, and then I'm just going to, escape single quotes and new lines for safe JSON parsing. Is just, this is safe content. And finally, I'm going to be yielding this particular data to the client. Okay, so we are going to have, data and the /n/n. This is just protocol. Okay, the server sent events requires you to add this and this at the start and at the end, and this is going to be the JSON that we are going to be sending to the client. Okay, so this is going to have the type. Okay, it has the escape characters. Okay, because we are using double quotes within double quotes, but the type is going to be content, and the content itself is going to be this particular safe content. Okay, so we are emitting this thing. Similarly, we are also emitting another event type called on chat model end. Okay, so we are emitting some data. Why are we doing this? So let me actually show you why we are doing this. So in this case, I'm going to change the thread ID, and I'm going to say, I'm going to make use of, I'm going to force the agent to use a tool call. Okay, so that I can show you why we're doing that. So I can say, when is the next SpaceX launch? Okay, so if I run this, okay, so we can see that the LLM has started to generate. So right here you can see that all these on chat model streams, the content is not going to be there. Okay, because if I come back to the end, okay, so this is where the LLM is done generating something. So in this case, you can see that the content is going to be empty, and it has completely shown that we have to call this particular tool call. Okay, so you can see that it is saying that use this particular query, use this particular tool, and then do an internet search. Okay, so this is what we are grabbing. Okay, so we are grabbing this thing so that in the UI you can see that we are showing this particular, we are showing this particular thing. Okay, so searching the web and the next SpaceX launch date. So in order to show both of these things, we need to grab this on chat model end. Okay, so sometimes the tool calls might be there, sometimes the tool calls might not be there, but we are only isolating when there might be tool calls. So that is exactly what we're doing right here. So we're checking if the tool calls are present or not. Okay, if it is not present, it's going to be an empty array. And then we are looping through it, and then we're checking if there is at least one tool call where the Tavily search is needed. So if it is not there, no problem at all. But if it is present, in that case, we will have to start showing this, searching the web, all this. Okay, so that is why we are emitting a different event. So what I'm doing, I'm just going to grab the query alone. So you can see that we're signaling the search is starting. We're again escaping, this is some parsing that we're doing. And then we are yielding a different type. Okay, so here we saw that we were, yielding a type content and the content name. In this case, we are going to be yielding type search start. And then we are passing the query as well. So this is how the client can actually differentiate between, what is what, right? So we might want to show a different UI or something like that. In that case, the client can easily differentiate based on this particular type. So in this case, it's going to be search start. All right. So what's the next thing? So we are also emitting this on tool end. So what is that? So if I come down here, we have this on tool start and on tool end. So it's only in the on tool end where we are having the full response of the Tavily search tool. Okay, so this is where we are seeing the entire, the 4 URLs that it pulled the data from. So this is where we are able to see everything. So this is why We don't want the on tool start because we are not going to have this particular information at that point. So that is why we are grabbing a hold of this on tool end event. So that is why I'm taking the on tool end event, and I'm also making sure that the event name is Tavily search. Okay, so there in the future, if you want to extend it, there could be multiple tools, right? In that case, you will have to add these conditions as well. Okay, so I'm grabbing the output. So this is going to be the output. In this case, it is going to be a list, right? So the response of the Tavily search is going to be a list of 4 different items. Each item is going to have the title, it's going to have the query, etc., etc. Okay, so that is exactly what I'm going to loop through, and I'm just going to grab the URLs, okay, because for the UI, I'm just going to show the URLs. So that is why I'm just providing the URLs. Okay, I'm converting the URLs to JSON, and finally, we're just going to be yielding it. So in this case, the type is going to be search results. Okay, earlier it was search start, and now it is going to be search results. All right, and finally, we're just going to send an end event. Okay, so this is going to be the complete server side code. So what I'm now going to do is I'm going to make sure let me just close this up. I'm going to run this file. Okay, so I can run it by saying uvcon. Okay, so uvcon is going to be, if you've worked with Node.js, we've got nodemon, right? Okay, similar to that, we've got uvcon in fast API, and we are going to go into this particular app.py. So that is what this thing stands for, the first part. And then the second part is going to reference this particular variable. Okay, where is it? So we are going to reference this particular variable. Okay, so this is going to be the fast API instance. Okay, so we're getting a reference to that. And then we're also saying -- reload, because if at all we want to make some changes, immediately we want the server to be restarted automatically, right? So that is why we are saying reload as well. So let's now run it, and I'm going to be testing this API endpoint. So I'm going to be testing this using Swagger docs. So if you do not know what Swagger docs is, it's basically like Postman, but it is something that fast API provides out of the box that we can actually use to test our endpoints. Okay, make sure that everything is working fine. So to access it, I can just say docs, and this is going to give you a very nice UI about all the different endpoints that we've written. In this case, we only have this one endpoint that we've written. So chat underscore stream and then messages. So if you click on it, you can see that it automatically shows you, okay, we have to provide this particular message, which is going to be required, and we can optionally provide the checkpoint ID as well. So I can click on this, try it out. So in this case, I can say something like, what is the, let's say, current weather, okay, weather in Delhi. Okay, so if I do that, you should be able to see all the different events that are emitted. Okay, it's taking a while. Okay, great. And right here, you can see that the first event that was emitted contains the checkpoint ID. So the client can actually grab a hold of this, remember it for future requests. All right. So since this is a query that requires tool calls. So in this case, it is going to return some empty content. Okay, so in this case, it's not going to do anything on the front end. And then you can see that search has started, right? This is we on the client side, we can grab this thing and then we can show a nice UI like this one. Okay, search has started, and we can also, we also have access to the query, right? We also have access to the query. All right. So once the search is done executing, once the Tavily is done executing, we are also getting another event where we are getting all the URLs. Okay, all the 5 URLs, 4 URLs, I think. And then we can make use of that as well, and we can show it right here. Okay, so I hope that you are able to see how it's all coming together. And just one hiccup, guys, one thing that I ran into when I wanted to run this code, one thing that I ran into was that there was a certificate issue that I kept getting when, the agent wanted to run the Tavily search. Okay, so this is going to be the fix, guys. So in the README, so all that I did was I just installed certify, and then I just put this particular line in the terminal as well, and that fixed the issue for me. All right, so let's move back. So what happens next? So right after we show all the URLs, okay, then we have access to the type content again. right? So we can now, okay, get all these different keywords, okay, all these different tokens that are being generated. So it's all going to be part of the type content, right? And then we can actually show it right here very neatly. So I really hope that you are starting to see how it all comes together. So in the next part of this video, we are going to be building out the React front end. So I'm pretty excited. I'll see you there. Hello guys. So in this section, we are going to be building out our UI using React, and more specifically, we are going to be using a React framework called Next.js. And again, if you're not a front-end developer, that is completely fine. You can just pull this code, clone this repository, and then just put in the commands that I tell you to put in. Okay, so you just need to run this npm run dev, and that is going to spin up the server, and everything should work perfectly fine. Okay, but if at all you are interested in front end, okay, so this particular part is for you. If you're not interested, always skip over it. But it would still, I believe, it would still help to know on a very high level how things are working on the front end. Okay, so to start off with, I'm going to be using, as I said, I'm going to be using Next.js, which is going to be a framework of React. Okay, so if I go to react.dev, you can see that Next.js is something that React recommends as well, and this is the command that I ran. Okay, so basically open a directory and then run this particular command, and that is going to give you this boilerplate code. Okay, so once you have this, this is where everything is going to start. Okay, so this app folder is going to be present in this brand new project structure. Okay, inside of this, you would also find a page.tsx. This is going to be the file where the topmost component in your entire application is going to sit. So what I mean by that is, if I just go and, okay, so if I just, let's say I get rid of all of this and I just say something like hello world. So if I save this and I come back to the UI, you can see that it says hello world, right? So let me actually go back. Let me undo all of the changes, and now you can see we have the earlier UI, right? So this is going to be the topmost file, and this home is going to be the topmost container that is going to be the starting point of our application. So if I scroll down to the very bottom in this return part, you should be able to see we have the header and the message area and the input bar. So what are these three things? This header is just going to be the static. Okay, it doesn't do anything actually. Okay, it's just going to be there for the aesthetics, right? And then we have the message area, and this message area is for whatever shows up in this particular window. Okay, so if it is a user, it should come on the right side. If it is not a user, it should come on the left side. So all these things are going to be taken care of by this particular component, the message area component. Okay, so we don't want to go too deep in the weeds and try to figure out what is doing what. If you want to do that, just pull the code, and then you can take your own time with it. But since this is not going to be a front-end focused course, I'm going to be skipping over it quickly. So we have the header, message area, and then finally we have the input bar. Okay, so this is what we're talking about. So anytime we type something in here, we are going to be grabbing a hold of that current value, and then we're setting the current value right here. And then anytime an enter is pressed, in that case we are going to fire this particular event handler called handle submit. Okay, so this is the UI part. Let's scroll up and let me show you what we're doing right here step by step. We are maintaining the list of messages right here. How can I help you? This is something that we are hard coding right here. Okay, so we are assigning it an ID, a message ID, and then we are also having this is user property, and that is going to be false in this case, right? Because this the AI is only asking this particular message, right? So it's going to be false, and the type is going to be message. So there's going to be different types of data that is going to be populated here, right? So in some cases it could be the search query, some cases it could be the search results. In all those cases, the type is going to be different. Accordingly, we can show different UI for that. Okay, so before we move on to that, let me show you what are the other things that this object could possibly hold. So this is going to be a TypeScript interface. You can see that ID is going to be a number, which we've already seen. The content is going to be string, which we've already seen, is user, and then the type, and then is loading. Okay, so right after the request hits the server and before the LLM actually starts generating something, we are showing a typing UI, right? So if I say I'm Harish, okay, so in this case you can see there's going to be a typing UI, right? So that is going to be maintained by this is loading, okay? And then we have this search info, right? So this is going to contain stages, query, and URLs. So stages is basically like, initially we could be searching the internet, okay? Searching could be a stage, and then reading could be the next stage, and then writing, right? Okay, so these are the different stages. Why are we maintaining it? I'm just maintaining it because to show the UI in a certain way. Okay, so let me show you what I mean. So I'm going to be using the same query that we've been using. So I'm going to ask, when is the next SpaceX launch? Okay, so in this case, okay, so you can see that we are searching the web. That is going to be one stage, right? And then we are reading it, and then we are writing it. So it's all going to be part of this entire thing is going to be part of one particular AI message response. So that's how we can think about it. Okay, so it's all going to be part of one message. So we look at that. So, okay, so this is going to be the main method. Okay, so 99% of all the logic is going to be maintained at this one handle submit method. Okay, so whatever happens when we, type something and we press enter, so this particular event is going to get triggered. So coming down, so this current message, okay, so whatever the user is currently typing, that is going to be maintained here. And then we are going to create a new message ID. Okay, we're just going to grab the maximum ID that is present in this existing list, and then we're just adding one to it. Okay, so that is all that we're doing. And the next thing is we're just grabbing the current user message, and then we're updating the state right here. Okay, so this is going to be a synchronous operation. So immediately we can just add this new item in the list of messages. So you can see that, I'm Harish. If I say this thing, immediately we expect it to show up here. Okay, so that is what this thing does. And then let's look at what we're doing. Okay, so we're clearing it out because we don't want it to linger on here. Okay, we want that to be cleared, so that's why we're clearing this out. And then this is where the actual the streaming, receiving all the streamed chunks is going to happen. Okay, so inside of this try block. Okay, so the first thing that I'm doing is I'm going to create a loading. What we do is when we type something here, we can see that there's something loading, right? So essentially what we're doing is we're creating this AI response ID. Okay, we're setting the content to empty string. The user is false, so that it shows up on the left side and not on the right side. The type is again going to be messages. We're setting the is loading to true, okay, because the chunks would not have started to come yet, right? And then search info. None of these stages would have started to happen. And the next thing is we are constructing the URL. Okay, so we know that this is going to be the API endpoint, right? So this is going to be localhost 8000, exactly where our server is listening to, right? So we are going to grab this particular URL, and then we are going to construct this entire URL. We are passing in the user input as well. So whatever message that the user has entered, that is going to be set right here. And then we're checking if the checkpoint ID is present or not. Initially, the checkpoint ID is not going to be present. So we are going to come down. And then this is very important, guys. So we know that we are dealing with server sent events on the server side, right? So how is the client actually going to, know that, events are getting emitted? Okay, so something is being streamed. So how do I capture it? So the browser actually gives you this particular browser API called event source. Okay, so this is going to be very important. So we are using this to connect the server sent event endpoint using event source. Okay, so we are providing the URL right here. We are initializing it. Okay, so anytime there is any event at all being consumed or received on the client side, this particular event handler is going to get, this particular callback function is going to get triggered. Okay, so this is where most of our logic is going to be done. Okay, so in case there is an error, this particular block is going to be executed, but you can see that that is going to be the end of it. So let's look at what is the first thing that we're doing. Okay, so from this event, we are going to get whatever data that was sent from the server side. Okay, so we're extracting the data from that, we're parsing it, and then we now have the object right here. Right now we're checking what type is it. Okay, so there's a couple of different types that we're checking for. So now you can see that we have like 6 different types that we are checking for. We had the checkpoint type, we had the content type, search start type. Okay, so if it's checkpoint, we're just going to store it on the client side using this particular use effect. Okay, so that for the next follow-up question by the user, we can just attach it. Okay, so that's what we're doing right here. Okay, so we can just where is it? So if it is there, we're just going to attach it in this particular query param. So this way the server is going to know, which particular session it is, and it can continue the memory from it, right? So coming down, so this is going to be data type checkpoint, and then we have the content. So if you're dealing with the content, we are just going to, whatever data is being received, we are going to, add it to this streamed content variable. Okay, initially it's going to be an empty string. We're just adding. So, if it says, hi Harish, how can I assist you today? So initially the content is going to be hi, and then, okay, it's going to append it. Okay, and then it's going to add it to this particular streamed content. And then as and when it is coming, we are also updating the state right here. Okay, so that we can actually reflect it in the UI. And then let's move on to the next thing. So we have data type search start, right? So along with this, okay, let's search for the search start in this thing. So you can see that along with the search start, we are going to provide the query as well, right? So whatever the internet search query, so we are going to grab a hold of the query. We are going to add it in the state as well. Okay, so the URL is still going to be an empty string. And then as usual, we are going to update the AI message with the search info. The same thing for the search results as well. So we're looking at, the data URLs, okay, and then we are going to update the URLs right here. So we are going to get the URLs from here, okay. So if I search for the search results, you should be able to see that we are sending the URLs, right? So we're grabbing a hold of that, and then we are updating the state again. So the minute we update the message there, we are going to show it in the UI. And then finally, we have the end event. So if we get this end event, we are just going to close the event source. Okay, so we don't have to keep it open more than we absolutely have to, right? So we are going to immediately close it. And that is it, guys. So if you are interested in, what we are putting inside of the components, it's just going to be some, Tailwind CSS. It's just going to be some, animation. We are using some animation, etc., etc. And even if you're not a front-end developer, guys, and even if you don't, understand this code, it's going to be pretty simple. Just copy paste it to ChatGPT or Claude, ask it to walk you through it, and I'm sure it would start making sense. So that is it for the front-end code, guys. So the next part is going to be, we are going to be deploying our server code. We are going to be deploying our AI agent. So I'll see you in the next section. Hello guys, I'm excited. Welcome to the last part of this course. We are going to be deploying our application. Okay, so far we built the server side code, we built the graph, we've tested it locally, but eventually we will have to deploy to production, and that is exactly what we're going to see. There's quite a lot of different ways to do it. My favorite way is to do it with Docker. Okay, so this is going to be the backend code. I haven't touched it at all since the last time we saw it. So the only two things that I've added to this repo are this particular Docker file and this Docker ignore. Okay, so this Docker file is going to have all the instructions that is necessary to put the project together in a different server, okay, in a public server. So I expect you to know some amount of Docker already. So here is what I'm doing. I'm basically going ahead and pulling a Python image, and then we are setting this work directory to be app. So inside of the Docker container, we are telling, okay, create an app folder, and then we are going to copy this requirements.txt, okay, into that particular app folder, and then we're also installing this in requirements.txt. Okay, and then we are going to copy the rest of the application code, including everything, right? Okay, so we don't want this IPYNB, so we can actually go ahead and delete it. I'm just going to keep it around in case we might need it for something. But actually, when you're running, when you're building this image, okay, we can actually go ahead and delete it as well. So we're essentially copying the rest of the things and then moving it inside of the app directory. And also we don't want to move the contents of the environment file as well. So that is exactly why we have this Docker ignore file as well, where we're going to put in all the different files that we want Docker to ignore, right? So we are going to copy the application code, and then finally we are going to expose the port 8000. And then this is going to be the command to run the application. Okay, so these are some things that you would recognize, right? Uvicon app, right? So this is what is going to spin up our container. All right. So once we have the Docker file and the Docker ignore setup done, So now it is time for us to start building our image, right? So once we build out our Docker image, we can then, use a cloud provider. So I'm going to be using Render. Okay, so you can use DigitalOcean if you want. I'm going with Render because they offer a free tier, and it does have some downtimes. Like, if you don't use the server, it is going to, take some time to spin up again. So there are some, drawbacks, but since we're just learning, this is going to be ideal for us. And then for the different steps that we have to do, like, building the Docker image, testing it locally, right? Okay, pushing to Docker Hub. You can see that I'm actually using my own API keys right here. So I want this to be extremely easy for you as a viewer to follow along. So I'm going to be removing all these API keys as soon as I upload the video. But yeah, this should make it extremely easy for you to follow along. Okay, so the first step that we have to do, okay, so you can see that this guide contains exact commands with your credentials for building, testing, and deploying your Perplexity app. So that's what I'm calling it. So personalized Docker and Render deployment guide. So step one is going to be, we have to build the Docker image. And if you're wondering why we have different commands for, Apple Silicon and the rest of it, and that is because Apple Silicon has a different processor, and if we build the image in a different processor, we cannot actually use Render because Render only accepts this AMD 64 processor. So that is why we are using this, and then we are making it standard. Okay, so let me actually copy this thing. This is going to be the first command. Okay, and then I'm going to copy this entire thing and then put it right here, and that is going to go ahead and start building my Docker image. So this might take some time. And if at all, you're using Windows or Linux or Intel Macs, in that case, just say Docker build -t Perplexity latest and a dot here as well. Okay, so why do we have this dot? We're just saying that it is in this particular root directory where we have this Docker file. So we're basically just giving it the location to our Docker file. All right, so while this is taking some time, let's go ahead and let's move on to step 2. So whatever image that we built right here, we are going to run it. Okay, so we are going to run it as a container, and we are going to test it. We have to say Docker run. So this is how we run an image. Okay, so this is how we run a container, and we are saying -d. This is a detached mode. Okay, so we don't want to worry about all the logs. Detached mode, and then we have this -p. So what this means is we are specifying the ports. So the container itself is going to have ports. Okay, so that is what we are saying, that okay, in the container use the 8000 port, and once the container is running, if you want to if you want to access that port inside of that container, use the localhost 8000. So that is what we are saying right here, 8000. So this 8000 is going to be the port of the container. This 8000 is going to be the port of the host machine. All right, and then we are going to set the OpenAI API key. We are going to set the Tavily API key, and then we are going to give this container a name called Perplexity container. Okay, and then the image that we are going to be using is Perplexity latest. Okay, so the same thing that we mentioned right here. Okay, so let's actually go ahead and copy this, and let me see if it is done. Okay, great. So you can see that the image has been built. So now let's go ahead and run this image. Okay, great. So now you can see it has given the container name. So if I actually go back to my Docker desktop, so right here you can see that we have the container running right here, right? So we have Perplexity latest, which is currently running on port 8000, right? So I can just come back to Chrome and I can go to localhost 8000. Okay, so now you can see that if I actually go to docs, you can see that we are actually able to access the endpoint and everything, right? So this is actually amazing, right? So you can see that we don't actually have any server running right here. So we're directly listening to this particular server. It is actually the container that is running our entire Python server, including all the LangGraph files as well, right? So now we know that the container is working fine. Now let's go ahead and push it. So let's actually look at what is the next step right here. Okay, so the next step is basically to push to Docker Hub. So now let's actually go ahead and we can also stop this particular container. Okay, we don't want it to be running because we now want to push it. Okay, so it's been stopped. and then we can also, do this particular command as well. So now let's go ahead and log in, okay, to Docker Hub so that we can actually push it to Docker Hub. So once we have it available in the repo in the Docker Hub, we can actually, go inside of a public server and then pull it, and then we can build the same image there as well. And then we can have our application be available globally, right? So I'm going to go ahead and say Docker login. Okay, so I can say Docker login, authenticating with existing credentials, username Harish Neil. Okay, so it's because I've already logged in. But if you have not logged in, it's going to, you can just provide your credentials and it's going to log you in. Okay, so what is the next thing? So the next thing is we have to tag our image with your Docker Hub username. Okay, so this is going to be the command Docker tag Perplexity latest. Okay, and then this is how we can actually do it. So let me copy it, put it over here. And now let's go ahead and push the image to Docker Hub. So we say Docker push, and this is going to be the username of my Docker Hub. So if I go here to Docker Hub, okay, so you can see that this is going to be my username, right? So Harish Neil is going to be my username. So that is exactly what it is showing right here. For you, it is going to be something else. And as you know, this is going to be the name of our image, right? So this is going to be the tag as well. So let's copy this entire thing and then let's go ahead and push it to Docker Hub. So you can see that it's preparing, waiting. So now it's actually going to be publicly available for, the world, right? So let's actually wait for a little bit. Okay, great. So it is done pushing. So if I actually go to Docker Hub right here, and great, you can see that it has been pushed less than a minute ago, right? So this is what we want. And now this is actually available publicly. So the next step is going to be very simple. Okay, so let's actually go back to our artifact. So we are going to be deploying on render, right? So I can go to my dashboard. Okay, so I can click on add new and I can click on web service. Okay, so right here, I can click on existing image. So in here, I can actually provide the Docker image URL. And for you, the username is going to be different. For me, this is going to be the image URL. So let me copy this and put it over here. Okay, great. So you can see that there is a tick mark right here. So I can now go ahead and click on connect, and then you can create a project if you want. I'm not going to do it. I am going to go for the free version right here. I can leave this region as it is. So coming down, this is where we have to provide our environment variables. So we have to provide the OpenAI API key and we have to provide the Tably as well. So I'm just going to quickly go ahead and copy that. So I'm just going to copy this, put it over here. This is going to be the OpenAI's. This is going to be the Tably's. All right. And that is it. So now all that I have to do is deploy this. So right now what's happening is, render is automatically pulling the image from Docker Hub because it's now been made publicly available. It's pulling it and you can see that it is actually, running it. It's building it in its own server and it's going to make our application available to the world. So you can see that the service is now live. And now you can see that up here, it provides me the new API endpoint. I can just copy this and I can actually go ahead and run this. And you should be able to see that we can actually access the Swagger docs of our deployed application, okay, in this particular endpoint. Okay, so now what I can do is I can just copy this endpoint, come back to my client side code. Okay, so right now it is actually pointed to our local host, right? So instead of this, I can actually, replace this. Let's remove this docs. Okay, let's save this file and let's actually now go ahead and see if, everything is working fine. So in this case, I'm going to say, I'm Harish. How are you? Okay, so now you can see that it is actually working, guys. So our application is successfully deployed on render. So if I actually inspect it and show it to you in the networks tab, you should be able to see calls going to render right now. So I can say, what is the weather in SF? So in this case, you can see that all the calls are actually going to Perplexity, right? Okay, so it's going to onrender.com, right? So perfect. So everything is working as expected. So if you want to go ahead, deploy the front-end code as well, that is pretty easy. There's a bunch of tutorials out there on how you can deploy a Next.js application on Vercel. And if at all you want to steal the code, I don't mind at all. Please go ahead, pull the code, clone it and then change the UI a little bit and then go ahead and put it in your list of portfolio projects. So I don't mind absolutely at all. Okay. So, and that is it, guys. I hope you learned a lot and I'll see you in the next video.